something's out there. Something massive, something cold, something so distant it takes 10,000 to 20,000 years to complete a single orbit around our sun. We haven't seen it. We can't photograph it. Yet the mathematical evidence suggests it's real, and it's 10 times more massive than Earth. This is Planet 9, a world that shouldn't exist according to everything we thought we knew about our solar system. But the math keeps pointing to the same conclusion. There's a giant lurking in the darkness beyond Neptune. In 2016, two astronomers at Caltech made an announcement that sent shockwaves through the scientific community. Konstantin Batygin and Mike Brown claimed they'd found evidence for a ninth planet, not through direct observation, but through pure mathematics and computer simulations. The prediction was bold. The implications were staggering. And the astronomical world split into believers and skeptics almost immediately. Here's what makes this different from every other "maybe there's something out there" claim. The evidence doesn't come from a single strange observation or a blurry photograph. It comes from watching how dozens of distant objects move, objects so far away they barely reflect any sunlight, objects that take thousands of years to complete their journeys around the sun. These frozen worlds are telling us something. Their orbits are aligned in ways that shouldn't be possible unless something massive is pulling on them. 6 of the most distant objects we've ever discovered all point in the same direction. They tilt downward from the plane of our solar system at nearly identical angles. The odds of this happening by random chance? About 1 in 500. Those aren't lottery odds. Those are "something's definitely going on here" odds. But let's back up. How do you lose a planet? The story begins much earlier than 2016. It starts over a century ago with an astronomer named Percival Lowell. In 1915, Lowell became convinced that something was disturbing the orbit of Uranus. He called this hypothetical object Planet X, where X stood for the unknown, not for the Roman numeral 10. Lowell died in 1916, never finding his mysterious planet. But his search continued at the observatory he founded in Flagstaff, Arizona. In 1930, a young astronomer named Clyde Tombaugh discovered Pluto. For decades, astronomers believed they'd found Lowell's Planet X. Pluto was celebrated as the 9th planet, the final member of our solar system family. Except there was a problem. Pluto was far too small to cause the gravitational effects Lowell had predicted. It turned out those perturbations to Uranus's orbit were measurement errors. They weren't real. The search for Planet X was based on a mistake. Pluto's story took another turn in 2006. The International Astronomical Union redefined what it means to be a planet. Pluto didn't make the cut. It became a dwarf planet instead, one of many similar objects in the Kuiper Belt. The man who provided much of the evidence leading to Pluto's demotion, Mike Brown. He even wrote a book titled "How I Killed Pluto and Why It Had It Coming." The irony that Brown might now discover a true 9th planet hasn't been lost on anyone. So if the old Planet X was a myth based on bad data, why should we believe in this new Planet 9? Because the evidence is completely different. This isn't about measurement errors or wishful thinking. It's about patterns that emerge when you look at the most distant objects in our solar system, objects that exist in a realm we barely understand. The outer solar system is strange. Beyond Neptune, at distances greater than 250 astronomical units, that's 250 times farther from the Sun than Earth, you enter a region where sunlight is so faint it's almost meaningless. Out here, objects move in slow motion, taking millennia to complete their orbits. We've discovered dozens of these extreme trans-Neptunian objects, and they're revealing something unexpected. In 2014, astronomers Scott Shepard and Chadwick Trujillo noticed something odd. A handful of these distant objects had orbits that clustered together. They weren't randomly scattered across the sky like you'd expect. They were grouped, almost shepherded, as if something massive was organizing them. Shepard and Trujillo suggested an unseen planet might be responsible, something several times larger than Earth and more than 200 times our planet's distance from the Sun. Badigian and Brown heard about this clustering and decided to investigate. What they found went far beyond the initial observations. When they ran computer simulations of the outer solar system, trying to recreate the orbits of these distant objects, they kept hitting the same conclusion. Without a massive planet out there, the simulations couldn't reproduce what we actually observe. But add a planet with specific characteristics, about 10 Earth masses in a highly elongated orbit, and suddenly everything clicked into place. The simulations matched reality. The alignment of these objects isn't subtle. 6 of them point in the same direction when they make their closest approach to the Sun. They're tilted at about 30 degrees downward from the plane where the other planets orbit. This kind of alignment doesn't happen naturally in a chaotic system. Something organized it. Something massive enough to gravitationally dominate a region of space larger than any known planet. There's more. Badigian and Brown simulations predicted that a second group of objects should exist, forced into positions at right angles to Planet 9 and into orbits perpendicular to the solar system's plane. 5 known objects fit this prediction exactly. The math predicted they should be there before anyone found them. In April 2024, Badigian and Brown published new evidence. They focused on a different population of trans-Neptunian objects, ones with orbits that reach inside Neptune's orbit. These objects spread inward from Neptune in a pattern that matches Planet 9's predicted gravitational influence precisely. Without Planet 9 in the simulations, this pattern doesn't appear. With it, the match is almost perfect. The study was statistically significant at about a 5 sigma confidence level, which in scientific terms means the probability of this being a coincidence is vanishingly small. Mike Brown stated it plainly. I think it is very unlikely that Planet 9 does not exist. There are currently no other explanations for the effects that we see. If Planet 9 isn't real, astronomers would need 5 or 6 separate unknown explanations for all the oddities they're observing in the outer solar system. That's possible, but it violates a principle scientists hold dear. The simplest explanation that accounts for all the evidence is usually correct. But here's what makes this search so difficult. Planet 9, if it exists, is unimaginably far away. The most recent estimates place it around 290 astronomical units from the Sun on average. To put that in perspective, Neptune orbits at about 30 astronomical units. Pluto's average distance is around 40 astronomical units. Planet 9 is 7 to 10 times farther out than that. At such distances, sunlight is incredibly weak. The planet would reflect almost no visible light. It would be extraordinarily dim, with an apparent magnitude somewhere around 21 or 22. That's roughly 25,000 times fainter than the faintest stars you can see with your naked eye. Even with the world's most powerful telescopes, finding Planet 9 is like searching for a specific grain of sand on a beach at midnight. You know roughly which beach to search, but the grain could be anywhere along miles of coastline. Previous searches have eliminated about 78% of the possible sky positions. That sounds impressive until you realize 22% of an already enormous search area is still enormous. The planet moves slowly, incredibly slowly. At its estimated distance, it would take between 10,000 and 20,000 years to complete one orbit. In the time since humans built the pyramids, Planet 9 has moved only a fraction of its total path. This makes it harder to detect because astronomers typically find distant objects by watching them move against the background stars. If something barely moves over months or years of observation, it can easily be mistaken for a distant star or galaxy. There's another complication. The planet's orbit is highly elongated. Sometimes it might be relatively closer to the Sun, perhaps 200 to 300 astronomical units away. At other times, it could be 600 astronomical units out or even farther. According to Kepler's laws of planetary motion, objects move more slowly when they're farther from the Sun. Statistically, Planet 9 is more likely to be near the far end of its orbit right now, where it's moving slowest and is dimmest. That's the worst possible scenario for detection. Yet despite these challenges, astronomers are confident they'll find it soon. The reason for this confidence lies not in traditional telescopes, but in a revolutionary new observatory that's about to begin operations. The Vera C. Rubin Observatory in Chile represents a complete game-changer for astronomy. This facility, a joint project of the National Science Foundation and the Department of Energy, has been under construction for years. It's equipped with the largest digital camera ever built for astronomy, and it's designed to do something no other telescope can match. Starting in 2025, it will photograph nearly the entire southern sky every few nights, creating an ongoing movie of the cosmos. Mike Brown calls it the perfect tool for finding Planet 9. If you were to hand me a big wad of cash and say, go build a telescope to either find this Planet 9 or find the best evidence possible for Planet 9, I would probably go and build the Vera Rubin Observatory. The observatory will capture images of roughly 10 billion objects over the next decade. Computer systems will constantly compare new images to previous ones, flagging anything that changes or moves. If Planet 9 is in the southern sky, Rubin will almost certainly detect it. Scott Shepard estimates the observatory has a 70 to 80% chance of finding the planet if it's real. But what if it's not in the southern sky? What if it's in the northern hemisphere, outside Rubin's view? That's where other telescopes come in. The Subaru telescope in Hawaii, with its combination of large aperture and wide field of view, is conducting its own search. Two teams of astronomers, Badijan and Brown along with Trujillo and Shepard, are working together, expecting the combined search to take up to 5 years. 5 years might seem like a long time, but in astronomical terms, it's remarkably quick. We're talking about finding an object that's been hiding for 4.6 billion years, an object that's never been seen by human eyes, an object that challenges everything we thought we understood about how our solar system formed. Because that's the real question lurking behind all of this. If Planet 9 exists, how did it get there? A planet that massive, that far from the Sun, shouldn't exist according to standard models of planetary formation. The solar system's outer regions didn't have enough material to build something that large at such distances. So where did it come from? The answer might be even stranger than the planet itself. The leading theory suggests our solar system once had 5 giant planets, not 4. Jupiter, Saturn, Uranus, Neptune, and a fifth world roughly the size of Uranus or Neptune. During the chaotic early days of the solar system, these giants were packed much closer together than they are now. They orbited in a dense disk of planetesimals, the leftover building blocks from planetary formation. Then, over millions of years, gravitational interactions between the giant planets and these smaller objects caused the planets to migrate. Jupiter moved slightly inward. The others drifted outward. This migration wasn't smooth or gentle. It was violent, chaotic, a cosmic game of pinball played with planet-sized objects. At some point during this upheaval, the fifth giant planet got too close to Jupiter. Jupiter, the most massive planet in the solar system with more than twice the mass of all other planets combined, acted like a gravitational slingshot. It flung the fifth giant outward with tremendous force. Most computer simulations of this scenario show the ejected planet being thrown completely out of the solar system, lost forever to interstellar space. But in a small percentage of simulations, something different happens. The ejected planet doesn't quite reach escape velocity. Instead, it settles into a distant, highly elliptical orbit, exactly the kind of orbit predicted for Planet 9. This scenario is called the Nice model, named after the French city where it was developed. The Nice model has become widely accepted because it explains several puzzling features of the solar system. It accounts for the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by asteroids and comets. It explains why Neptune's orbit is slightly eccentric. It clarifies the structure of the Kuiper belt. And now, it might explain Planet 9. The ejection hypothesis solves a fundamental problem. You can't build a planet as massive as Planet 9 at such extreme distances from the Sun. There simply wasn't enough material out there. The solar nebula, the disk of gas and dust from which planets formed, was too thin and spread out at those distances. Planet formation requires material to collide and stick together, and that process becomes exponentially slower when particles are spread across vast expanses of space. But if Planet 9 formed closer to the Sun, in the region where Uranus and Neptune formed, and was then ejected outward, suddenly its existence makes perfect sense. The physical characteristics match this origin story remarkably well. Planet 9 is predicted to have a mass of about 5 Earth masses, similar to Uranus and Neptune when you account for their thick atmospheres. It would be gaseous, an ice giant with a rocky core surrounded by water, methane, and ammonia ices, all wrapped in a hydrogen and helium envelope. These are exactly the characteristics you'd expect from a planet that formed in the outer solar system 6 billion years ago. But there's another possibility, one that's even more extraordinary. What if Planet 9 didn't form in our solar system at all? The Sun wasn't born in isolation. It formed in a stellar nursery, a dense cluster containing thousands of young stars packed into a relatively small volume of space. In such environments, close encounters between stars are common. During the first few 100 million years of the solar system's existence, another star could have passed within a few hundred astronomical units of the Sun. If that star had its own planetary system, and if one of its planets happened to be in just the right position during the encounter, the Sun's gravity could have captured it. This capture scenario would make Planet 9 an exoplanet, a planet that formed around another star. If confirmed, it would be the first exoplanet discovered within our own solar system, a world that spent billions of years orbiting a different sun before becoming part of ours. The odds of such a capture are low, but they're not zero. Computer simulations show that in dense stellar nurseries, planetary capture events do occur, though rarely. The capture hypothesis has an appealing elegance. It would explain why Planet 9's orbit is so different from the other planets, tilted relative to the solar system's plane and highly elongated. A captured planet wouldn't follow the orderly, nearly circular orbits of planets that formed in place. Its orbit would bear the fingerprints of a violent gravitational encounter, exactly what we see predicted for Planet 9. But here's what makes this puzzle even more complex. There's a third option that astronomers are seriously considering. What if there isn't just one Planet 9, but multiple smaller planets? What if instead of a single 5 Earth mass world, there are 2 or 3 planets, each a few Earth masses, scattered across the outer solar system? This multi-planet scenario could produce similar gravitational effects on trans-Neptunian objects while being harder to detect because each individual planet would be smaller and dimmer. Some researchers have proposed an even more exotic alternative involving a disk of small icy bodies with a combined mass of 10 Earth masses, spread across the outer solar system. This disk, if it exists, could gravitationally shepherd trans-Neptunian objects in ways that mimic the effects of a single large planet. The challenge with this disk hypothesis is that such a structure should be detectable through its infrared emission, and so far, surveys haven't found it. Then there are the truly speculative ideas. Could Planet 9 be a primordial black hole, a microscopic black hole formed in the early universe? Such an object would have the right mass to produce the observed gravitational effects but would be nearly impossible to detect directly. Or could it be a concentration of dark matter, the mysterious substance that makes up most of the universe's mass but doesn't interact with light? These exotic explanations remain on the fringes of scientific consideration because they require invoking phenomena we've never directly observed in our solar system. Occam's razor suggests the simpler explanation, a planet, is more likely. But the fact that astronomers are even considering such alternatives demonstrates how profoundly puzzling this situation is. What makes the formation question so crucial is this: the answer would tell us whether our solar system is typical or unusual. If Planet 9 is an ejected fifth giant, it suggests that planetary systems commonly lose planets during their chaotic youth. Astronomers have found evidence of ejected planets around other stars, so this wouldn't be unprecedented. It would mean that for every planetary system we observe, there might be one or more invisible planets lurking in the darkness beyond what we can easily detect. If Planet 9 is a captured exoplanet, it would suggest that stellar nurseries are dynamic enough to exchange planets between forming systems. This would have profound implications for understanding planetary demographics in the galaxy. How many stars captured planets? How many lost them? The architecture of planetary systems might be far more fluid and dynamic than we've imagined. Recent refinements to the Planet 9 hypothesis have actually made the formation question more pressing. A 2025 study using an expanded sample of 51 extreme trans-Neptunian objects proposed that Planet 9's orbit might be smaller than previously thought, with a semi-major axis of around 290 astronomical units rather than 400 to 600. If true, this would place Planet 9 closer to the Sun, making it brighter and easier to find, but it also changes the dynamical requirements for how the planet reached that orbit. The nice model simulations that showed a fifth giant being ejected to Planet 9's orbit were based on the earlier, larger orbital estimates. With a smaller orbit, the ejection dynamics would need to be recalculated. Could Jupiter fling a planet to 290 astronomical units without ejecting it entirely from the solar system? The answer depends on precise details of the ejection event, the angle, the velocity, the gravitational assists from other planets. What we're witnessing is science in action, the process of refining hypotheses as new data emerges. Each new trans-Neptunian object discovered adds another constraint to the models. Each failed search narrows the possible locations. The picture is becoming clearer, but the fundamental mystery remains. Somewhere out there, moving slowly through the darkness, there might be a world that holds the key to understanding our solar system's violent past. And the clock is ticking. Within the next few years, the Vera Rubin Observatory will either find Planet 9 or rule out large portions of the remaining search space. We're approaching a definitive answer to one of astronomy's biggest questions. But before we get there, we need to understand what finding Planet 9 would actually mean for the rest of the solar system, because its gravitational influence extends far beyond just those handful of trans-Neptunian objects. Planet 9's gravitational reach doesn't stop at those extreme trans-Neptunian objects. It extends throughout the outer solar system in ways that are subtle but detectable. Jupiter family comets, those periodic visitors that swing through the inner solar system every few years, would show different orbital tilts if Planet 9 exists. Computer simulations predict their inclination distribution should be broader, more spread out, than what we'd see in a Planet 9-free solar system. And when astronomers look at the actual data, that's exactly what they find. The distribution matches the prediction. Then there's the Oort cloud, that vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. Planet 9 would have affected how many objects got captured into the Oort cloud during the solar system's formation. Simulations show that with Planet 9 in its predicted orbit billions of years ago, fewer objects would have been flung into the Oort cloud. The gravitational stirring from a massive planet in the outer reaches would have ejected more objects entirely from the solar system rather than parking them in distant orbits. This prediction is harder to test directly since we can't count Oort cloud objects with any precision, but it represents another testable consequence of the hypothesis. What about the giant planets themselves? Would Planet 9 have left fingerprints on Jupiter, Saturn, Uranus, and Neptune? The answer depends on when Planet 9 reached its current orbit. If it was ejected early in the solar system's history, during the period of planetary migration described by the NICE model, then its ejection would have been part of the same chaotic reshuffling that moved all the giant planets. In that case, Planet 9's influence is already baked into the current orbital configuration we observe. The planets are where they are partly because of the gravitational chaos that sent Planet 9 outward. But there's a more direct effect. Planet 9's orbit is tilted about 6 degrees relative to the plane where the 8 known planets orbit. That tilt would exert a slow, subtle torque on the entire solar system over billions of years. Think of it like a spinning top that's slightly off balance. Over time, that imbalance affects the whole system's orientation in space. Calculations suggest that Planet 9 could explain a long-standing puzzle: why the Sun's equator is tilted about 6 degrees relative to the planetary orbital plane. The gravitational influence of a distant, tilted Planet 9, acting over 4.5 billion years, could have gradually torqued the entire inner solar system, including the Sun's rotation axis, into its current configuration. This prediction caught many astronomers by surprise when it was first published. It's one thing to affect distant icy bodies. It's another to tilt the Sun itself. But the math checks out. A 5 Earth-mass planet at 300 to 400 astronomical units, tilted at the right angle, applying gentle but persistent gravitational torque over geological timescales, could absolutely accomplish this feat. And suddenly Planet 9 isn't just explaining weird orbits at the edge of the solar system. It's explaining a fundamental property of our planetary system that's been visible since humans first pointed telescopes at the Sun. Yet another population shows Planet 9's fingerprints: high-inclination trans-Neptunian objects. These are objects whose orbits are tilted steeply relative to the plane where planets orbit, sometimes by 90 degrees or more. They're rare, which makes sense. Most of the solar system's material started in a flat disk and should stay relatively flat. But we found several objects with these extreme tilts, and they need an explanation. Planet 9's gravitational influence could pump up the inclinations of certain objects over millions of years through a process called causative oscillations. This mechanism causes orbits to trade eccentricity for inclination in a periodic cycle. An object might start with a moderately elliptical orbit in the plane, then gradually become more circular but more tilted, then swing back. With Planet 9's gravity driving these oscillations, some objects could get kicked into very high inclinations and stay there. 5 known objects fit this prediction with remarkable precision. They're positioned at roughly 90-degree angles to Planet 9's predicted location, and their orbits are perpendicular to the solar system's plane. When Badigian and Brown first ran their simulations, these objects appeared naturally in the results. The model predicted they should exist before anyone had specifically looked for them. Finding them in the real data wasn't just confirmation. It was the kind of successful prediction that makes scientists take notice. The gravitational mechanisms at work here operate on timescales that dwarf human civilization. An object in the outer solar system might take hundreds of thousands of years to complete one oscillation cycle. Planet 9 itself takes 10,000 to 20,000 years just to complete a single orbit. The gravitational dance between Planet 9 and these distant objects unfolds across geological epochs, invisible to any observer watching for less than millennia. We're catching a single frame of a movie that's been playing for billions of years. Does Planet 9 affect the known planets directly? Neptune's orbit should show tiny perturbations if Planet 9 exists, wobbles measurable in the planet's position over time. Astronomers have looked for these signatures. So far, the results are inconclusive, which actually makes sense given Planet 9's distance. At 300 to 600 astronomical units, its gravitational pull on Neptune is extraordinarily weak. Neptune is 30 astronomical units from the Sun. Planet 9 is 10 to 20 times farther out. Gravitational force drops off with the square of distance, so Planet 9's pull on Neptune is hundreds of times weaker than Neptune's pull on itself. Detecting such subtle effects requires decades of precise observations and sophisticated data analysis. We might not see clear perturbations in Neptune's orbit for years yet. Uranus presents a different puzzle. This ice giant is tilted on its side, rotating with its axis nearly in the plane of its orbit rather than roughly perpendicular like every other planet. Various theories have tried to explain this bizarre orientation: a giant collision during formation, gravitational interactions during planetary migration, or cumulative effects from multiple smaller impacts. Could Planet 9 be responsible? Probably not directly. The tilt likely originated during the solar system's chaotic youth, and Planet 9's current location doesn't provide the right geometry to have caused it. But if Planet 9 was ejected from the inner solar system, it might have been one of several factors contributing to the orbital chaos that tilted Uranus. Not the sole cause, but part of a complex sequence of gravitational interactions. The asteroid belt between Mars and Jupiter seems far removed from Planet 9's domain, but even here there might be subtle connections. Some asteroids have been found on highly elliptical orbits that take them far beyond Neptune. These aren't main belt asteroids in the traditional sense, they're trans-Neptunian objects that happen to pass through the inner solar system. Planet 9 could influence the population of these objects, determining which ones get perturbed onto planet-crossing orbits and which stay safely beyond Neptune. This matters for understanding impact rates on the inner planets over geological time. If Planet 9 exists, it's been shaping the flux of impactors throughout solar system history. Centaurs, those hybrid objects orbiting between Jupiter and Neptune, neither quite asteroids nor comets, show dynamical properties that could reflect Planet 9's influence. These objects are thought to originate from the trans-Neptunian region and get gravitationally scattered inward. The rate at which objects get scattered, and the specific orbits they end up on, depend on the outer solar system's gravitational environment. Add Planet 9 to the mix, and you change the probabilities. More objects might get kicked onto certain types of orbits, fewer onto others. Detailed population studies of centaurs could, in principle, reveal Planet 9's gravitational fingerprint even in the middle reaches of the solar system. What's remarkable about all these effects is their consistency. Planet 9 isn't just explaining one weird thing. It's explaining multiple independent phenomena across different populations of objects in different regions of the solar system. The clustering of extreme trans-Neptunian objects. The perpendicular objects. The Sun's axial tilt. The distribution of orbital inclinations. Each one could potentially have a different explanation. But they all point to the same solution: a massive planet on a distant, tilted orbit. That's what makes the hypothesis so compelling. Still, correlation isn't causation. Maybe these effects have other explanations we haven't considered. Maybe observational biases we haven't properly accounted for are creating patterns where none exist. Maybe the solar system is just weird in multiple unrelated ways. These possibilities keep skeptics skeptical, and rightfully so. Extraordinary claims require extraordinary evidence. But with each new study, with each additional prediction that proves correct, the case grows stronger. The question isn't really whether Planet 9 affects the solar system. If it exists at all, it must. Gravity doesn't have an off switch. The question is whether we can measure those effects precisely enough to confirm the planet's existence indirectly. And that's where the cutting edge of observational astronomy comes in: techniques for detecting planets not by seeing them directly, but by mapping their gravitational influence on everything around them. The art of finding invisible planets has evolved dramatically since Neptune's mathematical discovery in 1846. Back then, astronomers noticed Uranus wasn't following its predicted path. Something was tugging on it. They worked backward from those perturbations, calculated where the disturbing mass had to be, pointed their telescopes at that spot, and there it was. A new world revealed through pure mathematics. Planet 9 requires a more sophisticated approach. We're not tracking one object getting pulled by an unknown planet. We're analyzing dozens of distant bodies, each with its own orbital peculiarities, trying to extract a common signal from the noise. It's less like following footprints to find what made them and more like being a detective at a crime scene with multiple witnesses who each saw something slightly different. The statistical methods matter enormously here. Brown and Badijan didn't just notice the clustering and declare victory. They quantified it. They developed techniques to measure observational bias in each individual object's discovery, because not all parts of the sky get observed equally. Some regions get scanned more frequently. Some get deeper exposures. Telescopes point where astronomers tell them to point, and astronomers have their own interests and observing programs. This creates selection effects. If you only search for distant objects in certain parts of the sky, you'll only find distant objects in those parts of the sky. Obvious, right? But correcting for this bias mathematically isn't straightforward. You need to know not just where you looked, but how thoroughly you looked there, and with what sensitivity. Brown and Badijan accounted for these factors, and even after corrections, the clustering remained statistically significant. About 1 chance in 500 that it's random. That number has gotten better with time. As more objects get discovered and the sample size grows, the statistical confidence strengthens. By 2021, Brown and Badijan reanalyzed with improved bias corrections and found a clustering significant at 99.6% confidence. That's getting into the realm where you start taking things very seriously. But statistics alone don't make a planet. The real power comes from prediction. If your hypothesis is correct, it should tell you what else you'll find. Planet 9 makes specific predictions about populations of objects that should exist but hadn't been looked for yet. And that's where things get interesting. One prediction involves objects perpendicular to the solar system's plane. Not just tilted. Perpendicular. Orbiting the sun almost vertically while everything else goes around horizontally. These objects shouldn't exist in a normal solar system. There's no mechanism to put them there. Yet Planet 9's gravitational influence, according to the models, should create exactly this population. 5 objects matching this prediction have been found. 5 might not sound like many, but remember, these are extremely rare configurations. Finding even one was surprising. Finding 5 that matched the theoretical prediction in detail. That's not coincidence. Another test came in 2024. Brown and Badijan published analysis of a different population, low-inclination trans-Neptunian objects with orbits that reach inside Neptune's orbit. These objects have nothing to do with the original clustering that suggested Planet 9. They're on completely different types of orbits. Yet when you run simulations with Planet 9 included, these objects' orbital distribution matches what we actually observe. Remove Planet 9 from the simulations, and the match disappears. The statistical rejection of the Planet 9 free scenario sits at 5 sigma. That's the same confidence level physicists demanded before announcing the Higgs boson discovery. Does this prove Planet 9 exists? No. Science doesn't deal in proof, only in evidence and confidence levels. But the confidence is getting high enough that dismissing the hypothesis requires explaining away multiple independent lines of evidence. The skeptics haven't been silent. Samantha Lawler and others argue that observational biases are stronger than Brown and Badijan acknowledge. In 2020, 2 large surveys, the Outer Solar System Origins Survey and the Dark Energy Survey, found hundreds of trans-Neptunian objects and saw no significant clustering. OSOS documented over 800 objects. DES found 316 new ones. Both surveys carefully accounted for observational bias and concluded the orbits could be explained by known physical processes without invoking a 9th planet. This disagreement cuts to the heart of how science works. Same solar system, same objects, different conclusions. Why? It comes down to which objects you include in your analysis and how you correct for bias. Brown and Badijan focus on the most extreme objects, the ones farthest out with the most elongated orbits. These are the objects most likely to be influenced by Planet 9 because they venture into its gravitational domain. OSOS and DES looked at a broader population including objects that wouldn't be strongly affected by Planet 9 even if it exists. The debate also involves sample size versus sample quality. OSOS has more objects, but are they the right objects for testing this particular hypothesis? 1,000 data points don't help if they're measuring the wrong thing. Meanwhile, Brown and Badijan's smaller sample focuses on exactly the objects that should show Planet 9's influence most clearly. It's a classic tension in observational astronomy. More data isn't always better data if it dilutes your signal. Alternative explanations have emerged. Maybe instead of one big planet, there's a disk of smaller icy bodies with combined mass equivalent to Planet 9. Spread that mass out, and you might get similar gravitational effects. Or perhaps these orbits were set during the solar system's birth, when the Sun formed in a stellar cluster and neighboring stars perturbed the outer reaches. Some researchers even propose multiple Earth-mass rogue planets rather than one super-Earth. Each alternative has problems. The disk hypothesis requires an improbably specific mass distribution that stays stable over billions of years. The stellar cluster scenario works for setting initial conditions but doesn't explain why the clustering persists today, billions of years after the Sun left its birth cluster. Multiple rogues would need to have been captured with just the right orbits and masses to produce the observed effects without disrupting everything else. What makes Planet 9 compelling isn't that it's the only possible explanation. It's that it's the simplest explanation that accounts for multiple independent observations. One object, one orbit, multiple predictions that keep being confirmed. That's powerful. The thermal emission angle offers another avenue. Planet 9, if it exists, is still cooling from its formation. At 5 Earth masses, it retains significant internal heat. Even at 47 Kelvin, frigidly cold by any human standard, it radiates in the infrared. This radiation should be detectable with the right instruments, particularly submillimeter telescopes that specialize in this wavelength range. The challenge is sensitivity. Planet 9's thermal signature is faint, and the infrared sky is crowded. Lots of things emit at these wavelengths. You need long integration times, careful subtraction of foreground and background sources, and the patience to search a large area of sky. Several groups are working on this, using facilities like the Atacama Large Millimeter Array. No detections yet, but the search continues. Direct optical detection faces a different set of challenges. At aphelion, Planet 9 could be 800 astronomical units away or more, moving through the most distant parts of its orbit. At that distance, reflected sunlight is vanishingly faint. You need large telescopes with wide fields of view, and you need to image the same regions repeatedly to detect motion. The Subaru telescope in Hawaii has been conducting systematic searches. So have other facilities. They've covered about 78% of the possible sky positions where Planet 9 might be. That sounds good until you realize the remaining 22% is still a huge search space. Statistically, Planet 9 is more likely to be near aphelion than perihelion, simply because it moves slower out there and spends more time in that part of its orbit. That's where Kepler's second law bites you. Objects sweep out equal areas in equal times, which means they crawl along when far from the Sun. If Planet 9 is currently near aphelion, it's at its faintest and hardest to detect. Bad luck for us, but that's the reality. The search isn't hopeless. It's methodical, systematic, and ongoing. Every survey that comes up empty eliminates possibilities and narrows the remaining search space. Brown and Badijan have refined their predictions multiple times based on new data, updating the most likely orbital parameters. Their current best estimate puts the semi-major axis around 380 to 460 astronomical units, though a 2025 study by Siraj, Chaiba, and Tremaine suggests it might be closer, around 290 astronomical units. Closer means brighter. Brighter means easier to find. And then there's the Vera Rubin Observatory, scheduled to begin operations in 2025, which changes everything. The Vera Rubin Observatory is unlike anything that's come before. Sitting on Cerro Pachón in Chile at 2,700 meters elevation, it houses an 8.4-meter primary mirror and the largest digital camera ever built for astronomy. 3 gigapixels. That's not a typo. The camera weighs 3 tons and captures an area of sky equivalent to 40 full moons in a single image. Why does this matter for Planet 9? 2 reasons. Coverage and cadence. Rubin will survey the entire visible southern sky every few nights. Not targeted observations of specific regions. The whole sky, repeatedly, for 10 years. Every object in that survey gets tracked automatically. The system compares new images to previous ones, flagging anything that moves, changes brightness, or appears where nothing was before. Planet 9, if it exists, moves. Slowly. Over months and years, it would shift position relative to background stars. That's its signature. Rubin's repeated imaging strategy is custom-built to catch exactly that kind of motion. You don't need to know where to look ahead of time. You just watch everything and let the data tell you what moved. Mike Brown's enthusiasm about Rubin isn't exaggeration. He spent years searching with Subaru, which is an excellent telescope but requires choosing where to point. Rubin doesn't. It watches. constantly, systematically. If Planet 9 is anywhere in the southern sky at a detectable brightness, Rubin will find it. Not might find it. Will find it. Scott Shepard estimates the probability at 70 to 80%, assuming Planet 9 exists and has the predicted properties. Those are good odds in astronomy. Mario Jurek points out that Rubin will increase the known population of trans-Neptunian objects from around 4,000 to potentially 40,000. That's not just more objects. That's better statistics, tighter constraints, and a far clearer picture of what's actually happening in the outer solar system. The timeline is aggressive. Megan Schwamm says the first year or two of Rubin operations should answer the question. Either Planet 9 shows up in the data, or the lack of detection tells us something definitive about where it isn't and what it can't be. This is the moment. After nearly a decade of predictions, simulations, and targeted searches, we're about to conduct the most comprehensive survey of the outer solar system ever attempted. If Planet 9 is real, 2025 through 2027 could be the years we finally see it. But what if Rubin doesn't find it? That's the scenario nobody talks about much, but it's worth considering. Absence of evidence isn't evidence of absence, except when you've looked everywhere the thing could possibly be. Rubin gets us close to that threshold. If Rubin completes its survey without detecting Planet 9, the hypothesis doesn't collapse entirely, but it gets significantly harder to maintain. Maybe Planet 9 is fainter than expected. Maybe it's in a part of the sky Rubin can't see as well. Maybe it's currently too close to the galactic plane where background star density makes detection difficult. There are outs. But they start sounding like special pleading after a while. The other possibility is that Planet 9 exists but isn't where the models predict. Orbital parameters have shifted multiple times as new data comes in. The 2025 Siraj study suggested a closer, less eccentric orbit than previous estimates. If that's correct, Planet 9 might be brighter and easier to find. But if the models are still off, we might be looking in the wrong regions entirely. Then there's the alternative explanations. What if the orbital clustering of trans-Neptunian objects isn't caused by a single planet but by a disk of smaller objects, each too faint to detect individually but collectively massive enough to produce gravitational effects? That hypothesis has been proposed. It works mathematically for some observations but struggles to explain others, particularly the perpendicular objects. Or what if the clustering is a transient phenomenon caused by something that's no longer there? A passing star could have perturbed orbits temporarily. The Sun's birth cluster could have left a dynamical imprint that's still visible today. Multiple captured rogue planets might produce similar effects without requiring a single massive world. These scenarios feel more contrived than a single planet, but they're not impossible. Brown has argued that rejecting Planet 9 means accepting 5 or 6 separate unexplained phenomena, each requiring its own cause. That's inelegant. Science favors parsimony. One explanation that accounts for multiple observations beats several disconnected explanations. But parsimony isn't proof. Sometimes reality is messy and complicated. The discovery of Ammonite, a new sednoid announced by the Subaru team, adds another wrinkle. Ammonite's orbit doesn't cluster with the other sednoids the way Planet 9's gravitational influence would predict. It's off on its own. That might mean Planet 9's orbit needs further adjustment to account for Ammonite. Or it might mean something else entirely is going on. Every new discovery refines the picture, but it also introduces new constraints that any hypothesis has to satisfy. That's how science works. You don't get to cherry-pick the observations that support your model and ignore the rest. You have to explain all of it. Brown and Badigian have been transparent about this process. They've updated their predictions multiple times based on new data. They've addressed criticisms. They've acknowledged uncertainties. That's not weakness. That's how you build a robust scientific case. You test it against everything, adjust when necessary, and see if it still holds up. The April 2024 paper on low-inclination trans-Neptunian objects is a good example. These are objects that cross Neptune's orbit, a completely different population from the extreme distant objects that sparked the original hypothesis. Yet when you model their distribution, Planet 9's gravitational influence predicts their observed spread with remarkable accuracy. No Planet 9. The distribution doesn't match. With Planet 9, it does. That's independent confirmation using a different dataset. Statistical confidence levels matter here. A 5 sigma result means the probability of the observation occurring by chance is less than 1 in 3. 5 million. That's the standard for discovery in particle physics. It's extremely stringent. The 2024 study rejected the no Planet 9 scenario at approximately 5 sigma confidence. That's not suggestive. That's strong. Brown's statement that he thinks it's very unlikely Planet 9 doesn't exist reflects this accumulating evidence. It's not arrogance. It's Bayesian updating. Start with a hypothesis. Test it against observations. Adjust your confidence based on how well it performs. After 8 years of testing, the hypothesis keeps working. That shifts the probability upward. Could everyone be wrong? Of course. Science has a long history of confident predictions that turned out to be false. Vulcan, the hypothetical planet inside Mercury's orbit, was predicted to explain perturbations that Einstein's general relativity later explained without needing an extra planet. The luminiferous ether seemed necessary until it wasn't. Confidence doesn't equal certainty. But here's the key difference. Vulcan was never observed. Planet 9 hasn't been observed either, but the effects attributed to it keep showing up in independent datasets. The orbital clustering persists after correcting for observational bias. The perpendicular objects exist. The low-inclination objects match predictions. The Jupiter family comet distribution changes in the expected way. The predicted reduction in Oort cloud capture efficiency aligns with simulations. That's a lot of things to get right by accident. It's not impossible, but it's increasingly unlikely. Each successful prediction raises the prior probability that the underlying model is correct. So where does that leave us as Rubin prepares to begin operations? We're at a decision point. Within 2 years, maybe 3, we'll have data comprehensive enough to either confirm Planet 9's existence or rule it out across most of its possible parameter space. This isn't the kind of question that lingers unresolved for decades. The technology exists. The survey is happening. The answer is coming. If Rubin finds Planet 9, it will be one of the most significant planetary discoveries in history. Not because it's a planet, though that's cool. Because of what it tells us about solar system formation, migration dynamics, and the possibility that our planetary census was incomplete for the entire history of astronomy. If Rubin doesn't find it, that's also significant. It means either the hypothesis was wrong, or Planet 9 is so far, so faint, or so weirdly positioned that even our best efforts can't detect it. That possibility can't be dismissed. The outer solar system is vast. Assumptions about brightness and location might be off. But at some point, a hypothesis that can't be tested stops being useful. The broader implications extend beyond our solar system. Discovering Planet 9 would make our system more similar to others. Most exoplanetary systems contain super-Earths, planets with masses between Earth and Neptune. We don't have any. Planet 9 would fill that gap, suggesting that our system formed similarly to others, but with a quirk: one of the planets got kicked outward instead of staying close. That has implications for planet formation theory. How common is ejection? What determines whether a forming planetary system ends up with all its planets in tight orbits versus having one or more in distant eccentric orbits? Are we typical or unusual? Planet 9 helps answer those questions. It also affects how we think about planetary migration. The NICE model explains a lot about how the giant planets reach their current orbits, but it's not complete. If Planet 9 is an ejected ice giant, that's a direct observation of a process we've only simulated. We could study its composition, atmosphere, and thermal properties. We could learn what happens to a planet that gets thrown into the outer darkness and survives there for billions of years. All of that depends on detection. And detection depends on Rubin. The next few years will be decisive. The search itself has an interesting dynamic. Brown and his team aren't the only ones looking. Multiple groups worldwide are scanning different portions of the sky, using different methods, hoping to be the first to spot it. There's a competitive element, though it's mostly friendly. Everyone wants the discovery, but everyone also wants the answer, regardless of who provides it. What happens if Rubin spots something in the right region with the right motion? Confirmation would take time. A single detection isn't enough. You need multiple observations over weeks or months to establish an orbit. Then you need spectroscopy to determine composition. Is it icy? Gaseous? Does it have an atmosphere? What's its temperature? All of that requires follow-up with other instruments. And here's something people don't always consider. If Planet 9 exists and Rubin finds it, that's not the end of the story. It's the beginning. We'd have a new planet to study. A super-Earth in our own solar system, close enough to observe in detail but far enough to be genuinely alien. What can we learn from it? For one thing, we could study its atmosphere if it has one. Most super-Earths we've detected around other stars are too far away for detailed atmospheric analysis. Planet 9 would be right here, relatively speaking. We could point infrared telescopes at it, measure its thermal emission, detect molecular signatures, and figure out what it's made of. We could also study its interaction with the surrounding environment. Does it have moons? Rings? A magnetic field? How does it affect the local dust distribution? Does it capture comets or asteroids into temporary orbits? All of those questions become answerable once we know where it is. The formation question would become more tractable too. If Planet 9 is an ejected ice giant, we could compare its properties to Uranus and Neptune. Are they similar? Different? That tells us about the conditions under which they formed and what happened during the ejection process. Did Planet 9 lose its outer layers during the encounter with Jupiter? Did it retain them? The answers matter for understanding how planetary systems evolve. There's also the possibility of detecting other distant planets. If one exists, maybe others do. The outer solar system is huge. We've barely scratched the surface. Rubin will find thousands of new trans-Neptunian objects, and some of them might have orbits that point to additional unseen bodies. Planet 9 might not be alone. But let's consider the other scenario. Rubin surveys the entire accessible region and finds nothing. What then? First, it doesn't immediately kill the hypothesis. The predicted orbit has uncertainty. If Planet 9 is near its aphelion and farther than expected, Rubin might miss it. Its brightness could be lower than predicted. There are scenarios where Planet 9 exists but remains undetected even after Rubin's survey. However, those scenarios become increasingly constrained. If Rubin doesn't find it, the parameter space shrinks dramatically. The planet would have to be fainter, farther, or in a very specific location that Rubin didn't cover. At that point, the hypothesis starts looking less likely. It wouldn't vanish entirely. Science doesn't work that way. But the community's confidence would shift. If the best survey we've ever conducted finds nothing, most astronomers would conclude that Planet 9 probably isn't there, at least not in the form currently predicted. That would leave the clustering problem unresolved. The orbital alignment of trans-Neptunian objects would still need an explanation. Maybe it's observational bias after all, despite the corrections. Maybe it's a temporary configuration that will disperse over time. Maybe there's a different mechanism at work that we haven't thought of yet. Or maybe there's something else out there, not a single planet but a different kind of object. A primordial black hole, for instance. That's been proposed as an alternative. A black hole with a few Earth masses could produce similar gravitational effects without being visible. It wouldn't emit light, wouldn't reflect sunlight, and would be nearly impossible to detect directly. The black hole hypothesis is speculative, but it's not absurd. Primordial black holes, if they exist, would have formed in the early universe from density fluctuations. Some could have been captured by the solar system. The gravitational effects would be identical to a planet of the same mass. The only difference is detectability. How would you find a black hole in the outer solar system? Gravitational lensing, maybe. If it passed in front of a distant star, the star's light would bend around it, creating a brief brightening. Rubin could detect that. It's a long shot, but it's possible. Another alternative is a disk of smaller objects, collectively massive enough to produce the observed effects. Instead of one planet, imagine thousands of smaller bodies distributed across a wide region. Their combined gravity could shepherd trans-Neptunian objects into aligned orbits. The disk hypothesis has problems though. To match the observed clustering, the disk would need a very specific mass distribution and configuration. It's not impossible, but it requires fine-tuning. A single planet is simpler. Occam's razor favors the simpler explanation, but simplicity doesn't guarantee correctness. So where does the evidence actually point right now, before Rubin starts observing? The statistical case for Planet 9 has strengthened. The 2024 study showing alignment of low-inclination objects was a big deal. That's a new population, independent of the original clustering, behaving exactly as predicted. The odds of that happening by chance are very low. But statistics aren't proof. Astronomy has seen confident predictions proven wrong before. The key is falsifiability. Planet 9 is falsifiable. If Rubin surveys the predicted region and finds nothing, the hypothesis is either wrong or needs major revision. That's good science. It's worth stepping back and asking why this matters beyond pure curiosity. Why should anyone care if there's a ninth planet? One reason is completeness. If we don't know our own solar system, how can we claim to understand others? Planet 9, if real, has been there the entire time humans have looked at the sky. Missing something that large in our own neighborhood would be humbling. Another reason is the connection to exoplanetary science. Super-Earths are everywhere. We've found thousands around other stars, but we don't have one here to study up close. Planet 9 would be the only super-Earth we can observe in detail, the only one we can send probes to eventually. That makes it scientifically valuable beyond its role in solar system dynamics. There's also the historical angle. Discovering a new planet is rare. It doesn't happen often. Neptune in 1846. Pluto in 1930, though that got reclassified. If Planet 9 is real, this generation gets to witness something that happens maybe once per century. That's not nothing. And then there's the sheer weirdness of it. A planet 10 times Earth's mass, orbiting hundreds of times farther from the Sun than we do, taking 20,000 years to complete one orbit. It's so far out that the Sun looks like just another bright star. Temperatures are near absolute zero. If it has an atmosphere, it's probably frozen solid. It's a world more alien than anything we've explored, and it's technically in our solar system. What would it be like to visit Planet 9? Impossible with current technology, obviously. The distance is staggering. Voyager 1, the fastest probe we've ever launched, has been traveling for over 40 years and still hasn't reached the predicted inner edge of Planet 9's orbit. Getting there would take centuries with existing propulsion systems. But imagine if we could. What would you see? The Sun would be a bright point of light, no disk visible, providing almost no heat. The sky would be black, filled with stars that don't twinkle because there's no atmosphere to distort them. The planet itself, if gaseous, might have faint cloud bands, though they'd be moving incredibly slowly in the cold. Moons, if they exist, would be frozen solid, covered in ancient impact craters. It would be the most isolated place a human could stand and still be within the Sun's gravitational influence. The nearest planet, Neptune, would be billions of kilometers away. Earth would be invisible without a telescope. You'd be at the edge of the solar system, looking outward toward interstellar space, inward toward the distant Sun, and feeling utterly, completely alone. That's Planet 9. If it exists. And within 2 years, we'll have a much better idea whether it does. Rubin starts observations soon. The data will accumulate. The algorithms will scan for slow-moving objects. And somewhere in those billions of data points, there might be a faint dot that moves just slightly between images. Or there might not. Either way, we're about to find out. The search for Planet 9 is entering its final phase. The question that's lingered for nearly a decade will finally get an answer. Whatever that answer is, it'll reshape how we understand the solar system. That's worth paying attention to. Looking at the timeline, we're living through something remarkable. The Vera Rubin Observatory represents the culmination of decades of technological advancement in astronomy. Its 2-gigapixel camera, its systematic survey strategy, its ability to track billions of objects simultaneously, all of it converges on this moment. We built the perfect machine for finding Planet 9 without necessarily intending to. The telescope doesn't care about the hypothesis. It's going to scan the southern sky regardless, cataloging everything that moves, everything that changes, everything that exists in its field of view. Planet 9 is just one target among billions. But if it's there, Rubin will see it. The odds are too good. The coverage too complete. The sensitivity high enough. What happens next depends entirely on what the data shows. If Planet 9 appears in the images, moving slowly across the background stars over weeks and months, the discovery will unfold gradually. Not a single eureka moment, but a pattern emerging from noise. Statistical confidence building with each new observation. Orbital parameters refined as more data points accumulate. Eventually, certainty. The confirmation process would take time. You don't announce a planet based on a handful of detections. You need enough measurements to calculate an orbit accurately. You need spectroscopy to determine composition. You need infrared observations to measure temperature and size. The full characterization might take years. But the initial detection, the moment when someone realizes there's a new object in the right region with the right motion, that could happen within months of Rubin's first light. And if it doesn't show up? If 2 years pass, then 3, and the predicted regions yield nothing? The hypothesis doesn't instantly collapse, but it enters a different phase. The parameter space contracts. The alternative explanations become more attractive. At some point, you stop saying, "We haven't found it yet," and start saying, "It's probably not there." That outcome would be significant too. Not as exciting as discovering a new planet, but scientifically valuable nonetheless. We'd know the clustering of trans-Neptunian objects needs a different explanation. Maybe it's a selection effect we haven't fully accounted for. Maybe it's a transient configuration that won't persist. Maybe there's something else entirely driving those orbits, something we haven't considered. Science advances through ruling things out as much as confirming them. But the smart money is on detection. Brown and Badijan aren't betting their reputations on a whim. They've spent 8 years refining this hypothesis, testing it against new data, addressing criticisms, making predictions that keep being confirmed. The 2024 results on low-inclination objects were particularly compelling. Different population, same result. That pattern repeating across independent datasets is hard to dismiss. The formation question remains fascinating regardless of when detection happens. If Planet 9 is an ejected ice giant, it validates predictions from the NICE model that have been purely theoretical until now. We'd have direct evidence that planetary systems can eject giant planets without losing them entirely. That has implications for every exoplanetary system we observe. How many systems have hidden planets in distant orbits? How common is this configuration? If Planet 9 is a captured exoplanet, the implications are even stranger. It would mean our sun stole a world from another star during the solar system's youth. That's not impossible. Stellar nurseries are chaotic places where close encounters happen. But confirming it would be extraordinary. The first exoplanet discovered in our own solar system, a cosmic immigrant that's been here for 4.5 billion years. The public interest in Planet 9 reflects something deeper than just curiosity about astronomy. There's something compelling about the idea that we still don't fully know our own neighborhood. Despite centuries of observation, despite sending probes to the outer planets, despite thinking we'd mapped everything significant, there might still be a world we missed. A giant world, not some tiny asteroid, but a super-Earth mass planet that's been there all along. It's humbling in the right way. It reminds us that the universe doesn't reveal its secrets easily. Even in our own backyard, even with modern technology, there are still mysteries waiting to be solved. Planet 9, if real, represents the last great planetary discovery possible in the solar system. After this, we'll have found everything larger than Pluto. The inventory will be complete. The search itself demonstrates how modern astronomy works. No lone genius staring through a telescope. teams of researchers analyzing data from multiple instruments, running simulations on supercomputers, developing statistical methods to extract signals from noise, publishing results for peer review, responding to criticism, refining predictions. It's collaborative, iterative, and methodical. Not as romantic as the old stories of discovery, but more reliable. Brown's comment about Rubin being the perfect telescope for finding Planet 9 wasn't hyperbole. The match between the hypothesis's requirements and the observatory's capabilities is almost perfect. Wide field for covering large search areas. Deep sensitivity for detecting faint objects. Repeated observations for tracking motion. Automated data processing for handling billions of measurements. Everything needed to find a slow-moving distant planet, built into one facility. The timing feels right too. The hypothesis emerged in 2016. The predictions have been tested and refined over nearly a decade. The search space has been narrowed through systematic surveys. And now, just as we're ready for a definitive answer, the ideal instrument comes online. It's not coincidence. It's how science progresses. You develop a hypothesis, you test it as best you can with existing tools, and eventually technology catches up to enable the critical test. Rubin's broader impact on astronomy will extend far beyond Planet 9. The 10-year survey will revolutionize our understanding of the outer solar system, discovering tens of thousands of new trans-Neptunian objects, tracking comets, detecting asteroids, mapping the structure of the Kuiper Belt. Planet 9 is just one target in a much larger program. But it's the target everyone will be watching for. Imagine the moment of discovery. Someone running detection algorithms on Rubin data, seeing an object appear in the right region with the right motion. The double-checking. The orbital calculation. The realization that this might actually be it. The careful announcement. The flood of follow-up observations from telescopes worldwide. The gradual confirmation as the data accumulates. The moment when doubt shifts to certainty. Or imagine the alternative. Years passing. The survey completing. The predicted regions thoroughly searched. Nothing found. The slow acceptance that Planet 9 probably isn't there, at least not where expected. The return to other explanations for the orbital clustering. The questions about what we missed or misunderstood. Both scenarios advance our knowledge. One gives us a new planet to study. The other forces us to rethink our interpretation of outer solar system dynamics. Either way, we learn something fundamental about our cosmic home. The next 2 years will answer a question that's persisted since 2016. Is there a ninth planet? The mathematics say yes. The statistics say yes. The predictions keep being confirmed. But science demands direct observation. We need to see it. And we're finally at the point where that's possible. Planet 9 represents the kind of mystery that makes astronomy compelling. Not abstract or impossibly distant. Right here in our solar system. Big enough to matter. Strange enough to surprise us. And just barely beyond our current ability to detect, though that's about to change. The giant lurking in the darkness beyond Neptune might soon step into the light. Or it might remain a mathematical phantom, a compelling hypothesis that couldn't be confirmed. Within 2 years, we'll know. Rubin will scan the sky, the algorithms will run, and the data will tell us what's really out there. The answer is coming. 124 light years from Earth, a world exists that shouldn't be possible. Scientists detected something in its atmosphere that, on our planet, only comes from life. Not ancient fossils. Not chemical traces buried in rock. An active signal, present right now, floating in alien skies above an ocean that might stretch deeper than anything in our solar system. K2-18b orbits a dim red star in the constellation Leo, receiving about the same amount of light Earth gets from our Sun. But that's where the similarities end. This planet is more than 8 times Earth's mass and nearly 3 times wider. Its density falls somewhere between our rocky world and the ice giants lurking in the outer solar system. The James Webb Space Telescope aimed its instruments at this distant sphere and found water vapor, methane, carbon dioxide. Then it detected something else. Dimethyl sulfide. A molecule that, as far as we know, only biological processes produce. The scientific community is divided. Some researchers call it the most promising biosignature ever detected beyond Earth. Others point to recent laboratory experiments showing that non-living chemistry might create the same signal. Both groups agree on one thing. We're looking at a type of world that has no equivalent in our solar system, and we're only beginning to understand what it actually is. K2-18b belongs to a class of planets called subneptunes. They're the most common type of planet we've found orbiting other stars, yet we have nothing like them circling our Sun. Too large to be rocky like Earth or Mars. Too small to be gas giants like Jupiter or Saturn. These in-between worlds dominate the galaxy, and until recently, we had no idea what their surfaces might look like. The star K2-18 is what astronomers call an M-dwarf. A red dwarf. Cooler than our Sun by more than 2,000 degrees Celsius. Smaller, with only 45% of our star's radius. From Earth, even with the most powerful telescopes, you can't see it without instruments. It's simply too dim. Yet this unremarkable star, one of trillions like it scattered across the Milky Way, might be hosting something extraordinary. Red dwarfs make up roughly 75 to 80% of all stars in the galaxy. They burn their fuel so slowly that none of them, not a single one born since the universe began, has yet died of old age. K2-18 is estimated to be around 2.4 billion years old. Young by stellar standards. Our Sun is more than twice that age. But even at this relatively early stage, K2-18 has already settled into the calm, steady burn that will continue for hundreds of billions of years. The planet completes one orbit every 33 days. Fast by Earth standards, but this places K2-18b squarely in what scientists call the habitable zone. The distance from a star where temperatures allow liquid water to exist on a planet's surface. Not too hot. Not too cold. The Goldilocks zone, as it's often called, though that nickname hides how complex habitability actually is. When the Kepler Space Telescope first spotted K2-18b in 2015, it was just another data point. A slight dimming of starlight as an object passed in front of its host star. Thousands of such signals were being catalogued. What made this one different emerged later, when scientists calculated the planet's size, mass, and position. Here was a world in the habitable zone, large enough to hold onto a thick atmosphere, but potentially small enough to have a solid surface beneath. Then came the atmosphere measurements. The Hubble Space Telescope detected water vapor in 2019. Not just traces. Significant amounts. But Hubble's instruments couldn't tell us much more. Its sensitivity had limits. The wavelengths it could observe were restricted. Scientists knew there was water, but they couldn't see the full picture. They needed something more powerful. The James Webb Space Telescope changed everything. Launched in late 2021, Webb's mirror is nearly 3 times wider than Hubble's. Its instruments operate in infrared wavelengths that Hubble can barely touch. When Webb observed K2-18b, it needed just 2 transits to gather data that would have taken Hubble years of observations to match. And what Webb saw transformed K2-18b from an interesting discovery into something that might rewrite our understanding of where life can exist. The spectrum showed methane, about 1% of the atmosphere. Carbon dioxide, also around 1%. Water vapor, though less than 0.1% in the upper atmosphere where Webb's instruments are most sensitive. This combination is strange. If K2-18b were just a small version of Neptune, we'd expect to see ammonia. Lots of it. But there's barely any ammonia at all. The absence of something can be just as revealing as its presence. Scientists proposed an explanation that sounds like science fiction. K2-18b might be a Hycean planet. The term combines hydrogen and ocean. Picture this. A rocky core, possibly similar in composition to Earth's. Above it, an ocean. Not like our oceans. Deeper. Much deeper. Potentially hundreds of kilometers deep, stretching across the entire planet. And above that ocean, a thick atmosphere of hydrogen and other gases, pressing down with immense weight. Mikko Madhusudhan at the University of Cambridge coined the term Hycean in 2021. His team realized that planets like K2-18b could maintain liquid water oceans despite having hydrogen atmospheres. Conventional wisdom said such worlds would be too hot. The hydrogen would trap heat, creating runaway greenhouse effects. But the models showed something different. Under the right conditions, with the right distance from the star, these worlds could stay cool enough. The hydrogen blanket wouldn't cook the ocean. It would protect it. This hypothesis explains the atmospheric chemistry Webb detected. An ocean world with a hydrogen atmosphere would have methane and carbon dioxide from biological or geological processes in the water. The hydrogen would react with oxygen, keeping oxygen levels low and preventing ammonia from accumulating. Everything fits. Almost too neatly. Then there's the dimethyl sulfide. DMS, as scientists abbreviate it. On Earth, this molecule comes from phytoplankton. Microscopic marine organisms that drift through our oceans by the trillions. When they metabolize certain compounds, they release DMS as a waste product. It rises from the ocean into our atmosphere. You can smell it at the beach sometimes. That distinctive ocean scent. That's partly DMS. We've never found a non-biological process on Earth that produces meaningful amounts of DMS. It's considered one of the most reliable biosignatures we know. So when Webb's data suggested DMS in K2-18b's atmosphere, the implications were staggering. But here's where it gets complicated. The signal isn't strong. Statistically, it's at about 2.7 sigma confidence. In particle physics, scientists don't announce a discovery until they reach 5 sigma. That's a standard that means there's only a 0.00006% chance the signal is just random noise. K2-18b's DMS signal has about a 0.3% chance of being statistical fluctuation. Not terrible, but not conclusive either. More troubling, laboratory experiments in 2024 showed that certain chemical reactions in hydrogen-rich atmospheres can create DMS without biology. Ultraviolet light hitting specific molecules. Chemical pathways we hadn't considered. And in 2024, scientists detected DMS on a comet. A cold, lifeless comet. Suddenly, this supposedly bulletproof biosignature had holes in it. The debate intensified when researchers realized other molecules could be mimicking the DMS signal. Hydrocarbons with similar spectral signatures. Compounds that would look like DMS to Webb's instruments but mean something entirely different. Confirming what's actually there will require more observations. Different instruments. Years of additional data. Some scientists argue K2-18b isn't a water world at all. Recent computer models from September 2025 suggest that in planets this size, chemical processes destroy most water molecules. The hydrogen and oxygen separate. They bond with metals and other elements, sinking into the planet's interior. What looks like a water world from the outside might actually be a gas-rich mini-Neptune with no ocean at all. Just a thick, crushing atmosphere surrounding a core of rock and metal. The alternative interpretation is darker. Instead of a life-bearing ocean, K2-18b could have a surface of molten magma. The hydrogen atmosphere would trap heat efficiently. Too efficiently. The planet would be an inferno beneath its cloudy skies. The atmospheric chemistry we're seeing wouldn't come from life, but from volcanism. From the planet's interior bleeding gases into the sky. Both models fit the data. Both explain what Webb observed. The water world hypothesis needs life to account for the methane levels. The gas-rich model doesn't. Occam's razor suggests we should favor the simpler explanation. But simpler doesn't always mean correct. What makes this so difficult is that K2-18b exists in a category we don't fully understand. Subneptunes have no analog in our solar system. We can't visit one. Can't send a probe. Can't study one up close. Everything we know comes from analyzing starlight that's traveled for over a century through space, passed through an alien atmosphere for a fraction of a second, and then traveled another century to reach our telescopes. We're reading fingerprints in that light. Chemical signatures. Trying to reconstruct an entire world from shadows and spectra. The planet's density offers clues but no certainty. At 2.67 grams per cubic centimeter, it falls between Earth's 5.51 and Neptune's 1.64. That's consistent with a rocky core and thick atmosphere. It's also consistent with a water-rich composition, or an ice-rich interior with a moderate atmosphere. The density alone can't tell us which. The amount of light K2-18b receives is eerily similar to Earth's. About 1,368 watts per square meter, give or take. But that doesn't guarantee habitability. Venus receives almost twice that much, and its surface is hot enough to melt lead. Mars receives less than half, and its surface is a frozen desert. The amount of light matters. But so does the atmosphere. So does the planet's ability to regulate its temperature. So does whether there's even a surface to stand on. Understanding K2-18b means understanding an entirely new category of worlds. And what we learn here will apply to countless other planets. Because subneptunes aren't rare. They're everywhere we look. They're the most common type of planet in the galaxy. Kepler's data changed everything. Before that mission, we thought planets came in two basic sizes: small and rocky like Earth, or large and gaseous like Jupiter. The survey revealed something else entirely: a population peak between those extremes. Worlds that shouldn't exist according to our solar system's template. They're called subneptunes. Planets ranging from about 1.5 to 4 times Earth's radius. They make up roughly 30 to 50% of all exoplanets we've discovered. Yet we have nothing like them orbiting our sun. It's as if nature's most common planetary configuration somehow skipped us entirely. Or we're the anomaly. This gap in our understanding creates a fundamental problem. When we look at K2-18b, we're not comparing it to anything familiar. We're building models from scratch, testing hypotheses against worlds we've never seen up close. The formation pathways for subneptunes remain contested. One theory suggests they start as rocky cores that accumulate thick hydrogen atmospheres from the protoplanetary disk, born with those massive gas envelopes already in place. Another model proposes they begin as ice-rich bodies that migrate inward. The ice melts under increased stellar radiation. What remains is a water-rich interior beneath a hydrogen atmosphere captured from the disk or outgassed from the planet itself. Both scenarios can produce the same observational signature. Same size. Same density. Same atmospheric composition when viewed from 124 light-years away. But the internal structure would be completely different. One path gives you a rocky world with a thick atmosphere. The other gives you an ocean with a sky. Determining which is correct requires information we don't have. We can't measure K2-18b's internal structure directly. Can't drill into it. Can't send seismic waves through it. We're limited to surface observations. Atmospheric analysis. Indirect inference. The bimodality in planetary sizes adds another layer to this puzzle. Kepler found that planets cluster around two distinct radii. One group peaks at about 1.3 times Earth's size. The other around 2.4 times. There's a gap between them. A radius valley where fewer planets exist. This suggests different evolutionary paths. The smaller group likely represents rocky worlds that lost their atmospheres, stripped away by stellar radiation over billions of years. The larger group retained their gas envelopes. They're the subneptunes, massive enough to hold on to hydrogen despite their star's influence. K2-18b sits right in that larger cluster. But here's what makes this complicated. The radius valley isn't a hard boundary. It's statistical. Plenty of planets exist in the gap. And the position of that valley depends on the star's properties. Hotter stars push it to larger radii. Cooler stars like K2-18 shift it smaller. Which means K2-18b might be right on the edge of atmospheric retention. Balance between keeping its hydrogen envelope and losing it to space. That position matters for habitability. If the planet is losing its atmosphere, then any surface conditions we observe are temporary. The ocean, if it exists, would eventually be exposed to space, stripped away by stellar wind. The hydrogen atmosphere acts as a protective blanket. But if that blanket is thinning, the clock is ticking. We can estimate atmospheric loss rates, but the calculations depend on variables we can't measure precisely. The star's activity level over time. The strength of K2-18b's magnetic field. The exact composition of the upper atmosphere. Small changes in any of those factors alter the timeline dramatically. Then there's the composition uncertainty. The term subneptune implies a Neptune-like structure. But Neptune is an ice giant. Its interior is thought to contain water, methane, and ammonia ices mixed with rock, wrapped in a hydrogen-helium atmosphere. If K2-18b follows that template, it's not a water world at all. It's an ice world. The water would be high-pressure exotic ices. Not liquid. Not an ocean. Just crystalline structures formed under extreme pressure and temperature. Nothing life could use. The alternative is that subneptunes represent a different category entirely. Not scaled-down Neptunes, but something new. A hybrid between rocky planets and gas giants. With internal structures unlike anything in our solar system. If that's true, then the name itself is misleading. We're calling them subneptunes because we lack better terminology. But they might have more in common with super-Earths than with Neptune. The boundary between those categories is blurry. Super-Earths are typically defined as rocky planets up to about 10 Earth masses. Subneptunes as planets with significant hydrogen atmospheres. But a super-Earth with a thick atmosphere could look identical to a small subneptune. Same mass. Same radius. Same density. The only difference would be internal. One has a thin atmosphere over solid rock. The other has a deep atmosphere with no clear surface. K2-18b's mass is 8.63 times Earth's. That puts it at the upper end of super-Earths and the lower end of subneptunes. Right in the transition zone. Which category it belongs to depends on atmospheric mass fraction. How much of the planet is atmosphere versus core? Current estimates suggest K2-18b's atmosphere could be anywhere from 1 to 10% of its total mass. If it's 1%, the planet is mostly rocky with a substantial but not dominant atmosphere. If it's 10%, the atmosphere is so massive it determines the planet's entire structure. That's an order of magnitude uncertainty. And it changes everything about what the planet is like. A 1% atmosphere means there could be a solid or liquid surface beneath. A place where chemistry happens. Where molecules interact. Where, theoretically, life could exist. A 10% atmosphere means the hydrogen layer is so thick and so hot at depth that no surface exists. Just an increasingly dense gas transitioning into supercritical fluids. No boundary. No ocean. Nothing you could call a surface. Recent modeling work has tried to narrow this range. Simulations of subneptune formation suggest that if K2-18b formed in place, its atmosphere should be relatively thin. A few percent at most. But if it formed farther out and migrated inward, it could have captured much more gas. Migration is common. Most exoplanets we've found don't orbit where they formed. They move. Drift inward through gravitational interactions with the protoplanetary disk or with other planets. If K2-18b migrated, its current position tells us nothing about its formation environment. It could have started beyond the snow line where ice is stable. Accumulated a massive atmosphere in the cold outer disk. Then spiraled inward over millions of years. Or it could have formed roughly where it is now. Never migrated far. Retained only a modest atmosphere. Both histories are possible. Both fit the data. The migration question ties directly to composition. Planets that form beyond the snow line should be ice-rich. Water ice, methane ice, ammonia ice. When they migrate inward, that ice heats up. Some of it melts. Some of it vaporizes into the atmosphere. The result is a planet with a water-rich interior and an atmosphere loaded with volatiles. Exactly what you'd expect from a Hycean world. But planets that form inside the snow line would be rock and metal. Drier. Less volatile-rich. Their atmospheres would be captured hydrogen from the disk. Not outgassed water. The composition would be different. So finding water vapor in K2-18b's atmosphere seems to support the migration scenario. Water got there somehow. Either the planet formed with it, or it was delivered later by impacts. But here's the catch. The water vapor concentration is surprisingly low. Less than 0.1% based on Webb's observations. That's not what you'd expect from a planet with a massive water ocean. Earth's atmosphere is about 0.4% water vapor on average. More in the tropics. Less near the poles. But it's detectable. Measurable. On K2-18b, the water vapor signal is weak. Almost suspiciously weak for a supposed water world. One explanation is the cold trap effect. In Earth's atmosphere, water vapor rises until it reaches the cold upper layers. There it freezes out. Forms clouds. Falls back down as precipitation. This creates a cold trap that limits how much water vapor reaches the stratosphere. K2-18b might have an extremely efficient cold trap. Water evaporates from the ocean below. Rises through the hydrogen atmosphere. Hits a cold layer. Freezes. Never makes it to the upper atmosphere where we can detect it. If that's true, the low water vapor signal doesn't mean there's no ocean. It means the ocean is hidden. Locked beneath a thick atmospheric cold trap. Webb is seeing the dry stratosphere. Not the wet layers below. But that interpretation requires the ocean to exist in the first place. And the competing model suggests it doesn't. That K2-18b is a gas-rich mini-Neptune. The methane we see comes from chemistry, not life. The carbon dioxide comes from the star's radiation breaking apart molecules. The water vapor is just trace amounts, left over from formation or delivered by comets. No ocean required. Both models explain the observations. Neither can be ruled out yet. That's the frustrating reality of exoplanet science. We're working with incomplete information. Building castles on uncertain foundations. And K2-18b is just the beginning. There are thousands more subneptunes waiting to be studied. Each one a mystery wrapped in hydrogen and speculation. The real challenge isn't just figuring out what K2-18b is. It's understanding what subneptunes as a class can actually become. Because K2-18b isn't alone out there. Subneptunes are the most common type of planet we've found. They outnumber everything else. Hot Jupiters, super-Earths, Neptune analogs. Subneptunes dominate the census. Kepler found them everywhere. TESS keeps finding more. They orbit red dwarfs, sun-like stars, even slightly hotter F-type stars. And yet we have nothing like them in our own solar system. Earth is too small. Neptune is too big. There's a gap where sub-Neptunes should be. That gap tells us something important. Our solar system might not be typical. The architecture we're used to, rocky planets close in, gas giants farther out, might be the exception rather than the rule. Sub-Neptunes suggest a different kind of planetary system. One where migration is common. Where atmospheres are thick. Where the boundary between rocky and gaseous isn't clear-cut. Understanding sub-Neptunes means understanding how most planetary systems actually work. And that starts with a basic question. What determines whether a sub-Neptune becomes a Hycean world or stays a mini-Neptune? Size matters. But not in the way you'd think. It's not just about radius or mass. It's about the ratio between the core and the atmosphere. A planet with a large rocky core and a thin atmosphere behaves differently from one with a small core and a massive hydrogen envelope. The core provides gravity, holds the atmosphere down, keeps it from escaping. But if the atmosphere is too thick, the pressure at the base becomes extreme. Temperatures rise. The boundary between atmosphere and surface blurs. You end up with a supercritical fluid. Not quite gas, not quite liquid. Something in between. That's the problem with assuming K2-18b has a solid surface beneath its hydrogen envelope. The pressure might be too high. The temperature might be too extreme. The ocean, if it exists, might not sit on a rocky crust like Earth's oceans do. It could be suspended within layers of supercritical water. Compressed hydrogen above. Dense metallic core below. No clear boundary anywhere. Atmospheric escape changes everything. Hydrogen is light. Really light. It doesn't take much energy to strip it away. Ultraviolet radiation from the host star can do it. Stellar winds can do it. Even the planet's own heat can cause the upper atmosphere to expand and bleed off into space. This process is called hydrodynamic escape. It's why Earth doesn't have a thick hydrogen atmosphere anymore. We lost it early in our history. The sun's radiation stripped it away. Left us with nitrogen and oxygen. Secondary atmosphere formed by volcanic outgassing and later by life. Sub-Neptunes around red dwarfs face a different challenge. Red dwarfs are dim. They don't put out as much total energy as the sun. But they're violent. Especially when they're young. Stellar flares, coronal mass ejections, intense X-ray and ultraviolet bursts. All of that hammers planets in the habitable zone. K2-18 is about 2.4 billion years old. Not particularly young. But not ancient either. It still flares. Still produces bursts of high-energy radiation. Those bursts can strip away hydrogen, peel back the outer layers of the atmosphere. Over time, a mini-Neptune could lose enough hydrogen to become a super-Earth. The core remains. The ocean, if there was one, might survive. But the thick hydrogen envelope is gone. This process might explain why some sub-Neptunes have thick atmospheres and others don't. It's not just about formation. It's about survival. Here's where things get tricky. If K2-18b is losing hydrogen, how much has it lost already? And how much will it lose in the future? Models suggest that planets around red dwarfs can lose significant fractions of their atmospheres over billions of years. But the rate depends on distance from the star. K2-18b is far enough out that the radiation isn't catastrophic. Close enough that it's not negligible. The balance is delicate. If the planet formed with a massive hydrogen envelope, it might have enough left to maintain the Hycean scenario. If it started with less, the envelope might be thinning, transitioning towards something more Earth-like, or maybe something entirely different. A world with a thin hydrogen layer over a high-pressure steam atmosphere. Neither Hycean nor mini-Neptune. Something new. The methane abundance complicates this picture even further. Methane and hydrogen don't normally coexist in equilibrium. At high temperatures, methane breaks down. Carbon and hydrogen separate. You end up with carbon dioxide and water instead. But K2-18b's atmosphere shows both methane and carbon dioxide. That suggests the atmosphere isn't in equilibrium. Chemical reactions are happening. Slowly. Continuously. Methane is being produced somewhere. Either by geological processes on the surface, if there is a surface. Or by life, if there is life. Or by photochemistry in the upper atmosphere, driven by starlight. Photochemistry can do strange things. Ultraviolet light breaks molecules apart. Creates reactive fragments. Those fragments recombine in unexpected ways. On Titan, Saturn's largest moon, photochemistry produces complex organic molecules. Tholins, long-chain hydrocarbons, even amino acid precursors. All without biology. Just chemistry and sunlight. K2-18b's atmosphere might be doing something similar. Starlight hits the upper layers. Breaks apart carbon dioxide and water vapor. Creates methane and other organics. The methane we detect isn't proof of life. It's proof of chemistry. Active, ongoing chemistry. But chemistry that could, under the right conditions, lead to biology. Let's talk about that possibility. Life on K2-18b. Not intelligent life. Not civilizations. Just microbes. Simple organisms. Floating in the atmosphere or swimming in the ocean below. If the ocean exists. On Earth, life appeared relatively quickly. Within a few 100 million years of the planet cooling enough to have liquid water. The early Earth was hostile. Volcanic. Bombarded by asteroids. No oxygen in the atmosphere. And yet life took hold. Adapted. Thrived. If life can start on Earth under those conditions, why not on K2-18b? The planet receives similar amounts of starlight. It's in the habitable zone. Temperatures, at least in some layers, might be right. Water is present, even if only as vapor. Carbon dioxide and methane provide building blocks. The hydrogen atmosphere might even help. Hydrogen can act as a reducing agent. Drives certain chemical reactions that produce organic molecules. Early Earth had more hydrogen in its atmosphere than it does now. That might have been important for the origin of life. But there's a problem. Nitrogen. Life as we know it requires nitrogen. Proteins, DNA, RNA, all contain nitrogen. On Earth, nitrogen makes up 78% of the atmosphere. It's abundant. Available. Organisms have evolved to use it. On K2-18b, nitrogen is conspicuously absent. Chemical models suggest nitrogen compounds would be rare. Hard to detect. The atmosphere is hydrogen-dominated. Hydrogen reacts with nitrogen. Forms ammonia. Ammonia is reactive. Breaks down easily. Doesn't accumulate. Without nitrogen, how does life build proteins? How does it store genetic information? Maybe it doesn't. Maybe life on K2-18b, if it exists, uses a different biochemistry. Silicon instead of carbon. Sulfur instead of nitrogen. Entirely different molecular structures. We don't know if that's possible. We've never seen it. But the universe is vast. Chemistry is flexible. What seems impossible might just be unfamiliar. Then there's the question of energy. Life needs energy. On Earth, most life gets it from sunlight, directly or indirectly. Photosynthesis captures light, converts it to chemical energy. Food chains build from there. But K2-18b's atmosphere is thick. Hydrogen scatters light. Clouds and hazes block it. How much sunlight actually reaches the surface? Or the ocean? If there's an ocean, calculations suggest light levels would be low. Dim. Not zero, but not abundant. Photosynthesis might struggle. Life would need to adapt. Use longer wavelengths. Red light, infrared. Or rely on chemical energy instead. Hydrothermal vents on the ocean floor, if there is a floor, could provide energy. Chemical gradients. Dissolved minerals. Life could cluster around those vents. Just like it does on Earth in the deep ocean. Far from sunlight. Thriving on chemistry alone. That kind of life wouldn't produce oxygen. Wouldn't change the atmosphere. Wouldn't leave obvious biosignatures. It would be invisible to our telescopes. Hidden beneath kilometers of hydrogen and water. We'd never know it was there unless we sent a probe. And even then, finding it would be hard. Life in the deep ocean is sparse. Scattered. Easy to miss. This brings us back to dimethyl sulfide. The controversial biosignature. The molecule that might or might not be there. On Earth, DMS comes from phytoplankton. Tiny marine organisms. They produce it as a byproduct of their metabolism. It escapes into the atmosphere. We can measure it. Use it to track biological activity in the oceans. Finding DMS on K2-18b would be huge. Direct evidence of life. A smoking gun. But the signal is weak. Tentative. Barely above the noise. And there are alternative explanations. Photochemistry. Geological processes. Comets. Even measurement error. The signal could be real but not biological. Or it could be an artifact. Something in the data that looks like DMS but isn't. Distinguishing between these possibilities requires better data. More observations. higher precision. And that means waiting for Webb to observe K2-18b again, for future telescopes to come online, for technology to improve. Science moves slowly, especially when the stakes are this high. But here's what makes the wait so difficult. Every month that passes is a month we could be getting answers. Every telescope hour allocated to other targets is an hour not spent on K2-18b. And the competition is fierce. Webb is the most in-demand telescope in history. Thousands of proposals. Hundreds of targets. Everyone wants time. Everyone has questions that need answering. K2-18b is important, but so are distant galaxies, forming stars, other exoplanets. The telescope can only look at one thing at a time. So we wait. Meanwhile, the debate intensifies. Papers published. Rebuttals written. Models refined. Each new analysis shifts the probability slightly. Sometimes toward life. Sometimes away from it. The scientific process grinding forward at its characteristic pace. Methodical. Careful. Frustratingly slow when you want a definitive answer right now. But this is how science works. How it has to work. Extraordinary claims require extraordinary evidence. And we're not there yet. What we do have is context. K2-18b isn't the only sub-Neptune we've found. There are hundreds. Maybe thousands. Most haven't been studied in detail. Most never will be. Too faint. Too far. Wrong geometry for transits. But they exist. A whole population of worlds between Earth and Neptune in size. And we don't really understand them. Our solar system doesn't have anything like this. Nothing between Earth's radius and Neptune's. No intermediate examples to study up close. So we're learning from scratch. Building models. Testing hypotheses. Figuring out what these worlds actually are. The term sub-Neptune is almost misleading. It suggests a smaller version of Neptune. A mini ice giant. But that might not be accurate. Some could be ocean worlds. Others might be rocky planets with thick atmospheres. Some could have hydrogen envelopes sitting on top of molten surfaces. Magma oceans underneath, not liquid water. The possibilities are broad. Too broad. We need more data to narrow them down. And K2-18b, because it's bright enough to study, becomes a test case. A prototype. If we can figure out what it is, we might understand the whole population. That's why the stakes are so high. This isn't just about one planet. It's about an entire class. Understanding K2-18b means understanding thousands of other worlds we'll discover in the coming decades. Some closer. Some in better positions for study. Some around quieter stars. K2-18b might not be the best candidate for life. But it's the first one we can actually characterize. The first one where we can measure atmospheric composition in detail. That makes it invaluable. Even if the answer turns out to be disappointing. And disappointing is still possible. Likely, even. Most planets aren't habitable. Most don't have life. The universe is vast, but it's also mostly empty. Mostly hostile. Finding even microbial life on another world would be the discovery of the millennium. Maybe of human history. But it's not guaranteed. Not even probable, depending on who you ask. The odds are uncertain. The universe hasn't told us yet how common life is. K2-18b could be the first clue. Or it could be another dead end. Consider what we're actually looking for. Not cities. Not technology. Not intelligence. Just chemistry. Molecules that shouldn't be there unless something is producing them. Something alive. On Earth, that's oxygen. Methane combined with oxygen. Certain gases that react quickly and disappear unless constantly replenished. Biosignatures. But they're not foolproof. Nature is clever. Abiotic processes can mimic biology. Volcanoes produce gases. Lightning creates compounds. Photochemistry, the interaction of light with molecules, can generate complex chemistry without any life involved. Distinguishing between biological and non-biological sources is hard. Sometimes impossible without visiting the planet directly. That's the limitation we're up against. We can study atmospheres from 124 light-years away. Incredible. Revolutionary. But there's only so much we can learn from a distance. We can measure what's there. But understanding why it's there, what's producing it, that's harder. Requires models. Assumptions. Educated guesses. And those can be wrong. Have been wrong before. Will be wrong again. Science corrects itself over time. But in the moment, uncertainty dominates. So what happens next? More observations. That's certain. Webb will observe K2-18b again. Has to. The question is too important to leave hanging. But scheduling is complex. Coordinating telescope time takes years. Planning observations. Analyzing data. Writing papers. More years. We might not have definitive answers for another decade. Maybe longer. That's the reality of astronomy. Progress measured in years, not weeks. Patience isn't optional. It's required. But there's reason for optimism too. Technology improves. Future telescopes are coming. Larger mirrors. Better instruments. More sensitive detectors. The extremely large telescope. The Habitable Worlds Observatory. Missions specifically designed to study planets like K2-18b. They'll see things Webb can't. Measure molecules at lower concentrations. Distinguish between different sources more effectively. Build better models of what these worlds actually look like. And there's another approach. Direct imaging. Instead of watching planets transit their stars, just photograph them directly. Block out the star's light. Image the planet itself. Incredibly difficult. Requires advanced technology. Adaptive optics. Coronagraphs. Star shades. but it's being developed, tested. In a few decades, we might be able to take actual pictures of planets like K2-18b. See their surfaces, if they have surfaces. Watch their weather. Map their features. That would change everything. For now, though, we're limited to spectroscopy. Reading the rainbow. Decoding the light that filters through alien air. It's indirect. But it works. We've learned more about exoplanet atmospheres in the past 5 years than in the entire previous history of astronomy. And it's accelerating. Each new observation teaches us something. Each planet studied adds to the picture. K2-18b is part of that larger story. One chapter in a book we're still writing. And maybe that's the real point. Not whether K2-18b has life right now, but what it represents. The beginning of a new era, when we can actually study other worlds in detail, characterize their atmospheres, ask meaningful questions about habitability, about life, about our place in the universe. For most of human history, those were philosophical questions. Abstract. Unanswerable. Now they're scientific questions. Testable. With data. With evidence. That's profound. Whether K2-18b itself is inhabited or not, the fact that we can ask the question, that we have tools to investigate, that's the real breakthrough. Because K2-18b won't be the last. There will be others. Better candidates. Closer stars. More favorable conditions. Planets around sun-like stars instead of red dwarfs. Worlds with oxygen-rich atmospheres. Clearer biosignatures. Less ambiguity. K2-18b is just the first we've been able to study seriously. The first where the technology caught up with the ambition. It's a pioneer. And pioneers are messy. Complicated. Full of contradictions and uncertainty. But they open the path. They show what's possible. They teach us what questions to ask and how to answer them. That's K2-18b's role. Not to give us easy answers, but to show us where to look next. And pioneers teach us what we got wrong. That's crucial. Because K2-18b revealed something uncomfortable. Our models weren't good enough. The planet defied easy categorization. Water world. Maybe. Mini Neptune. Possibly. Something else entirely. Can't rule it out. The data fit multiple scenarios. That's the problem. Or rather, that's the lesson. Before K2-18b, scientists had theoretical models. Predictions about what these planets might be like. How thick their atmospheres were. What molecules they'd contain. How heat would distribute across their surfaces. Then Webb looked. And the reality was messier than the theory. More complicated. The methane levels were higher than expected. The carbon dioxide signal weaker. The temperature structure didn't match predictions. It forced a reckoning. Not with the planet, but with the models. They needed updating. Refinement. More variables. better physics. That's how science actually works. Not smooth and linear. Messy and iterative. You think you understand something. Then you measure it. And you are partly right and partly wrong. So you adjust. Build better models. Test them. Repeat. K2-18b is driving that cycle now, forcing researchers to confront assumptions about how hydrogen atmospheres behave, how carbon cycles through these worlds, what makes a planet habitable versus just temperate. These aren't small questions. They're fundamental. And they affect how we interpret every other planet we study. Because K2-18b isn't unique. It's typical. Subneptunes are everywhere. Most common planet type in the galaxy. We don't have any in our solar system. Nothing between Earth and Neptune. That gap in size. So we're learning about them from scratch. No local examples to study up close. Just distant observations. Light filtered through alien air. And K2-18b is the best example we have so far. Close enough to study. Bright enough star. Favorable geometry. Regular transits. It checks the boxes. That's why it matters so much. Not because it definitely has life, but because it's teachable. A planet we can actually learn from. And what it's teaching is humility. The universe is more complex than our models. Always has been. Always will be. That's not a failure. It's the nature of discovery. You start with simple ideas. Basic physics. Clean predictions. Then reality shows up. And it's complicated. Full of edge cases. Unexpected interactions. Chemistry you didn't account for. Physics you oversimplified. So you adapt. That's the process. And K2-18b is accelerating it. Each observation adds data. Constraints. Things the planet can't be. Things it might be. Slowly, the possibilities narrow. Not to a single answer. Not yet. But toward better questions. More refined hypotheses. Testable predictions. That's progress. Even when it feels slow. Even when headlines oversell the findings. Even when the public wants simple answers and scientists can only offer complex probabilities. The truth is, K2-18b is forcing us to develop new tools. Not just instruments. Conceptual tools. Ways of thinking about planets that don't fit Earth's mold. Because for centuries, we only knew one planet with life. Ours. So naturally, we looked for Earth twins. Similar size. Similar composition. Similar star. That made sense. Start with what you know. But K2-18b isn't an Earth twin. Not even close. 8 times the mass. Hydrogen atmosphere. Orbiting a red dwarf. Everything's different. Yet it might still be habitable. Might. That possibility is reshaping the field, expanding what we look for, how we define habitability. Because if life can exist there, under those conditions, then the range of possibilities is much wider than we thought. More planets qualify, more systems to study, more chances to find something. But here's the thing. We still don't know if K2-18b itself qualifies. The jury's still out, and might be for years. Because this isn't a simple measurement. It's an interpretation problem. The data is real. The spectra are accurate. But what they mean depends on context we don't fully have. Temperature profile of the atmosphere. Unknown. Circulation patterns. Unknown. Cloud coverage. Unknown. Surface conditions, if there even is a surface. Unknown. We're trying to solve a puzzle with most pieces missing. And some pieces might not even belong to this puzzle. They might be contamination, noise, artifacts of how we process the data. That's always a risk. Especially with signals at the edge of detectability. You see a pattern. Is it real? Or is it statistical fluctuation? Free sigma confidence sounds impressive. Until you remember that means 1 in 370 chance it's random. Not zero. Not definitive. Just probable. And when you're looking at dozens of molecules simultaneously, running hundreds of models, testing thousands of parameters, probabilities compound. False positives become likely. Not intentional. Just statistical reality. That's why the 5 sigma threshold exists. To separate signal from noise. To ensure discoveries are robust. Reproducible. Real. K2-18b's DMS signal doesn't meet that standard. Not yet. Maybe not ever. But that doesn't diminish its importance. Because even the possibility, even the hint, even the suggestion that we might be seeing biosignatures, that changes the conversation. It makes this planet a priority. A target for follow-up. A case study for how to do this kind of science carefully. How to communicate uncertainty. How to balance excitement with rigor. And that's valuable. Because the next planet might have clearer signals. Stronger evidence. Less ambiguity. And we'll know how to handle it because we practiced on K2-18b. Made mistakes. Learned lessons. Refined our methods. That's the real legacy. Not whether this specific planet has life, but what studying it teaches us about finding life elsewhere. The techniques we develop. The models we build. The standards we establish. Those will outlast any single discovery. They'll apply to dozens of planets. Hundreds eventually. Each one adding to the picture. Some will be false alarms. Others dead ends. A few might be genuine hits. But we won't know which is which unless we do the work. Carefully. Methodically. Without rushing to conclusions. And that's harder than it sounds. Because there's pressure. From media. From funding agencies. From the public. Everyone wants answers. Clear, simple, definitive answers. But science doesn't work that way. Especially not at the frontier. Especially not when you're trying to detect life across interstellar distances using instruments that barely existed 5 years ago. It's messy. It's uncertain. It's frustrating. But it's also exhilarating. Because we're doing something humans have never done before. Seriously investigating whether life exists beyond Earth. Not philosophically. Not speculatively. With data. With measurements. With evidence. That's unprecedented. And K2-18b sits right at the center of that revolution. Not because it's perfect, but because it's real. A planet we can study. An atmosphere we can probe. A mystery we can actually investigate. And whatever we find, whether it's life or just chemistry, whether it's ocean or magma, whether it's habitable or hostile, we'll have learned something profound. About how planets work. About what conditions permit life. About where to look next. That knowledge is cumulative. Each planet studied makes the next one easier. Each technique refined makes the next observation sharper. Each model improved makes the next interpretation clearer. We're building a framework. Step by step. Planet by planet. And K2-18b is a cornerstone. Not the first. Not the last. But essential. A planet that pushed us forward. That revealed our ignorance. That showed us how much we still have to learn. That's its gift. Not easy answers, but better questions. And the questions we ask now shape the answers we'll find later. What should we look for? How should we interpret ambiguous data? When should we claim discovery versus admitting uncertainty? Those aren't abstract philosophical debates. They're practical decisions that determine whether we find life in our lifetime or waste decades chasing ghosts. K2-18b forces us to confront those choices. Because it's not giving us clear answers. It's giving us complicated, messy, frustrating data that could mean multiple things. And how we respond to that, how we handle the ambiguity, sets precedent. Do we rush to conclusions because we want headlines? Or do we acknowledge limitations and keep working? The scientific community chose the latter. Mostly. There were sensational press releases. Premature celebrations. Media coverage that outpaced the actual findings. But the researchers themselves have been cautious. Transparent about uncertainties. Clear about what's confirmed versus speculated. That's progress. Because a generation ago, we might not have had that discipline. The temptation to claim discovery would have been overwhelming. Now we know better. We've learned from past mistakes. From claims that didn't hold up. From excitement that turned to embarrassment. K2-18b benefits from that institutional memory. From a scientific culture that values rigor over speed. And that matters more than any single detection. Because the next planet might have clearer biosignatures. Stronger signals. Less ambiguity. And when it does, we'll need a framework for evaluating it. Standards for what counts as evidence. Protocols for verification. K2-18b is building that framework. in real time, under pressure, with the world watching. It's not ideal, but it's necessary, because we can't wait until we have perfect data to figure out how to handle it. We need to learn by doing. Make mistakes now so we don't make them later. And that's what's happening. Every paper published about K2-18b adds to our understanding, not just of this planet, but of the process. How to model atmospheres. How to account for uncertainties. How to distinguish chemistry from biology. Those lessons apply everywhere. To every exoplanet. Every future observation. Every potential biosignature. That's the infrastructure of discovery. The unsexy foundation work that makes breakthroughs possible. And K2-18b is central to that effort. Not because it's special, but because it's available. A planet we can study right now with instruments that exist today. That's rare. Most potentially habitable planets are too far away. Their stars too dim. Their signals too weak. K2-18b is in a sweet spot. Close enough to observe. Bright enough to measure. Complex enough to challenge us. That combination won't exist for many planets. So we study this one intensely. Extract every bit of information. Push our instruments to their limits. Because opportunities like this don't come often. And we can't afford to waste them. Which brings us to the next question. What happens now? More observations, obviously. Different instruments. Longer integration times. New wavelengths. Each one adding detail. Resolving ambiguities. Confirming or refuting earlier findings. That's already happening. Teams are analyzing additional JWST data. Planning follow-up campaigns. Developing new models. The work doesn't stop just because we published papers. It accelerates. Because now we know what to look for. Where the gaps are. What measurements would be most valuable. That focus is powerful. It turns vague curiosity into specific research programs. Transforms speculation into testable hypotheses. Converts possibilities into probabilities. But there's a limit to what we can learn from K2-18b alone. At some point, we'll extract everything we can from this planet. Hit diminishing returns. Need new targets. And that's fine. Because K2-18b was never meant to answer every question. Just the first ones. Just enough to show us what's possible. To prove that we can characterize sub-Neptune atmospheres. Detect carbon-bearing molecules. Search for biosignatures across interstellar distances. Those capabilities are transformative. They change what's achievable. What's worth attempting. What deserves funding. Before JWST, most of this would have been impossible. Now it's routine. Difficult, but routine. And as technology improves, as instruments become more sensitive, as techniques get refined, it'll become easier. Cheaper. Faster. That's the trajectory. From impossible to hard to standard. K2-18b represents the transition point. The moment when characterizing potentially habitable exoplanet atmospheres became feasible. Not easy, but feasible. And once something becomes feasible, it scales. More planets get observed. More data gets collected. More patterns emerge. Eventually, we'll have a catalog. Dozens of atmospheres. Hundreds maybe. Each one revealing something about planetary formation, chemical evolution, habitability conditions. Some will be dead worlds. Others ambiguous. A few might show genuine biosignatures. But we won't know which is which until we look. And K2-18b taught us how to look. Where to point our telescopes. What wavelengths to prioritize. What molecules to search for. That knowledge compounds. Each planet studied makes the next one easier. Each technique developed makes future observations sharper. Each model validated makes new interpretations clearer. We're building momentum. And it's happening faster than anyone expected. 5 years ago, most scientists thought this kind of atmospheric characterization was decades away. Now we're doing it. Publishing results. Debating interpretations. Planning follow-ups. That acceleration is real. And it's not slowing down. Because the tools keep improving. Nancy Grace Roman Space Telescope launches soon. Then the Habitable Worlds Observatory. Each one more powerful than the last. Each one capable of observations that seem impossible today. And each one will look at planets like K2-18b. But better. With more precision. Less ambiguity. Stronger constraints. Until eventually, the question isn't whether we can detect biosignatures. It's whether the biosignatures are actually there. That's the future K2-18b is pointing toward. A future where finding life becomes a matter of observation rather than speculation. Where we can definitively say whether a planet hosts biology or just chemistry. Where ambiguity gives way to certainty. We're not there yet. Not close. But we're moving in the right direction. And every planet like K2-18b moves us further. Teaches us more. Reveals our blind spots. Exposes our assumptions. Challenges our methods. That's uncomfortable. But it's how science progresses. Not through easy answers, but through difficult questions. Not through confirmation, but through challenge. Not through certainty, but through doubt refined into knowledge. K2-18b embodies that process. A planet that refuses to fit our categories. That demands we think harder. Look closer. Question more deeply. It's frustrating. But it's also exactly what we need. Because finding life won't be easy. Won't be obvious. Won't announce itself clearly. It'll be subtle. Ambiguous. Contested. Just like the DMS signal. Just like the methane anomaly. Just like everything about K2-18b. And if we can't handle that complexity now, we won't handle it later. When the stakes are higher. When the evidence is stronger. When the implications are clearer. So we practice. On this planet. In this moment, with these tools, learning how to do the hardest thing humans have ever attempted, detecting life beyond Earth, not through radio signals or spaceships, but through chemistry, through light filtered through alien air, through patterns in spectra that might mean biology, or might not. That uncertainty is the point. Because life, if it exists elsewhere, won't accommodate our expectations, won't match our templates, won't make detection easy. It'll force us to expand our definitions, challenge our assumptions, rethink what we mean by alive. K2-18b is the first real test of whether we're ready for that challenge. And the answer so far is mixed. We're learning, improving, getting better at handling ambiguity. But we're also realizing how much we don't know, how many assumptions we made, how limited our frameworks are. That's humbling, but it's also necessary. Because the universe doesn't care about our limitations. It is what it is. And if we want to understand it, we need to adapt. Build better tools. Develop better theories. Ask better questions. K2-18b is teaching us how. So here's what we're left with. A planet 124 light-years away that we can't visit. Can't probe directly. Can't sample. All we have is light. Starlight that passed through an atmosphere for a fraction of a second before traveling more than a century to reach our telescopes. And from that light, we're trying to determine if life exists. Not intelligent life. Not civilizations. Just microbes. Chemistry that might be biological. Or might not. That's the reality. That's the challenge. And K2-18b sits at the center of it. Not because it's perfect. Not because it has clear answers. But because it's the first planet where we could even ask the question seriously. With data. With evidence. With instruments powerful enough to see molecular signatures in alien air. That's unprecedented. For all of human history, the question of life beyond Earth was philosophical. Abstract. Now it's scientific. Testable. We have tools. Methods. Frameworks. They're imperfect. Incomplete. But they exist. And they're improving. Every observation teaches us something. Every model refined makes the next interpretation clearer. Every technique developed makes future discoveries more likely. K2-18b is part of that process. Not the end point. Not even a highlight. Just a step. An important step. The moment when characterizing potentially habitable exoplanet atmospheres became feasible. When we could look at a sub-Neptune and actually measure what's in its air. Methane. Carbon dioxide. Water vapor. Maybe dimethyl sulfide. Maybe not. The uncertainty doesn't diminish the achievement. It defines it. Because this is what discovery looks like at the frontier. Messy. Complicated. Full of competing interpretations and provisional conclusions. Science doesn't give us clean narratives. It gives us data. And we argue about what it means. Build models. Test predictions. Wait for more observations. That cycle continues. For K2-18b. For dozens of other planets. For centuries probably. Until we either find life or conclude it's rarer than we hoped. But we won't get there by expecting easy answers. By demanding certainty before we've done the work. We'll get there by doing what we're doing now. Carefully. Methodically. With appropriate skepticism and appropriate excitement balanced in tension. Learning from mistakes. Refining methods. Building infrastructure that outlasts any single discovery. That's K2-18b's legacy. Not whether it hosts life, but what studying it teaches us about looking. About the questions we can answer and the ones we can't. About the difference between possibility and probability. Between hint and confirmation. Between exciting and definitive. Those distinctions matter. They determine whether we find something real or chase phantoms for decades. And K2-18b is where we're learning to make them. In real time. Under pressure. With limited data and unlimited speculation. It's not ideal. But it's necessary. Because the universe doesn't wait for us to be ready. It exists whether we understand it or not. And planets like K2-18b, worlds that defy our categories and challenge our assumptions, they're not obstacles. They're opportunities. Chances to expand our thinking. To recognize what we don't know. To build better frameworks for finding answers. That work isn't glamorous. Doesn't make headlines. But it's what enables breakthroughs. What transforms speculation into science? What turns curiosity into knowledge? And somewhere in that process, maybe on K2-18b or maybe on some planet we haven't discovered yet, we'll find what we're looking for. Evidence. Real, undeniable, reproducible evidence that life exists beyond Earth. Or we won't. And that answer matters too. Because knowing we're alone would be just as profound as knowing we're not. Either way, we'll have learned something fundamental about the universe. About how common or rare the conditions for life actually are. About whether Earth is typical or exceptional. About our place in a cosmos that's been indifferent to our existence for 13.8 billion years. K2-18b won't answer those questions alone. But it's helping us figure out how to ask them properly. How to design the observations. How to interpret the results. How to distinguish signal from noise. That contribution is permanent. Whatever we eventually discover about this specific planet, the methods we develop studying it will persist. Applied to other worlds. Other mysteries. Other questions we haven't even formulated yet. That's how science builds. Incrementally. One planet. One observation. One refined technique at a time. And right now, in this moment, K2-18b is where that building is happening. Not the foundation. Not the pinnacle. Just one crucial piece in a structure that's still taking shape. A structure that might eventually tell us whether we're alone. And if we're not, what life looks like when it doesn't look like us. A telescope floating 1 million miles from Earth just detected something that shouldn't exist. Two chemicals in the atmosphere of a distant planet, chemicals that on Earth are produced exclusively by living organisms. This isn't speculation or wishful thinking. It's data from the most powerful observatory humanity has ever built, pointing at a world 124 light-years away where something might be alive right now. The planet is called K2-18b. You've never heard of it, but scientists have been watching it obsessively since the James Webb Space Telescope turned its instruments toward this particular corner of the constellation Leo. What they found there has divided the scientific community into camps of cautious optimism and aggressive skepticism, because the implications are staggering. We might be looking at the first real evidence of life beyond Earth. Here's what makes this so compelling. The chemicals detected, dimethyl sulfide and dimethyl disulfide, don't just sometimes get produced by life on Earth. They're made almost exclusively by microscopic marine organisms like phytoplankton and algae. These aren't gases that form easily through random chemistry. They require specific biological processes, the kind that happen when living cells metabolize sulfur compounds in ocean water. Finding them in another planet's atmosphere is like walking into an empty house and smelling fresh coffee. Something made that. But let's pump the brakes for a second, because this story is way more complicated than the headlines suggest. K2-18b sits in what astronomers call the habitable zone of its star, a red dwarf much smaller and cooler than our Sun. The planet orbits this star every 33 days, receiving roughly the same amount of light Earth gets from the Sun. It's massive compared to our world, about 8.6 times Earth's mass and 2.6 times larger in diameter. That makes it what scientists call a sub-Neptune, somewhere between Earth and the ice giants in our own solar system. The distance? 124 light-years. That means the light the Webb telescope is analyzing left that planet during the late 1800s on Earth. We're looking at old light, ancient photons that traveled through space for more than a century before hitting Webb's mirrors and revealing their secrets. What makes K2-18b particularly interesting is that it might be what's called a Hycean world. The term was coined in 2021, a mashup of hydrogen and ocean, describing planets that weren't supposed to be habitable but might actually be perfect for life. These are worlds covered in deep oceans, potentially hundreds or even 1,000 kilometers deep in some places, with thick hydrogen-rich atmospheres above them. Before the concept of Hycean planets, scientists assumed hydrogen atmospheres would make worlds too hot for life. K2-18b is forcing a rethink of that assumption. The detection itself happened through a method called transit spectroscopy. When K2-18b passes in front of its star from our perspective, starlight filters through the planet's atmosphere before reaching us. Different molecules absorb specific wavelengths of light, creating a kind of chemical fingerprint. Webb's instruments are so sensitive they can detect these tiny variations in brightness and identify what gases are present millions of miles away. In 2023, the telescope detected methane and carbon dioxide in K2-18b's atmosphere. That was already significant, the first time such carbon-based molecules were spotted on an exoplanet in a habitable zone. But there was something else in the data, a weak signal that looked like it might be dimethyl sulfide. So the research team, led by scientists from the University of Cambridge, pointed Webb back at the planet using a different instrument, the mid-infrared instrument, designed to detect different wavelengths of light. What they found was stronger evidence for both dimethyl sulfide and dimethyl disulfide. The concentrations are wild compared to Earth. On our planet, these chemicals exist at levels below 1 part per billion in the atmosphere. On K2-18b, the estimated concentrations are over 10 parts per million. That's thousands of times stronger. If these readings are accurate, something is pumping these gases into that atmosphere at an extraordinary rate. On Earth, the process works like this. Marine phytoplankton, particularly dinoflagellates and coccolithophores, produce a compound called DMSP as part of their cellular processes. When these organisms die or get eaten, or when viruses attack them, DMSP breaks down into dimethyl sulfide. It's a complex chain involving bacteria, enzymes, and photochemical reactions. The DMS then escapes into the atmosphere where it plays a role in cloud formation and the planet's sulfur cycle. It's a signature of biological activity in ocean ecosystems. Finding it on another world should mean something similar is happening there. Should. That's where the controversy explodes. The statistical confidence level of this detection sits at 3 sigma. In scientific terms, that means there's a 0.3% chance the signal is just random noise, a fluke in the data. Sounds pretty good, right? Except the gold standard for scientific discovery is 5 sigma, which represents a probability of less than 0.00006% that the result is random. The difference between 3 sigma and 5 sigma is the difference between interesting and definitive. The research team knows this. They've been careful not to claim they've discovered life. What they're saying is that the data they have is consistent with the presence of these biosignature molecules, and that more observations are needed. They estimate another 16 to 24 hours of observation time with Webb could push them to that 5 sigma threshold. But here's where it gets messy. Other scientists have analyzed the same data and reached different conclusions. Some argue that the DMS signal isn't actually there at all, that it overlaps too much with methane signals and the analysis methods aren't robust enough to separate them. The data, they say, is consistent with a flat line, no bump or wiggle indicating a real detection. It's a classic case of seeing what you want to see in noisy data. Then there's the magma planet hypothesis. Some researchers think K2-18b isn't a water world at all, but a hellscape with oceans of molten rock instead of liquid water. Raymond Peary-Humbert, a planetary physicist at Oxford, has run models suggesting the planet is too hot for life, that any water present would be superheated and the surface would be volcanic. If that's true, the entire Hycean world concept for K2-18b collapses. There's also the non-biological production problem. DMS has been detected on comets and in interstellar space, proving it can form without life through purely chemical processes we don't fully understand. Just because we only know biological sources on Earth doesn't mean that's the only way it forms in the universe. The cosmos is creative with chemistry in ways we're still discovering. The debate reveals something fundamental about where we are in the search for extraterrestrial life. The James Webb Space Telescope has given us capabilities we've never had before. In just a few years of operation, we've learned more about exoplanet atmospheres than in the previous 3 decades combined. But we're operating at the absolute edge of what's possible with current technology. We're trying to detect faint signals from small planets incredibly far away, and interpretation of that data requires making assumptions about alien environments we can't directly observe. This is the paradox. We finally have tools powerful enough to potentially detect life on other worlds, but we might not have tools precise enough to prove it definitively. Webb might identify the most promising candidates, the worlds worth watching more closely, but confirming life could require the next generation of telescopes that haven't been built yet. What we do know is this: K2-18b is real. It's sitting in its star's habitable zone. It has an atmosphere with carbon-based molecules. The chemistry is complex and active. Whether that chemistry includes life remains an open question, one that's driving some of the most heated scientific debates happening right now. The lead researcher, Nikku Madhusudhan from Cambridge, has said that the only scenario currently explaining all the Webb data, past and present, is one where K2-18b is a Hycean world teeming with life. But he's also emphasized the need for deep skepticism, for testing and retesting, because that's how science works. No one wants to claim prematurely that we found alien life. What kind of life are we talking about if it exists? Not little green men or intelligent civilizations. The conditions on K2-18b, assuming it's habitable at all, would support microbial life at best. Think of Earth's oceans billions of years ago, filled with single-celled organisms producing gases as metabolic waste. That's the kind of biology we might be detecting, primitive but profound. The hydrogen-rich atmosphere adds another layer of complexity. Laboratory experiments show that Earth microorganisms can survive in hydrogen atmospheres, so hydrogen itself isn't a deal-breaker for life. But it changes which biosignature gases are reliable indicators. Some gases that scream life on Earth might form through non-biological processes in hydrogen-rich environments, making interpretation even trickier. The temperature is estimated between 250 and 300 Kelvin in the absence of greenhouse effects. That's cold, but not impossibly so. With the right atmospheric composition and pressure, liquid water could exist. The deeper layers of the atmosphere might be too hot, crushing, but there could be a zone, a sweet spot where conditions align. Ocean depths on Hycean worlds are staggering to contemplate. Depending on surface gravity and temperature, these oceans could extend tens to hundreds of kilometers deep, reaching pressures of 60,000 bar before the water transitions to high-pressure ice. That's an alien environment by any measure, but Earth's deep oceans host life in equally extreme conditions. Hydrothermal vents, crushing pressure, total darkness, yet life thrives. If K2-18b is producing dimethyl sulfide biologically, the implications extend far beyond one planet. Hycean worlds are thought to be common around red dwarf stars, the most numerous stars in the galaxy. Their larger sizes compared to rocky planets make them easier to observe and analyze. If these worlds can host life, the number of potentially habitable planets in the universe explodes. But we're getting ahead of ourselves. The data is preliminary, contested, requiring confirmation. The scientific process is working exactly as it should, with competing teams analyzing the same information and reaching different conclusions. That tension, that back and forth, is how we eventually arrive at truth. What happens next matters enormously. The full dataset became publicly available in late April, meaning more astronomers can now scrutinize every detail. Additional observation time with Webb has been requested. Other instruments on other telescopes might be able to contribute complementary data. The investigation is just beginning. Standing at this moment in history feels significant regardless of what we ultimately discover about K2-18b. We're asking questions about alien life not through speculation but through direct observation of another world's chemistry. We're analyzing gases in an atmosphere 124 light-years away and debating whether they come from living organisms. That alone represents a milestone. The search for life beyond Earth has entered a fundamentally new phase, one where we're no longer limited to searching for radio signals or planning distant missions to Mars. We're using infrared telescopes to sniff the air of alien worlds, looking for the chemical exhaust of biology. What we're learning is that the universe is far more complex than our models predicted, that every new observation raises new questions, and that the answer to whether we're alone might be closer than we ever imagined. But first, we need to understand what we're actually looking at. The challenge lies in how we actually detect these molecules from such an enormous distance. Light becomes the messenger. When K2-18b passes between its star and Webb's instruments, starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, creating a unique spectral fingerprint. Each molecule has its own signature pattern, a barcode written in missing wavelengths. Webb's mid-infrared instrument was specifically designed to read these barcodes. The telescope doesn't see K2-18b directly. What it captures is the star's light after it's been altered by passing through alien air. The brightness drops slightly during transit, and that drop varies by wavelength depending on what's in the atmosphere. Methane absorbs certain infrared wavelengths. Carbon dioxide takes others. And dimethyl sulfide, if it's there, should create its own distinctive absorption pattern. The problem is that these signals are incredibly faint. We're talking about detecting changes in brightness of less than 1%, and then within that tiny signal, finding even smaller variations that indicate specific molecules. It's like trying to identify a single instrument in an orchestra from a mile away while standing next to a jet engine. The initial detection of dimethyl sulfide came from analyzing how starlight was absorbed at specific infrared wavelengths between about 3 and 5 microns. The researchers saw what they interpreted as the spectral signature of DMS, a pattern that shouldn't be there unless something is producing this molecule. But here's where it gets complicated. Dimethyl disulfide has overlapping spectral features in the same wavelength range. Both molecules belong to the same chemical family. Both are predicted biosignatures. The current data can't definitively distinguish between them. Think of it like hearing a muffled voice through a wall. You know someone's speaking, but you can't quite make out whether they said yes or yeah. Both fit what you're hearing. Additional observations might sharpen the signal enough to tell them apart, but right now, we're stuck with one or the other, possibly both. The concentrations detected make the biological interpretation even more intriguing. On Earth, dimethyl sulfide exists in the atmosphere at concentrations below 1 part per billion by volume. It's produced by marine phytoplankton, released into the air, and quickly broken down by chemical reactions. The levels are low because production is balanced by destruction. On K2-18b, the estimated concentration is over 10 parts per million, thousands of times higher than Earth's levels. That's a massive difference requiring explanation. If biology is producing DMS on K2-18b, it must be doing so at extraordinary rates, or the molecule must be more stable in that environment, or both. A hydrogen-rich atmosphere might slow down the chemical reactions that normally destroy DMS on Earth. Alternatively, if there's a vast ocean teeming with DMS-producing organisms and the atmospheric chemistry is different, concentrations could build up to levels we never see in our own atmosphere. But the skeptics have compelling counterarguments. The DMS signal isn't strong. It appears in some data analysis methods but not others. When you're working at the absolute limits of instrumental sensitivity, noise becomes a serious concern. Random fluctuations can create patterns that look like signals. Statistical tools help separate real detections from false positives, but they're not perfect, especially when the signal is weak. The 3 sigma confidence level means there's a 0.3% chance the signal is just noise, a random fluctuation that happens to look like dimethyl sulfide. That might sound pretty good, but science has a higher bar. 5 sigma confidence, the gold standard for claiming a discovery, means less than a 0.00006% chance of being wrong. We're not there yet. Not even close. Then there's the methane problem. Computer models accounting for the physics and chemistry of both DMS and methane in a hydrogen-based atmosphere suggest the signal might actually be methane, not dimethyl sulfide at all. Methane was already detected on K2-18b in previous observations. If methane absorption overlaps with where we expect to see DMS, we might be mistaking one for the other. It's like trying to hear a whisper next to someone shouting. The loud signal can mask or mimic the quiet one. Raymond Peary-Humbert from Oxford University published research suggesting K2-18b might not be a water world at all. His models indicate the planet could be too hot for liquid water oceans, that what we're seeing might be better explained by a magma planet with oceans of molten rock instead of water. If that's true, the entire Hycean interpretation collapses. No water ocean means no marine phytoplankton-like organisms producing DMS. The whole biological hypothesis falls apart. A magma planet sounds outlandish, but it's not impossible. The temperature estimates for K2-18b range from about 250 to 300 Kelvin without greenhouse effects, but greenhouse warming from a thick hydrogen atmosphere could push surface temperatures much higher. If the deeper atmosphere is hot enough to melt rock, we're not looking at a potentially habitable world but a hellscape wrapped in hydrogen. The recent reanalysis added more fuel to the skeptical fire. Independent researchers examined the same Webb data and found that instead of a clear signal, a bump or wiggle in the spectrum, the data looks consistent with a flat line. No dimethyl sulfide. No dimethyl disulfide. Just noise and uncertainty. They argue that more observations are absolutely necessary before making any claims about biosignature gases. This is where science gets messy and beautiful at the same time. Multiple teams analyzing identical data reach different conclusions. It's not that anyone's being dishonest or incompetent. It's that interpretation at the edge of detectability involves judgment calls about data processing, statistical methods, and modeling assumptions. Different choices lead to different results. Some researchers emphasize the signal they see and argue it's worth taking seriously even if it needs confirmation. Others emphasize the uncertainty and argue the evidence doesn't meet the threshold for a credible detection. Both perspectives are valuable. The optimists push the field forward by exploring possibilities. The skeptics keep everyone honest by demanding rigorous proof. The Discovery team, led by researchers including Miku Madhusudhan, maintains that the only scenario currently explaining all the Webb data, including past and present observations, is a Hycean world potentially hosting life. They're not claiming definitive proof. They're saying this interpretation fits the evidence better than alternatives. But they also emphasize the need for deep skepticism of their own results. Science advances through testing and retesting, not through accepting the first interesting result that comes along. What's undeniable is that we're operating at the absolute limit of current technology. Webb was designed to do exactly this kind of observation, but even Webb has constraints. The signals from small planet atmospheres are weak. The number of suitable targets is limited. The inference methods, the mathematical tools we use to extract meaning from noisy data, have inherent limitations. We're pushing against fundamental barriers of what's possible with this generation of instruments. So what comes next determines everything. The full dataset became publicly available in late April, opening the door for more astronomers to scrutinize every detail. Fresh eyes might spot something previous analyses missed. Alternative interpretations will be proposed and tested. The scientific community will collectively work through the data, and consensus will eventually emerge, though it might take months or years. Additional observation time with Webb is crucial. The team estimates that 16 to 24 hours of follow-up observations could push the statistical significance from 3 sigma to 5 sigma, crossing the threshold from intriguing possibility to credible detection. That's not a guarantee, though. More data might strengthen the signal, or it might make the whole thing disappear, revealing it was noise all along. Other instruments might contribute complementary information. Ground-based telescopes, future space missions, different observational techniques could all add pieces to the puzzle. The detection of biosignature gases isn't a one-shot deal. It's a gradual accumulation of evidence from multiple independent sources until the weight of data becomes overwhelming. But there's a deeper question lurking beneath all the technical debate. Even if we confirm dimethyl sulfide is present, even if we reach 5 sigma confidence, even if alternative explanations are ruled out, we still face the interpretation problem. Does the presence of DMS necessarily mean life? On Earth, yes. Dimethyl sulfide is produced by biological processes, mainly marine phytoplankton breaking down a precursor molecule called dimethylsulfonylpropionate. The biochemical pathways are complex, involving enzymes, bacteria, viruses, and photochemical reactions. It's deeply integrated into Earth's sulfur cycle and plays a role in cloud formation by contributing to sulfate aerosol production. The connection to life is ironclad here. But K2-18b isn't Earth. It's a world with a hydrogen atmosphere, potentially crushing pressures, temperatures, and chemistry completely unlike anything in our experience. Could there be non-biological pathways producing DMS under those exotic conditions? We genuinely don't know. DMS has been detected on comets and in the interstellar medium, proving it can form without biology in certain environments. Those detections don't involve planetary atmospheres or the concentrations we're discussing, but they demonstrate that the molecule itself isn't exclusively biological. Unknown chemistry in unknown conditions could potentially generate biosignature gases through non-living processes. This is the challenge facing astrobiology. There's no silver bullet, no single molecule that unambiguously screams life regardless of context. Everything depends on context. The molecule matters less than the environment producing it. What we need is a comprehensive understanding of what K2-18b actually is, and right now, we're operating with incomplete information. Let's step back and examine what we actually know about this world. K2-18b orbits an M-dwarf star, a red dwarf, about 124 light-years away in the constellation Leo. The star itself is smaller and cooler than our Sun, with a surface temperature around 3,457 Kelvin compared to the Sun's 5,778 Kelvin. Its radius is only 45% of the Sun's. These details matter because they shape the radiation environment, the energy budget, and the habitability prospects of any planet in the system. K2-18b completes one orbit every 33 days, placing it squarely within what astronomers call the habitable zone, the region where temperatures theoretically allow liquid water to exist on a planet's surface. It receives roughly the same amount of stellar radiation that Earth receives from the Sun. That sounds promising until you remember that habitable zone is a crude first-order approximation. It doesn't account for atmospheric composition, greenhouse effects, albedo, or a dozen other factors that determine whether a planet is genuinely habitable or a hellscape dressed in optimistic terminology. The planet is massive. 8.6 times Earth's mass. 2.6 times Earth's radius. Those numbers push it into the category of sub-Neptunes, worlds larger than Earth but smaller than Neptune. In our solar system, there's nothing quite like it. We have rocky terrestrial planets and gas giants, but nothing in between. Sub-Neptunes are common throughout the galaxy, yet we have no local example to study. That's a problem because it means we're working from theory and distant observations rather than direct knowledge. Here's where things get interesting. K2-18b's size and mass suggest it shouldn't be a rocky planet like Earth. It's too big. Traditional models predicted that planets of this size would have thick hydrogen atmospheres, crushing pressures, and no solid surface to speak of. Mini Neptunes, basically. Not places where life as we understand it could take hold. But the data from Webb complicated that picture considerably. The detection of methane and carbon dioxide in 2023 was the first hint that K2-18b might be something different. These carbon-based molecules in a habitable zone planet suggested chemistry compatible with life. Then came the potential DMS detection, and suddenly we're looking at a planet that doesn't fit neatly into existing categories. This led researchers to propose that K2-18b might be a Hycean world. The term Hycean was coined in 2021 by Niku Madhusudhan and his team at Cambridge. It's a portmanteau of hydrogen and ocean. The concept describes planets with vast liquid water oceans beneath thick hydrogen-rich atmospheres. Before this idea emerged, astronomers assumed such planets would be too hot to harbor life. The hydrogen atmosphere would trap heat through a runaway greenhouse effect, turning any water into superheated steam. But detailed modeling suggested otherwise. Under certain conditions, a hydrogen atmosphere could actually be cool enough to allow liquid water oceans at the surface. Think about what that means. A planet with an ocean covering its entire surface, potentially hundreds or even thousands of kilometers deep depending on temperature and gravity. Pressures at the ocean floor could reach 60,000 bar before transitioning to high-pressure ice phases. Above this ocean, a thick blanket of hydrogen gas, completely unlike Earth's nitrogen-oxygen atmosphere. Temperatures at the surface might reach 200 degrees Celsius or higher, yet the ocean persists because the pressure is so immense. This is not an environment remotely similar to Earth. If life exists there, it's operating under physical and chemical rules we can barely imagine. The hydrogen atmosphere alone changes everything. On Earth, certain biosignature gases are considered reliable indicators of life because they react quickly and shouldn't persist without biological replenishment. But in a hydrogen-rich atmosphere, those same gases might be produced through non-biological chemistry or might be stable enough to accumulate without life. The rulebook we've been using doesn't apply. Laboratory experiments have shown that Earth microorganisms can survive in hydrogen-rich atmospheres. Hydrogen itself isn't toxic to life. But that's different from saying life could originate and thrive in such conditions. We're extrapolating from our limited understanding of terrestrial biochemistry into a regime where we have no data. The ocean depths on a Hycean world depend critically on surface temperature and gravity. Models suggest they could span anywhere from tens of kilometers to potentially 1,000 kilometers before the pressure becomes so extreme that water transitions into exotic ice phases that exist only under crushing force. These ice layers would be hot, not cold, because temperature increases with depth. The conventional image of ice doesn't apply here. Within such an ocean, where would life exist? Near the surface, where temperatures might be survivable but radiation from the star could be intense. Deeper down, where pressure is enormous but conditions might be more stable. Around hydrothermal vents on the ocean floor, if such things exist. We genuinely don't know. The possibilities are wide open, constrained only by physics and chemistry, not by any examples we can point to. But there's a competing interpretation that throws all of this into question. Some researchers, including Raymond Pury-Humbert at Oxford, argue that K2-18b isn't a water world at all. Their models suggest it's too hot for liquid water to exist at the surface. Instead, they propose it might be a magma planet, a world where the surface is molten rock, not ocean. If that's correct, the entire Hycean hypothesis collapses, and K2-18b becomes a completely different kind of object, one with no habitability potential whatsoever. The debate hinges on details. Atmospheric composition, cloud properties, albedo, internal heat flow. Small differences in these parameters lead to radically different conclusions. One model produces a temperate water world. Another produces an inferno. Both are consistent with the limited data we have, which tells you how uncertain the situation really is. What about the concentration of DMS itself? On Earth, dimethyl sulfide exists in the atmosphere at levels below 1 part per billion by volume. Trace amounts. On K2-18b, the estimated concentration is over 10 parts per million. Thousands of times stronger. That's a massive difference. If the detection is real, it demands an explanation. Biological processes on Earth don't produce DMS at those concentrations in the atmosphere. So either K2-18b has vastly more biological activity than Earth, or the chemistry producing DMS there operates through entirely different mechanisms. Perhaps life on a Hycean world, if it exists, is incredibly productive. An ocean teeming with microorganisms, all releasing DMS as a metabolic byproduct, could potentially generate those high concentrations. Or maybe the atmospheric dynamics are different. On Earth, DMS gets oxidized quickly. On K2-18b, maybe it persists longer, accumulating to higher levels. We're speculating now, stacking assumptions on top of incomplete data. The alternative is that we're misinterpreting the signal entirely. Recent reanalyses of the web data suggest the DMS feature might not be there at all. Instead of a clear spectral bump indicating the molecule's presence, the data might be consistent with a flat line, just noise. The strength of the claimed detection depends entirely on how you process and interpret the raw data. Different analysis techniques produce different results. That's not ideal when you're trying to make the most important discovery in human history. Both DMS and DMDS are from the same chemical family, and their spectral features overlap in the wavelength range Webb observed. The current data can't definitively tell them apart. Future observations might resolve that ambiguity, or they might reveal that neither molecule is actually present. We're waiting on more data to settle questions that can't be answered with what we have now. The scientific process is working exactly as it should. Initial detection, public announcement, independent verification attempts, debate, more observations, gradual convergence toward truth. It's messy. It's slow. It involves false starts and dead ends. But it's the only method we have for reliably understanding reality. The alternative is wishful thinking dressed up as certainty. What happens if follow-up observations confirm DMS is really there? We're still left with the interpretation problem. Does its presence mean life, or does it mean we discovered an exotic chemical pathway that operates under conditions we've never studied? The problem runs deeper than just identifying molecules. It's about understanding what they mean in an environment nothing like Earth. When we detect DMS in our atmosphere, we know where it comes from because we've studied the organisms that produce it. We've mapped the pathways, measured the rates, understood the seasonal variations. We have context. On K2-18b, we have none of that. We're looking at a hydrogen-rich atmosphere wrapped around a planet that might be ocean, might be magma, circling a star completely different from our sun. Every assumption we make is built on Earth-based chemistry, and there's no guarantee those rules apply. Consider how DMS behaves here. Marine phytoplankton, specifically dinoflagellates and coccolithophores, synthesize it through complex biochemical pathways involving enzymes, viral interactions, and photochemical processes. Once released into the atmosphere, it oxidizes quickly, gets broken down, contributes to cloud formation. The whole cycle is tightly regulated by temperature, light availability, nutrient concentration. Change any of those parameters, and the entire system responds differently. Now imagine trying to predict what happens on a world where the atmospheric pressure is different, the radiation environment is different, the ocean chemistry is different. You can't just transplant Earth biology there and expect it to work the same way. That's why the concentration issue is so puzzling. Over 10 parts per million compared to less than 1 part per billion on Earth. If biology is producing it, the ecosystem would need to be extraordinarily productive, generating DMS at rates we've never observed. Or the atmospheric chemistry could be preventing its breakdown, allowing it to accumulate. Both scenarios require mechanisms we don't fully understand. You're trying to reverse engineer an alien biosphere from a single data point. It's like finding a footprint and trying to reconstruct the entire animal. Then there's the non-biological possibility. DMS has been detected on comets and in interstellar space, proving it can form without life. The processes aren't well understood, but they exist. Maybe K2-18b has some exotic chemistry driven by radiation, temperature gradients, or mineral interactions that produces DMS abiotically. We can't rule that out. The challenge is that we don't know all the ways molecules can form under extreme conditions. Chemistry textbooks are written based on laboratory experiments and Earth observations. We're constantly discovering that nature is more creative than our models predict. Statistical significance matters here more than in most fields. The current detection sits at 3 sigma. In particle physics, you need 5 sigma before claiming a discovery. That's because the stakes are enormous and the risk of false positives is real. 3 sigma means there's a 0.3% chance the signal is just noise, random fluctuations masquerading as a real feature. Sounds pretty good until you consider how many observations astronomers make, how many wavelengths they examine, how many molecules they search for. With enough attempts, even unlikely coincidences become probable. The researchers know this. They're calling for more observation time, specifically 16 to 24 hours with Webb, to push the detection past 5 sigma. That would reduce the false positive probability to essentially 0. But getting that telescope time isn't trivial. Webb is the most in-demand observatory in history. Every astronomer wants a piece of it. Time is allocated through competitive proposals, peer review, priority ranking. K2-18b is important, but so are hundreds of other targets. Distant galaxies, forming stars, other exoplanets. The telescope can only point in one direction at a time. Patience is required, which is frustrating when you're sitting on potentially the biggest discovery ever made. While we wait, other teams are analyzing the same data independently. That's how science progresses. Multiple groups, different analysis techniques, various assumptions. If everyone reaches the same conclusion, confidence grows. If results diverge, that tells you the signal is ambiguous and more data is essential. Recent reanalyses have been less optimistic than the original announcement. Some researchers see a flat line where others see a spectral feature. The difference comes down to data processing choices. How you remove noise, how you model the baseline, which wavelength ranges you emphasize. None of these choices are obviously right or wrong. They're judgment calls, and different judgments lead to different conclusions. This is normal in cutting-edge science, especially when working at the limits of instrumental capability. Webb is astonishingly sensitive, but it's not magic. Detecting molecules in the atmosphere of a planet 124 light-years away requires extracting incredibly faint signals from noisy data. Think about what's actually happening. Light from a distant star passes through a thin layer of gas surrounding a planet. That gas absorbs specific wavelengths corresponding to molecular vibrations. Webb measures the spectrum, looking for those absorption features. But the planet's atmosphere is tiny compared to the star. The signal you're trying to detect is a fractional change in brightness at specific wavelengths. Any instrumental artifact, any calibration error, any unaccounted variable can produce false features. The overlap between DMS and DMDS complicates things further. Both molecules are sulfur-containing organics with similar structures. Their spectral signatures overlap in the wavelength range Webb observed. You can't definitively say which one you're seeing, or if it's a combination, or if it's something else entirely producing a similar-looking feature. Future observations at different wavelengths might resolve the ambiguity, but right now, the data is consistent with multiple interpretations. What about the hydrogen-rich atmosphere itself? On Earth, biosignature gases are identified based on their behavior in our nitrogen-oxygen atmosphere. Certain molecules, like oxygen or methane in large quantities, are considered strong biosignatures because they shouldn't coexist without biology constantly replenishing them. But in a hydrogen-dominated atmosphere, those rules change. Some gases that would be biosignatures on Earth become unreliable indicators elsewhere. The chemistry is just different. Hydrogen reacts with things nitrogen doesn't. It changes oxidation states, reaction rates, equilibrium concentrations. You need entirely new models to predict what a biosignature would even look like in that environment. Microorganisms from Earth can survive in hydrogen-rich conditions. Lab experiments have demonstrated that. So hydrogen itself isn't toxic to life. But would life that evolved in a hydrogen atmosphere produce the same waste gases as Earth life? Maybe. Maybe not. Evolution is contingent. Life adapts to its environment using whatever chemistry is available. On Earth, photosynthesis uses water and produces oxygen. On a Hycean world, maybe life uses different molecules, produces different byproducts. We're looking for Earth-like biosignatures because those are the ones we know how to recognize. That doesn't mean they're the only ones that exist. The bigger question is whether we're even asking the right questions. For nearly a century, astronomers have focused on atmospheric disequilibrium as a sign of life. The idea is that certain gas mixtures shouldn't exist together unless something is actively maintaining them. Oxygen and methane, for example. They react with each other, so if you detect both in significant quantities, something must be replenishing them faster than they can react away. Life is one explanation. But it's not the only one. Geological processes, photochemistry, exotic atmospheric dynamics could also create disequilibrium. The challenge is distinguishing between biological and non-biological sources from light years away. K2-18b represents a test case for this entire approach. If the DMS detection holds up, if follow-up observations confirm it, we're forced to interpret what it means. Is it life? Is it chemistry we don't understand? Is it an instrumental artifact we haven't identified? Each answer has profound implications. If it's life, everything changes. If it's not, we've learned something important about planetary atmospheres and the limits of remote sensing. Either way, the process of figuring it out advances our understanding. The lead researchers have been careful with their language. They're not claiming definitive proof of life. They're presenting data, proposing interpretations, calling for verification. That's exactly how it should work. The temptation to overhype is enormous. This is the kind of discovery that makes careers, wins awards, gets remembered in textbooks. But claiming life prematurely, only to be proven wrong later, damages credibility and sets the field back. Better to be cautious, methodical, rigorous. Let the data accumulate. Let the debate unfold. Let the truth emerge through the messy, slow process of scientific consensus building. What happens if 5 sigma is reached and DMS is confirmed beyond doubt? We're still left with interpretation. The molecule is there, but what's producing it? That question can't be answered with spectroscopy alone. You'd need detailed atmospheric models, laboratory experiments simulating High-Cean conditions, maybe even direct detection of other biosignatures to build a coherent case. One molecule isn't enough. You need a pattern, a suite of indicators that together point toward biology as the most likely explanation. That's the standard. Anything less leaves too much room for doubt. And that's where the timeline becomes critical. The researchers estimate they need between 16 and 24 additional hours of observation time with Webb. That might not sound like much, but telescope time is precious. Webb isn't dedicated to a single target. Hundreds of research teams compete for every available hour. Scheduling those observations, collecting the data, processing it, that takes months. Maybe longer. During that waiting period, the scientific community doesn't sit idle. The original dataset became publicly available in April, which means independent researchers can now access the same raw data. They'll run their own analyses, apply different statistical methods, test alternative interpretations. Some will support the findings. Others will challenge them. That's the messy reality of frontier science. Consensus doesn't emerge from a single paper but from a community-wide process of scrutiny and verification. Here's what makes this particularly complicated. The signal isn't clean. It's buried in noise, overlapping with methane spectral features, sitting right at the edge of what current instruments can reliably detect. Different teams using different data reduction techniques might reach different conclusions about whether the bump in the spectrum is real or an artifact. That's already happening. Recent reanalyses of the same data suggest the signal might be consistent with a flat line, no feature at all. The original team stands by their results, pointing to specific wavelengths and modeling approaches that support the detection. Who's right? More data will tell. But even if the 5 sigma threshold is eventually reached, even if DMS is confirmed with statistical certainty, we're not done. Confirmation means the molecule is there. It doesn't automatically mean life put it there. You'd still need to rule out non-biological explanations. And here's where it gets tricky. DMS has been detected in comets. It's been found in the interstellar medium, the diffuse gas and dust between stars. That proves it can form through purely chemical processes, no biology required. So how do you distinguish between biological and non-biological sources from 124 light-years away? Context matters. On Earth, DMS concentrations in the atmosphere are typically below 1 part per billion. On K2-18b, the estimated concentration is over 10 parts per million, thousands of times higher. That difference is significant. Non-biological processes tend to produce trace amounts, not massive concentrations. But that's an assumption based on Earth chemistry. Maybe High-Cean world chemistry operates differently. Maybe there's some exotic photochemical pathway we haven't considered that churns out DMS at high concentrations without biology. You can't rule it out just because we haven't thought of it yet. This is why the search for biosignatures requires multiple lines of evidence. One molecule, however compelling, isn't enough. You need a pattern. A suite of gases that together make biological production the most parsimonious explanation. The researchers detected methane and carbon dioxide in earlier observations. Those are consistent with biological activity, but they're also produced by geological processes. Add DMS to the mix and the biological hypothesis becomes stronger. But it's still not definitive. You'd want to see other sulfur compounds, maybe organic molecules, signatures of metabolic waste products that don't have obvious non-biological sources. The challenge is that we're working with incredibly limited information. Transmission spectroscopy gives you atmospheric composition, nothing more. You can't see the surface. You can't measure ocean salinity or pH. You can't detect cellular structures or DNA. All you have is the chemical fingerprint of gases backlit by starlight. From that, you're trying to infer the presence of life. It's like trying to diagnose a patient's illness by analyzing their breath, except the patient is 124 light-years away and you only get to sample their breath once every few years. What would make the case stronger? Detection of gases that have no known non-biological source. On Earth, certain compounds are produced exclusively by life. Methyl chloride, for example, is made by marine algae and has no significant geological source. If you detected that on K2-18b, alongside DMS and other biosignatures, the biological hypothesis would become much harder to dismiss. But even then, you'd need to demonstrate that no unknown chemistry could produce those gases. That's a high bar. Some researchers argue we're approaching this wrong. Instead of looking for individual molecules, we should be looking for chemical disequilibrium patterns that only life can sustain. The idea is that life constantly pushes chemistry away from equilibrium, maintaining gas mixtures that would otherwise react away. On Earth, oxygen and methane coexist because life produces both faster than they can react with each other. Without life, that disequilibrium would collapse within a few million years. If you can demonstrate that K2-18b's atmosphere is in persistent disequilibrium, and that no geological or photochemical process can maintain it, that's stronger evidence than any single molecule. The problem is proving the negative. How do you demonstrate that no unknown process exists? You can't. You can only show that all known processes fail to explain the data. That's weaker than it sounds because planetary science is full of surprises. Venus has phosphine in its atmosphere, and nobody's entirely sure why. It could be life, or it could be some weird atmospheric chemistry we don't understand yet. The same uncertainty applies here. There's also the question of what kind of life we're talking about. If K2-18b hosts biology, it's almost certainly microbial. Single-celled organisms living in the ocean, metabolizing whatever chemistry is available. Not fish, not plants, nothing complex. The conditions wouldn't support it. High atmospheric pressure, crushing ocean depths, temperatures that might reach 200 degrees Celsius in deeper layers. Surface waters might be cooler, more temperate, but you're still looking at an alien environment fundamentally different from Earth. Life adapted to that environment wouldn't look like Earth life. It would be something else entirely. Which raises an interesting philosophical point. When we search for biosignatures, we're inherently biased toward Earth-like life because that's the only reference we have. We know what Earth life produces, what gases it releases, what chemical disequilibria it creates. But life elsewhere might operate on completely different principles. Silicon-based instead of carbon-based. Using ammonia instead of water. Metabolizing in ways we haven't imagined. If that's the case, we might be looking right at biosignatures without recognizing them because they don't match our preconceptions. This is the central tension in astrobiology. You want to cast a wide net, consider all possibilities, but you also need specific, testable predictions. You can't search for everything simultaneously, You have to prioritize, make educated guesses about what's most likely. That inevitably introduces bias. The challenge is being aware of that bias and not letting it blind you to unexpected findings. K2-18b might not be the planet where we finally confirm extraterrestrial life. The signal might not hold up. The interpretation might shift as more data comes in. But it's pushing the field forward regardless. It's forcing researchers to refine their models, develop better detection methods, think harder about what constitutes convincing evidence. Each attempt, whether successful or not, teaches us something about planetary atmospheres, about the limits of our instruments, about the complexity of distinguishing biology from chemistry. The next generation of telescopes will help. Instruments currently being designed will have higher sensitivity, better spectral resolution, the ability to study smaller, rockier planets. They'll be able to detect fainter signals, resolve overlapping spectral features, measure atmospheric composition with greater precision. That will narrow the uncertainty, make the interpretations less ambiguous. But it won't eliminate the fundamental challenge. We're still doing remote sensing across vast distances, inferring complex phenomena from limited data. What happens if we do eventually confirm life on K2-18b or another exoplanet? The implications extend far beyond astronomy. It would reshape our understanding of biology, showing that life isn't unique to Earth but emerges wherever conditions allow. It would raise questions about how common life is, whether intelligence is inevitable, what our place is in a universe teeming with biology. Those aren't just scientific questions. They're philosophical, even existential. But we're not there yet. Right now, we're in the uncertain middle ground between detection and confirmation. The data is suggestive but not conclusive. The interpretations are plausible but not proven. The path forward requires patience, rigor, and a willingness to accept that we might not get definitive answers as quickly as we'd like. The scientific process doesn't move in straight lines. It advances through incremental steps, occasional breakthroughs, and frequent setbacks. Each observation adds a data point, constrains the possibilities, eliminates hypotheses that don't fit. That's how knowledge builds. Not through sudden revelations, but through accumulated evidence slowly shifting the balance of probability. K2-18b represents one data point in that larger process. A significant one, certainly. The detection of potential biosignature gases on a habitable zone planet using our most advanced telescope is noteworthy regardless of how the interpretation ultimately resolves. But it's still just one planet among thousands we've discovered, millions that likely exist in our galaxy alone. Consider the broader landscape. Webb has only been operational since 2022. In that short time, it's already transformed exoplanet science, providing atmospheric data that was impossible to obtain before. WASP-39b, a hot Jupiter, revealed a complete chemical inventory including water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and sulfur dioxide. That last one was particularly interesting because it requires photochemistry, chemical reactions driven by starlight in the upper atmosphere. It showed that planets far different from Earth still have complex atmospheric processes. TOI 561b, an ultra-hot super-Earth, challenged assumptions about small planets close to their stars. Conventional wisdom said they shouldn't retain atmospheres. The stellar radiation should strip away any gases. Yet Webb detected what appears to be a thick atmosphere, possibly above a global magma ocean. The planet's unusually low density suddenly made sense. It's not just rock. It has a substantial gaseous envelope despite the harsh environment. These discoveries matter because they expand our understanding of what's possible. Each unexpected finding forces researchers to reconsider their models, question their assumptions, think more creatively about planetary formation and evolution. That's the value of exploration. Not just confirming what you already believe, but discovering what you didn't anticipate. Which brings us back to the central question. How do we know when we've actually found life? The answer isn't simple because life itself isn't simple. On Earth, biology produces countless chemical signatures. Oxygen, methane, phosphine, nitrous oxide, dimethyl sulfide, hundreds of volatile organic compounds. But almost all of these can also be produced through non-biological processes under the right conditions. Oxygen comes from photosynthesis, but also from water vapor breaking apart in the upper atmosphere. Methane comes from microbes, but also from volcanic activity and geochemical reactions. Phosphine might come from life, but it's also produced in gas giants through atmospheric chemistry. The challenge is distinguishing biological production from geological or atmospheric production when you can't visit the planet to investigate directly. You're limited to remote observations, spectral analysis, statistical inference. That means looking for combinations of gases that are unlikely to coexist without biology. On Earth, oxygen and methane together create a disequilibrium signature. They react with each other chemically, so their simultaneous presence suggests continuous replenishment from different sources. Biology maintains that disequilibrium. Remove life, and the gases would equilibrate, disappearing over geological timescales. But what if alien biochemistry operates differently? What if life elsewhere uses different metabolic pathways, produces different waste products, creates different atmospheric signatures? We wouldn't necessarily recognize it because we're calibrated to Earth's patterns. This is the biosignature detection paradox. You need specific predictions to guide your search, but those predictions inevitably narrow your perspective. You might miss what you're not looking for. Some researchers argue for a more agnostic approach. Instead of searching for specific molecules, look for any chemical disequilibrium that can't be explained by known planetary processes. If you detect an atmosphere that's thermodynamically unstable, something must be maintaining it. That something could be biology. The problem with this approach is that planetary processes are complex and not fully understood. What looks like unexplained disequilibrium might just be physics we haven't modeled correctly. You risk false positives if you're not careful. The flip side is false negatives. If you're too conservative, demanding ironclad proof before accepting a biosignature, you might dismiss genuine detections because they don't fit your preconceptions. Science requires balancing these risks. Being open to unexpected findings while maintaining rigorous standards of evidence. It's not easy. The history of science is littered with premature announcements, overinterpreted data, claims that didn't hold up to scrutiny. That's why the K2-18b team is proceeding cautiously despite the suggestive signals. They've reached 3 sigma statistical significance, meaning there's a 0.3% chance the signal is random noise. That sounds compelling, but in scientific terms, it's not enough for confirmation. The standard for discovery claims is 5 sigma, which corresponds to a probability of less than 0.00006% that the signal is coincidental. Getting from 3 sigma to 5 sigma requires more observation time, better data, additional wavelength coverage. The team estimates they need 16 to 24 more hours of telescope time to reach that threshold. Whether they'll get it is uncertain. Telescope time is precious. Webb is oversubscribed by a factor of 10, meaning far more proposals than available observation slots. Every hour spent on K2-18b is an hour not spent on other targets. committees evaluate proposals, prioritize based on scientific merit, feasibility, likely impact. K2-18b is compelling, but so are dozens of other candidates. The allocation process is competitive. Assuming they do get the time and the signal strengthens to 5 sigma, then what? Even definitive detection of dimethyl sulfide doesn't automatically mean life. It just means biology becomes the most likely explanation. You'd still need to rule out alternative scenarios. Could photochemistry in a hydrogen-rich atmosphere produce DMS through pathways we haven't considered? Could geological processes release sulfur compounds that combine in the atmosphere to form DMS? Are there reactions involving minerals, water, and atmospheric gases that might generate these molecules without biology? These questions need answers before claiming discovery. The scientific community would scrutinize every aspect. The data reduction methods, the spectral analysis techniques, the atmospheric models, the statistical treatments. Other teams would attempt independent analyses using the same data. They'd look for errors, biases, alternative interpretations. This process is essential. Extraordinary claims require extraordinary evidence, and the claim of extraterrestrial life is about as extraordinary as it gets. The evidence needs to withstand intense scrutiny from multiple independent groups before acceptance. Even if the biosignature interpretation holds up, you're still left with profound uncertainties. You know life probably exists on that planet, but you don't know what kind. You don't know how it originated, how it evolved, whether it's widespread or rare. You don't know if it's simple or complex, ancient or recent, thriving or barely surviving. All you have is a chemical signature in an atmosphere 124 light-years away. The rest is inference and speculation. That might seem frustrating, but it's actually remarkable. A century ago, we didn't know if other planets existed beyond our solar system. 50 years ago, we had no way to study their atmospheres. 20 years ago, we couldn't detect biosignature gases even if they were present. Now we're at the threshold of potentially confirming life elsewhere. The pace of progress has been extraordinary. The capabilities we've developed in just a few decades would have seemed like science fiction to earlier generations. Future telescopes will push further. The Habitable Worlds Observatory, currently in early planning stages, is designed specifically to characterize Earth-like planets around Sun-like stars. It will have a coronagraph to block starlight, allowing direct imaging of planets in reflected light rather than relying on transit spectroscopy. That opens up new possibilities. You could study planets that don't happen to pass in front of their stars from our perspective. You could analyze surface features, detect seasonal variations, maybe even observe geological activity. Ground-based extremely large telescopes coming online in the next decade will complement space-based observations. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope will have collecting areas far larger than Webb, allowing them to gather more photons and achieve higher spectral resolution. They'll be limited by Earth's atmosphere, but adaptive optic systems are becoming sophisticated enough to compensate. Combined with space telescopes, they'll provide multiple independent measurements of planetary atmospheres, reducing uncertainties and strengthening conclusions. The technology is advancing rapidly. So is our theoretical understanding. Researchers are developing more sophisticated atmospheric models, accounting for complex chemistry, cloud formation, atmospheric circulation patterns. They're studying extreme environments on Earth, places where life persists under conditions previously thought uninhabitable. Deep ocean vents, acidic hot springs, Antarctic ice, high-altitude deserts. Each discovery of terrestrial extremophiles expands the envelope of possibility for where life might exist elsewhere. This is the context in which K2-18b should be understood. Not as a definitive answer, but as a milestone in an ongoing journey. We're learning how to ask the right questions, developing the tools to answer them, building the knowledge base to interpret what we find. Each planet we study teaches us something new about atmospheric processes, planetary formation, the conditions necessary for habitability. That knowledge accumulates, refining our search strategies and improving our detection capabilities. The question of whether we're alone in the universe won't be answered by a single observation. It will be answered through accumulated evidence from multiple planets, multiple biosignatures, multiple independent confirmation. K2-18b might be part of that answer. Or it might turn out to be a false alarm, teaching us about atmospheric chemistry instead of biology. Either way, it's moving the field forward. That's what matters. Not whether this particular planet hosts life, but whether we're getting better at finding out. And we are. The tools exist now. The methods are proven. The candidates are identified. What happens next depends on how we use them. The timeline stretches ahead with uncomfortable uncertainty. Those additional observation hours with Webb might happen next year. Or the year after. Scheduling depends on committee decisions, competing priorities, telescope availability. Meanwhile, K2-18b keeps orbiting its red dwarf star, oblivious to our scrutiny, its atmosphere continuing whatever processes are producing those spectral features we're arguing about. What's clear is that we've crossed a threshold. Not necessarily the threshold of discovering life, but the threshold of being able to look. Webb represents a capability that didn't exist 5 years ago. We can now analyze the atmospheric composition of planets in habitable zones around other stars. That's not incremental progress. That's a fundamental shift in what's possible. Think about where we were just a generation ago. The first exoplanet around a Sun-like star was confirmed in 1995. Before that, we literally didn't know if planets existed beyond our solar system. We suspected they did, but suspicion isn't knowledge. Now we've cataloged thousands. We know that planets are common, that rocky worlds exist throughout the galaxy, that many orbit within their stars' habitable zones. The question has shifted from, are there other worlds? To, what are those worlds like? K2-18b forces us to confront how we answer that second question. The data is ambiguous. The interpretations diverge. But the fact that we're having this debate at all, arguing over spectral features in the atmosphere of a planet 124 light-years away, that's the real story. We're not just theorizing anymore. We're measuring, analyzing, testing hypotheses against actual observations. Whether dimethyl sulfide is really there, whether it's produced by life or exotic chemistry, those questions will get resolved through the normal scientific process. More data will arrive. Better models will be developed. Consensus will eventually form, though it might take years. That's fine. Science doesn't run on news cycle timelines. It runs on evidence accumulation, and evidence takes time. The broader trajectory is what matters. Each planet studied adds to our understanding of atmospheric processes, of what's normal and what's anomalous, of how to distinguish biology from geology from instrumental artifacts. We're building a reference library of planetary atmospheres, learning to read chemical signatures across an enormous range of conditions. That knowledge base will prove invaluable when the next candidate emerges, and the one after that. Because K2-18b won't be the last world where we detect potential biosignatures. Webb is just getting started. There are thousands of exoplanets within its observational range. Sun will be too hot, too cold, too massive, too small. But Sun will sit in that narrow band of conditions where life as we understand it might exist. Those are the targets. Those are where humanity's attention will focus over the coming decades. The search for life beyond Earth isn't a single moment of discovery. It's a process of gradually narrowing uncertainty, eliminating alternatives, building confidence through accumulated evidence. Maybe K2-18b is the first confirmed detection. Maybe it's a stepping stone toward understanding Hycean worlds that don't actually host life. Maybe it's teaching us that our biosignature detection methods need refinement before we can trust them. All of those outcomes advance the field. What we're witnessing is the maturation of a scientific discipline. Astrobiology is transitioning from speculation to observation, from hypothetical arguments to data-driven conclusions. The tools exist now to test ideas that were purely theoretical a decade ago. That's transformative. It changes the conversation from, could there be life? To, here's what we measured, here's what it might mean, here's how we find out for sure. The philosophical implications lurk beneath the technical debates. If life exists on K2-18b, even simple microbial life, it would demonstrate that biology isn't unique to Earth. It would show that the chemical and physical conditions necessary for life arise naturally when planets form in habitable zones. That has profound consequences for how common life might be throughout the galaxy, throughout the universe. If it happened twice in one small corner of space, it's probably happened billions of times elsewhere. But those implications only matter if the detection is real. And that's still uncertain. The data is suggestive. The interpretation is plausible. The statistical confidence is approaching significance. But we're not there yet. The gap between intriguing possibility and confirmed discovery remains, and crossing that gap requires rigor that can't be rushed. So we wait. For more telescope time. For additional observations. For independent verification. For the slow grinding process of science to either confirm or refute what the initial data suggested. That waiting is hard, especially when you're potentially sitting on the biggest discovery in human history. But it's necessary. Getting it right matters more than getting it first. Meanwhile, the search continues. Other planets. Other biosignatures. Other research teams developing new detection methods, new analytical techniques, new ways of interpreting atmospheric chemistry. The field is advancing on multiple fronts simultaneously. K2-18b is one thread in a much larger tapestry. Whether this particular thread leads to confirmation of life or not, the tapestry keeps growing, the picture keeps coming into focus. What happens over the next few years will determine whether K2-18b enters the history books as the first world where we found evidence of extraterrestrial life, or as a cautionary tale about the challenges of biosignature detection. Either way, it's already changed how we think about the search. It's demonstrated that we have the capability to detect potential biosignatures. It's revealed the complexity of interpretation. It's shown us both the promise and the pitfalls of this endeavor. The universe doesn't care about our timelines or our eagerness for answers. It will reveal its secrets at its own pace, through careful observation and rigorous analysis. Our job is to keep looking, keep measuring, keep questioning our interpretations until the weight of evidence becomes overwhelming. That's how we'll eventually answer the question of whether we're alone. Not through a single dramatic discovery, but through accumulated knowledge that makes the answer undeniable. K2-18b might be that answer. Or it might be a false start. The only way to know is to keep looking at the data, keep refining the models, keep pushing the instruments to their limits. Because somewhere out there, on some planet around some distant star, life probably exists. Finding it, proving it, understanding it, that's the challenge defining this era of astronomy. And we're closer now than we've ever been. 41 light-years from Earth, there's a world where rocks don't just melt, they vaporize. Where the surface glows brighter than molten steel. Where an entire year passes in less time than it takes you to sleep through the night. This is 55 Cancri, and according to everything we thought we knew about planetary science, it shouldn't have an atmosphere. It shouldn't be able to hold on to gases at all. Yet somehow, against every prediction, it does. The discovery announced in May 2024 changed the game completely. Let's start with something that sounds impossible. Imagine a planet twice the size of Earth, but 8 times heavier. Now place it so close to its star that it completes an orbit in just 17.7 hours. The planet's surface temperature reaches 3,770 Kelvin on the side facing the star. That's 6,330 degrees Fahrenheit. Hot enough to turn silicon, iron, aluminum, and calcium into vapor. The night side, perpetually locked in darkness, still glows at temperatures exceeding 2,000 degrees Fahrenheit. This isn't science fiction. This is 55 Cancri, officially named Janssen, and it represents one of the most extreme environments ever confirmed to exist. The planet orbits a Sun-like star designated 55 Cancri, located in the constellation Cancer. When astronomers first detected it using data from 2003 and 2004, they had no idea what they'd found. At the time of its announcement in 2004, Janssen became the first super-Earth ever discovered around a main sequence star. Nothing in our solar system prepared us for this. We have rocky planets like Earth and Mars. We have gas giants like Jupiter and Saturn. But we have nothing that bridges the gap quite like this, a world that defies our categories and challenges our models of how planets form and survive. The numbers tell a story of extremes that push physics to its limits. Janssen orbits at just 1.4 million miles from its host star. To put that in perspective, Mercury, the closest planet to our Sun, orbits at roughly 36 million miles. Janssen is 25 times closer to its star than Mercury is to ours. At this distance, the gravitational forces and radiation levels would absolutely devastate any world in our solar system. What happens to a planet in such proximity? It becomes tidally locked. One hemisphere eternally faces the star, baking under relentless radiation. The other faces the void of space, never seeing direct starlight. This creates a planetary environment unlike anything we experience on Earth, a world split between fire and relative cold, though even that cold side maintains temperatures that would instantly incinerate any known form of life. Early observations using the Spitzer Space Telescope between June and July of 2013 revealed something strange. The hottest spot on the planet wasn't where it should be. On a tidally locked world with no atmosphere, you'd expect the point directly facing the star, the substellar point, to be the hottest location. But measurements showed the peak temperature shifted 30 to 41 degrees eastward from where physics said it should be. Something was moving heat around. But what? Scientists initially proposed 2 possibilities. Either the planet had an atmosphere capable of redistributing thermal energy through winds, or something else entirely was at work, perhaps exotic rotational dynamics or internal heat transport through the planet's presumed magma ocean. For years, the debate remained unresolved. Spitzer's instruments, though revolutionary for their time, couldn't provide the spectral resolution needed to definitively answer the question. Then came the James Webb Space Telescope. Between its near-infrared camera and mid-infrared instrument, Webb possessed capabilities that transformed exoplanet science. In observations that each lasted about 8 hours, the telescope measured subtle changes in infrared light as Janssen orbited its star. The technique, called secondary eclipse spectroscopy, works by capturing the combined light of the star and planet, then subtracting out the star's light alone when the planet passes behind it. What remains is the planet's own thermal emission, its heat signature, carrying information about atmospheric composition encoded in specific wavelengths. The precision required for these measurements is staggering. Janssen's thermal emission is utterly dwarfed by the brightness of its host star. Isolating that faint planetary signal demands not just sensitive instruments, but sophisticated data analysis techniques that can tease apart overlapping spectral features. Multiple observations were necessary to build sufficient signal-to-noise ratios and check for consistency. When the team analyzed the data, they found patterns that shouldn't exist. Between 4 and 5 microns in the infrared spectrum, less light reached the telescope than expected. This dip, this absorption feature, pointed to something specific: molecules in the planet's atmosphere absorbing those particular wavelengths. The spectral signature matched carbon dioxide or carbon monoxide. Not vaporized rock, which would show a completely different pattern, but actual volatile gases. The kind of atmosphere you'd associate with volcanic outgassing, not a bare molten surface. This was the moment everything changed. For decades, atmospheric scientists operated under a firm assumption: rocky planets orbiting this close to their stars simply cannot maintain atmospheres. The physics seemed straightforward. Intense stellar radiation should strip away gases through atmospheric escape, where high-energy photons give molecules enough kinetic energy to overcome the planet's gravity and flee into space. At Janssen's orbital distance, this process should be devastating and continuous. Yet here was evidence, the strongest to date, that a rocky exoplanet beyond our solar system possesses a genuine atmosphere. Not rock vapor. Not a tenuous envelope of evaporated minerals. An actual secondary atmosphere, likely rich in carbon-bearing molecules, persisting despite conditions that should obliterate it. The discovery paper, published in Nature in May 2024, was unequivocal. The measurements ruled out the hypothesis that Janssen is simply a lava world shrouded in vaporized rock. Instead, the data indicated what researchers call the bona fide volatile atmosphere, one that's continuously replenished by outgassing from below. This is where the magma ocean hypothesis enters the picture. Scientists believe Janssen's interior remains so hot that vast portions of its mantle exist in a molten state. Temperatures and pressures keep enormous quantities of rock liquefied. As this magma ocean churns through convection, driven by the extreme temperature gradient between day and night hemispheres, dissolved gases bubble up and escape through volcanic activity. Think of it like champagne releasing carbon dioxide, but on a planetary scale with molten rock instead of wine. The outgassing rate apparently matches or exceeds the rate of atmospheric loss to space, creating a dynamic equilibrium. Gases escape. More gases bubble up. The atmosphere persists not because it's stable, but because it's continuously renewed, a planetary system maintaining itself against impossible odds through sheer volcanic vigor. Renyu Hu, a planetary scientist at the California Institute of Technology, pointed out something profound about this discovery. By observing this extrasolar example of atmosphere-magma interaction, we gain insights into how the early solar system worked. Earth itself, during the first 100 million years after formation, would have been hot enough to maintain widespread magma oceans. Venus likely experienced similar conditions. Mars too. Studying Janssen gives us a window into processes that shaped our own world billions of years ago, except we're watching them unfold in real time rather than trying to reconstruct them from ancient geological records. The implications extend far beyond one peculiar planet. If rocky worlds can maintain atmospheres under such extreme conditions, what does that mean for our understanding of planetary habitability? What does it tell us about the diversity of rocky planet evolution? The conventional wisdom just took a serious hit, and scientists are racing to understand the mechanisms that make this possible. But there's more to this story. The controversy surrounding Jansen's very existence reveals how challenging exoplanet science can be, and how easily initial observations can mislead us. When astronomers first analyzed the radial velocity data that revealed Jansen's presence, they thought they'd found a planet with a 2.8-day orbital period. This measurement stood for years, shaping early models of the 55 Cancri system. Then in 2005, researcher Jack Wisdom questioned the planet's existence entirely, suggesting the signal was an alias, a false pattern created by the way the data was sampled. The debate intensified. Some analyses seemed to confirm the 2.8-day planet. Others cast doubt. Finally, in 2010, researchers Dawson and Fabrici demonstrated conclusively that the true orbital period was 0.7365 days. Not 2.8 days. Less than 18 hours. The planet was real, but it was far closer to its star than anyone had imagined. This correction wasn't just a minor adjustment. It fundamentally transformed our understanding of Jansen's environment, moving it from merely very close to extraordinarily close, from extreme to apocalyptic. When the planet's transit across its host star was finally observed and confirmed in April 2011 using the MOST Space Telescope, it vindicated Dawson and Fabrici's work and opened the door to direct characterization of the planet's properties. Transit observations are crucial because they let astronomers measure a planet's radius directly by watching how much starlight it blocks. Combined with mass measurements from radial velocity data, this enables calculation of density, a fundamental clue about internal composition. For Jansen, the density measurements revealed a world unlike anything in our solar system, setting the stage for decades of follow-up observations that would culminate in the James Webb Space Telescope's groundbreaking atmospheric detection. Now we understand that Jansen represents something extraordinary, a natural laboratory where planetary science meets its most extreme test case. The discovery of its atmosphere forces us to reconsider fundamental assumptions about what's possible in the universe. And the story of how we came to understand this world reveals the messy, contentious, ultimately triumphant process of scientific discovery itself. What we're learning is that the universe doesn't care about our assumptions. It will create worlds we never imagined, operating under conditions we thought impossible. Jansen is just the beginning. The temperature measurements tell a story that defies intuition. Jansen's dayside reaches 3700 Kelvin according to the latest Spitzer data reanalysis from 2022. That's 6300 degrees Fahrenheit. Hot enough to vaporize calcium. Silicon boils at these temperatures. Iron exists as vapor, not metal. We're not talking about a place where rocks melt. We're describing conditions where the distinction between solid, liquid, and gas becomes almost meaningless for materials we think of as permanent. The night side presents its own puzzle. Even though this hemisphere never sees direct starlight, it maintains temperatures around 1400 Kelvin. That's 2000 degrees Fahrenheit. Glowing red-hot in perpetual darkness. Something is redistributing heat across this world with remarkable efficiency, and for years scientists couldn't agree on what that something was. Here's where things get genuinely strange. When the Spitzer Space Telescope mapped Jansen's thermal emissions between June and July 2013, astronomers expected the hottest spot to align with the substellar point, the location directly facing the star. Basic physics suggested that's where maximum heating should occur. Instead, They found the temperature peak offset by 30 to 41 degrees eastward. 30 degrees doesn't sound dramatic until you realize what it implies. That offset means heat is being transported across the planet's surface through some active mechanism. Atmospheric winds could explain this. But so could more exotic phenomena involving the planet's rotation or internal dynamics. The offset is too large to dismiss as measurement error, yet too consistent to be random variation. Think about what this redistribution requires. You need energy transport powerful enough to shift the thermal maximum across hundreds of kilometers of surface. On Earth, our atmosphere and oceans accomplish this through convection and circulation patterns. But Jansen's environment is so extreme that conventional atmospheric models struggle to explain how gases could survive long enough to establish stable circulation. The debate raged for years. One camp argued the planet must have an atmosphere despite the hostile conditions. How else could you explain the heat distribution? The offset hotspot? The surprisingly moderate nightside temperatures? Another group countered that we were simply seeing vaporized rock, a tenuous shroud of silicon, iron, aluminum, and calcium boiled directly off the surface. At Jansen's temperatures, rocks don't just melt. They evaporate. This rock vapor could create something atmosphere-like without being a true secondary atmosphere. Distinguishing between these scenarios became crucial. A rock vapor envelope would form from the planet's own surface material, constantly replenished as long as temperatures stayed extreme. It's not really an atmosphere in the traditional sense, more like the haze above a boiling pot. A true secondary atmosphere would require ongoing volcanic outgassing from the interior, implying active geological processes and a fundamentally different planetary state. The Spitzer observations provided tantalizing clues but lacked the spectral resolution to definitively settle the question. Infrared brightness measurements showed patterns inconsistent with a bare rock surface, suggesting some kind of gaseous envelope. Yet the data couldn't identify specific molecular signatures that would prove the presence of volatile compounds like carbon dioxide or carbon monoxide. Scientists needed better instruments. They needed precision spectroscopy capable of detecting absorption features from specific molecules. They needed observations that could distinguish between the spectral signature of vaporized rock elements and actual atmospheric gases. Enter the James Webb Space Telescope. Webb's near-infrared camera and mid-infrared instrument can measure thermal emission spectra with unprecedented detail. The observing strategy was elegant. Watch Jansen complete multiple orbits, capturing data when the planet is visible beside its star and when it disappears behind the star during secondary eclipse. During eclipse, you're seeing only starlight. Before and after eclipse, you're seeing starlight plus the planet's own thermal glow. Subtract one from the other, and you isolate the planet's emission spectrum. Each observation session lasted about 8 hours, covering nearly half of Jansen's 17.7-hour orbital period. The precision required is extraordinary. The planet's thermal emission is utterly dwarfed by the star's brightness, like trying to detect a candle next to a searchlight. Multiple observations were necessary to build sufficient signal-to-noise ratio and verify consistency across different orbital phases. When the team analyzed Webb's NIRCan data in 2024, they saw something unmistakable. A dip in the spectrum between 4 and 5 microns. Less light reaching the telescope at these specific wavelengths. This wasn't random noise or instrumental artifact. This was absorption. Something in the planet's atmosphere was absorbing infrared light at wavelengths characteristic of carbon-bearing molecules. Aaron Beloroof from JPL explained the significance. That spectral dip suggests carbon monoxide or carbon dioxide, both of which absorb strongly in this wavelength range. The MIRI data extending from 5 to 12 microns confirmed the pattern. This wasn't vaporized rock. Silicon, iron, aluminum, and calcium would produce completely different spectral signatures. What Webb detected pointed unambiguously toward volatile compounds, gases you'd expect from volcanic emissions, not from evaporated surface material. The implications hit immediately. Janssen has a bona fide atmosphere. Not rock vapor. Not a temporary artifact of extreme heating. An actual secondary atmosphere, likely rich in carbon dioxide or carbon monoxide, probably both. Gases that had to come from somewhere, that had to be continuously replenished against the relentless stripping force of stellar radiation. This shouldn't work. Conventional planetary science said rocky planets this close to their stars couldn't maintain atmospheres. The radiation environment is too hostile. High-energy photons should give atmospheric molecules enough kinetic energy to escape the planet's gravity entirely. Atmospheric escape should strip away any gases within geologically short timescales. Yet here's Janssen, maintaining an atmosphere despite conditions that should make retention impossible. The answer lies beneath the surface. Renyu Hu from Caltech explained the likely mechanism. The atmosphere isn't primordial, it's a secondary atmosphere, constantly regenerated by outgassing from a magma ocean. Imagine the entire planetary mantle in a molten state. Temperatures and pressures high enough to keep vast quantities of rock liquid. As this magma churns and convects, dissolved gases bubble out, similar to carbon dioxide escaping from champagne. This outgassing process creates a dynamic equilibrium. Yes, the stellar wind strips atmosphere away. But volcanic emissions from the magma ocean replenish it at rates matching or exceeding the loss. It's not a stable atmosphere in the sense of Earth's, it's a constantly refreshed envelope of gas maintained by ongoing geological activity. The magma ocean model explains multiple observations simultaneously. The heat redistribution. Convection in the molten mantle transports thermal energy. The offset hotspot. Preferential outgassing on the day side creates atmospheric circulation patterns. The night side warmth. Heat from the interior prevents complete cooling even in permanent darkness. Computer simulations of Janssen's interior dynamics reveal fascinating complexity. Using surface temperature contrasts as boundary conditions, researchers modeled two-dimensional mantle convection under different climate scenarios. If the day side hosts a full magma ocean while the night side remains solid or only partially molten, large superplumes form on the day hemisphere. Hot material rises in massive upwellings. Cold material descends on the night side, though without forming strong downwelling structures. In some simulations, the superplume shifts tens of degrees toward the terminator, the boundary between day and night. This asymmetric convection could drive preferential outgassing on one hemisphere, potentially creating atmospheric composition gradients between day side and night side. Different gases on different hemispheres. Chemical stratification driven by the extreme temperature gradient. What makes this discovery genuinely revolutionary isn't just confirming the atmosphere's existence. It's demonstrating that our understanding of planetary atmospheres was too narrow. We built theories based on solar system examples: Earth, Venus, Mars, the gas giants. None of those worlds experience conditions remotely like Janssen's. We assumed extrapolation would work. The universe just proved otherwise. Diana Dragomir from the University of New Mexico, who contributed to discovering Janssen's transits during her doctoral work, emphasized the broader implications. This challenges fundamental assumptions about what's possible. If rocky planets can maintain atmospheres under such punishment, what does that mean for planetary habitability elsewhere? What does it reveal about the diversity of rocky planet evolution? The magma-ocean mechanism opens new questions. How common are lava worlds in the galaxy? Do other ultra-hot rocky planets maintain similar atmospheres? Could there be a whole class of worlds we've completely overlooked because we assumed atmospheric retention was impossible under extreme stellar radiation? Jansen gives us a window into processes that shaped Earth billions of years ago. Our planet spent its first 100 million years hot enough to maintain widespread magma oceans. Venus likely went through similar phases. Mars too. But we can't observe those ancient conditions directly, we're stuck reconstructing them from geological traces. Jansen lets us watch in real time, studying atmosphere-magma interactions as they happen rather than inferring them from billion-year-old rocks. The implications extend beyond theoretical interest in planetary science. Understanding how rocky planets retain atmospheres under extreme radiation could reshape our approach to finding habitable worlds. Current habitability models focus on moderate environments, Earth-like distances from Sun-like stars. But what if that framework is too conservative? Consider red dwarf stars. They make up roughly 70% of all stars in the galaxy. Most known exoplanets orbit red dwarfs. And red dwarfs present a problem. Their habitable zones, where liquid water could exist, sit uncomfortably close to the star. Close enough that stellar flares and radiation would seemingly strip away atmospheres. Conventional wisdom suggested rocky planets around red dwarfs couldn't maintain the atmospheric protection necessary for life. Jansen changes that calculation. If a world can hold on to an atmosphere while orbiting at 1/25 Mercury's distance from a Sun-like star, while enduring temperatures that vaporize rock, then maybe our assumptions about red dwarf habitability need revision. The mechanisms keeping Jansen's atmosphere intact might operate elsewhere. Different scales, different temperatures, but the same fundamental principle: continuous replenishment overcoming atmospheric loss. This doesn't make Jansen habitable. Nothing lives at 3,700 Kelvin. But it proves atmospheric retention works under conditions we thought impossible. And that matters when searching for life beyond Earth. The detection methods used for Jansen also demonstrate how far exoplanet characterization has advanced. Webb's instruments measured infrared light in the 4 to 12 micron range. Each 8-hour observation captured nearly half the planet's orbital period. The planet completes a full orbit in under 18 hours. That rapid orbit initially seemed like a disadvantage, less time for detailed observation. But it actually helps. Multiple orbits can be observed in a single observing session, allowing astronomers to build up signal strength and check for consistency. The secondary eclipse method Webb employed is deceptively simple in concept. Measure the combined light from star and planet. Wait until the planet passes behind the star. Measure just the star. Subtract. What remains is the planet's thermal emission. Simple in theory. Extraordinarily difficult in practice. The planet's contribution to total system brightness is minuscule. Like trying to detect a candle next to a searchlight from 41 light-years away. And not just detect it, measure its color spectrum precisely enough to identify specific molecules. Aaron Belorua from JPL pointed out the telltale signature, a dip in the spectrum between 4 and 5 microns. That's where carbon monoxide and carbon dioxide absorb infrared light. If the planet were surrounded by vaporized rock, silicon and iron compounds would create completely different absorption features. The spectrum doesn't match rock vapor. It matches volatile gases. This distinction matters because it confirms the magma-ocean model over alternatives. Some researchers have proposed that Janssen might be a bare rock world with a thin envelope of evaporated surface material. Under that scenario, the planet would essentially be sweating rock vapor. Silicon, iron, aluminum, the elements that make up planetary crust, would evaporate from the day side and circulate before condensing on the night side. That could explain some observations but struggle to account for the heat redistribution patterns and the stability of the thermal emission over time. The volatile atmosphere model fits better. Carbon dioxide or carbon monoxide released from interior outgassing creates a genuine atmosphere, not just surface evaporation. This atmosphere can transport heat through winds and circulation patterns. It can maintain relatively stable composition despite continuous loss to space because volcanic activity keeps replenishing it. And it explains why the planet's thermal emission shows less variability than expected for a bare rock surface. But questions remain. The atmosphere's exact composition remains uncertain. Is it primarily carbon dioxide? Carbon monoxide? Some mixture? Do other gases contribute significantly? Nitrogen, sulfur compounds, even water vapor from the magma ocean? Webb's current observations can't fully resolve this. Future observations with longer integration times and coverage of additional wavelengths could narrow the possibilities. The planet's internal structure also invites speculation. Standard rocky planet models don't apply straightforwardly. At the temperatures and pressures inside Janssen, rock doesn't behave like rock on Earth. Phase diagrams, the charts showing which states of matter exist under different conditions, become exotic at these extremes. Materials that normally form solid minerals might exist as superionic phases, where some atoms remain locked in crystal lattices while others flow freely like liquids. Bizarre states of matter that laboratories can barely reproduce. Some research suggests Janssen might have a carbon-rich composition rather than the silicon and oxygen-dominated chemistry of Earth-like planets. The host star, 55 Cancri A, shows elevated carbon abundance in its spectrum. If the protoplanetary disk that formed the system was similarly carbon-rich, planets might have incorporated more carbon than typical solar system bodies. Under the extreme pressures in Janssen's interior, that carbon could crystallize into diamond. This sparked the diamond planet hypothesis, the idea that Janssen's mantle might contain diamond layers hundreds of kilometers thick. It's a tantalizing possibility. The temperatures and pressures are certainly sufficient. Pure carbon at those conditions would form diamond. Whether Janssen actually contains enough carbon, and whether it's distributed in ways that allow large-scale diamond formation, remains speculative. But the chemistry isn't impossible. Density measurements provide some constraints. Janssen is roughly 8 times Earth's mass and twice Earth's radius. That gives a density of about 7 grams per cubic centimeter, higher than Earth's average density of 5.5 grams per cubic centimeter. Higher density suggests either more iron in the core or a compressed structure from the planet's gravity. Or both. It doesn't definitively prove or disprove the diamond hypothesis, but it's consistent with various compositional models. The planet's thermal variability adds another layer of mystery. Observations show the planet's brightness changes over time, not just the expected variations as it orbits, but longer-term fluctuations that suggest surface conditions aren't static. One explanation invokes massive volcanic eruptions. Picture Mount St. Helens scaled up by factors of thousands. Eruptions violent enough to inject vast dust clouds into the atmosphere, temporarily blocking thermal emission and changing the planet's apparent brightness. When the dust settles or gets swept away by atmospheric winds, brightness returns to baseline. Alternatively, the variability might come from a gas torus co-orbiting with the planet. Similar to Jupiter's Io plasma torus, a donut-shaped cloud of charged particles surrounding Jupiter in Io's orbit. Io's intense volcanic activity feeds this torus. If Janssen experiences similarly vigorous outgassing, it could create a surrounding cloud of material that periodically obscures or enhances the planet's thermal signature as viewed from Earth. Both explanations require extreme levels of geological activity. But Janssen is extreme in every measurable way, so neither scenario seems implausible. Scientists have also searched for electromagnetic interactions between Janssen and its host star. The planet orbits so close that it sits deep within the star's magnetic field. Jupiter's moon Io creates a magnetic footprint on Jupiter through electromagnetic coupling. Charged particles from Io's volcanoes interact with Jupiter's magnetic field, generating radio emissions. Similar interactions might occur between Janssen and 55 Cancri. Radio observations in 2011 looked for these signals. Nothing detected. Either the interactions don't occur at detectable strength, or the observation methods weren't sensitive enough. The null result also suggests Janssen might lack a strong intrinsic magnetic field. Earth's magnetic field is generated by convection in its liquid iron core. Janssen's interior temperatures might prevent the kind of convection needed for dynamo action. Or perhaps the magma ocean itself disrupts magnetic field generation. Without a protective magnetosphere, atmospheric loss to stellar wind should be even more severe. Yet the atmosphere persists. That persistence keeps circling back as the central puzzle. Everything about Janssen's environment should doom any atmosphere. The stellar radiation. The lack of magnetic protection. The intense gravitational forces from tidal locking. The evaporation driven by surface temperatures exceeding 3000 Kelvin. Yet there it is, carbon-bearing gases surrounding a world that shouldn't have them. The magma ocean mechanism explains how, but raises its own questions. How deep is the magma ocean? Does it cover the entire planet or just the day side? What's the composition of the molten material? Is it similar to Earth's mantle composition, or something more exotic? How efficiently does convection operate under these extreme conditions? And most intriguingly, does the night side have fundamentally different conditions that might create chemical gradients in the atmosphere? That last question touches on something particularly fascinating about tidally locked worlds. The permanent day and night hemispheres create environments so different they might as well be separate planets. One side continuously blasted by stellar radiation. The other side in eternal darkness. The atmospheric dynamics between these two faces would be extraordinary. If an atmosphere exists, and we now know it does, winds must connect the hemispheres. Heat from the day side gets transported toward the night side through atmospheric circulation. But how efficiently? That depends on wind speeds, atmospheric density, and the atmosphere's chemical makeup. Computer models of tidally locked planets suggest wind patterns unlike anything on Earth. Instead of the Coriolis-driven circulation cells we're familiar with, tidally locked worlds develop what's called a superrotating jet, a continuous high-altitude wind stream that flows eastward around the planet at tremendous speed. This jet would redistribute heat, carrying energy from the scorching day side toward the cooler night side. On Janssen, these winds might reach hundreds or even thousands of meters per second. Hypersonic winds sculpting temperature gradients that would be lethal in either direction. Standing on the day side would be like facing a blast furnace. Standing on the night side would still be hot enough to melt lead, but relatively speaking, comparatively mild. The terminator, the boundary between day and night, becomes the most interesting region. Here, conditions transition from one extreme to another. Temperature gradients drive powerful convection. Rising air from the day side meets descending air from the night side. turbulence would be constant and violent. If life were ever to exist on such a world, and it can't on Janssen, but theoretically on cooler tidally locked planets, the Terminator would be the only survivable zone. Not too hot, not too cold. Though on Janssen, even the Terminator remains far above the boiling point of water. Computer simulations of Janssen's interior reveal mantle dynamics that would reshape our understanding of planetary geology. The extreme temperature difference between hemispheres creates asymmetric convection patterns. Hot magma rises on the day side, forming massive plumes. These aren't small volcanic features, they're continent-sized upwellings of molten rock pushing toward the surface. On the night side, cooler material descends. Though cooler is relative, it's still thousands of degrees. These descending flows complete the convection cell, driving circulation through the planet's mantle. The entire planet becomes a heat engine, powered by the temperature differential its tidal locking creates. The dayside plumes can shift position. In some models, they migrate tens of degrees toward the Terminator. This movement would create varying volcanic activity across the dayside, with hotspots appearing and disappearing over time. If volcanic outgassing is concentrated in these plume regions, atmospheric composition might vary geographically. The atmosphere near the strongest plume would be richer in freshly outgassed volatiles. Regions away from active plumes would have older, more processed atmospheric chemistry. This brings up something fascinating about Janssen's atmosphere. It's not static, it's being constantly renewed. Every second, stellar radiation strips away gases on the dayside. High-energy photons and stellar wind particles collide with atmospheric molecules, giving them enough velocity to escape Janssen's gravity. The atmosphere bleeds into space continuously, yet it persists. The magma ocean replenishes what's lost. Dissolved gases in the molten rock bubble to the surface through volcanic vents. The same process that created Earth's early atmosphere 4 billion years ago continues on Janssen today. It's a dynamic equilibrium, loss balanced by supply. Remove either factor and the atmosphere would either grow indefinitely or disappear completely. This equilibrium is delicate. Small changes in volcanic activity or stellar radiation could tip the balance. If volcanic outgassing slows, atmospheric loss would gradually thin the atmosphere. If stellar activity increases during a flare, temporary atmospheric stripping could occur before volcanic replenishment catches up. The atmosphere's composition reflects this balance. Carbon dioxide and carbon monoxide dominate because they're stable enough to survive in this environment and abundant in volcanic emissions. Other gases present in smaller quantities might include sulfur dioxide, water vapor, and various rock-derived species. But the carbon-bearing molecules dominate the spectral signature web detected. Water deserves special attention. Earth's magma contains dissolved water that outgasses during eruptions. Janssen's magma ocean likely contains water too. But at dayside surface temperatures, water can't exist as liquid. It would immediately vaporize. Even on the night side, temperatures remain too high for liquid water. Any water in Janssen's atmosphere exists as superheated steam. This steam contributes to the greenhouse effect. Water vapor is an excellent absorber of infrared radiation. Even in small quantities, it would trap heat, contributing to the night side surprisingly high temperatures. The night side doesn't cool as much as bare rock calculations would suggest, partly because atmospheric circulation brings heat from the dayside, and partly because greenhouse gases trap what little heat remains. The vertical structure of Janssen's atmosphere adds another layer of complexity. Near the surface, the atmosphere is dense and hot. Pressure increases with depth into the magma ocean until there's no clear boundary between atmosphere and planet, just a gradual transition from gas to liquid to solid as you descend. Higher up, the atmosphere thins. Temperature remains high due to stellar radiation, but pressure drops. At some altitude, the atmosphere becomes thin enough that molecules can escape to space. This exosphere marks the fuzzy edge of Jansen's atmosphere, where the planet ends and space begins. Comparing Jansen to early Earth reveals profound connections. When Earth formed 4.5 billion years ago, the entire surface was molten. Impacts during planetary formation delivered enough energy to melt rock globally. The early Earth was a magma ocean world, probably tidally locked to the moon before tidal forces gradually slowed Earth's rotation. During this period, Earth's atmosphere came from volcanic outgassing. Carbon dioxide, water vapor, nitrogen, and other volcanic gases accumulated. The atmosphere was thick, hot, and utterly hostile to modern life. But it was the starting point for everything that followed. As Earth cooled, the magma ocean solidified. Water vapor condensed into oceans. Chemistry became more complex. Studying Jansen gives us a laboratory for understanding that crucial phase. We can't travel back 4 billion years, but we can observe a world currently in a state Earth once occupied. The processes happening on Jansen right now happened on Earth long ago. Magma ocean dynamics. Atmospheric outgassing. The balance between atmospheric creation and loss. Venus offers another comparison. Modern Venus has a crushing carbon dioxide atmosphere that creates a runaway greenhouse effect. Surface temperatures reach 750 Kelvin. But early Venus, like early Earth, was likely covered by magma oceans. Venus's atmosphere today is a product of billions of years of evolution, outgassing, atmospheric loss, and chemical reactions that eventually created the hellscape we observe now. Jansen represents an arrested state. Its proximity to its star prevents cooling. The magma ocean never solidifies. The planet remains locked in the early phase that Earth and Venus passed through. It's a living fossil of planetary evolution, preserved by extreme conditions that prevent further development. Mars provides a contrasting example. Mars once had a thicker atmosphere, probably sustained by volcanic activity. But Mars is small. Its interior cooled relatively quickly. Volcanic activity slowed and eventually stopped. Without replenishment, atmospheric loss gradually stripped away most of Mars's atmosphere. Solar wind and lack of a protective magnetic field accelerated the process. Jansen's size, 8 Earth masses, means its interior remains hot through radioactive decay and tidal heating. Volcanic activity will continue for billions of years. Unlike Mars, Jansen won't cool enough for atmospheric loss to win. The magma ocean persists, and with it, the atmospheric replenishment mechanism. These comparisons highlight how planetary outcomes depend on multiple factors. Size determines how long internal heat lasts. Distance from the star determines surface temperature and atmospheric loss rates. Rotation state affects heat distribution. Magnetic fields protect atmospheres from stellar wind. Chemical composition influences what gases are available for outgassing. Change any of these variables and you get a different world. Put Jansen farther from its star and it becomes a super-Earth with a solid surface and potentially habitable conditions. Shrink it to Mars size and it cools quickly, losing its atmosphere despite volcanic activity. Remove the magma ocean and the atmosphere disappears within thousands of years. Janssen occupies a precise point in this parameter space where extreme conditions create an unlikely equilibrium. The planet is large enough to stay geologically active, close enough to its star to maintain surface melting, tidally locked in a way that creates extreme hemispheric differences, and it has exactly the right composition to supply carbon-bearing gases through outgassing. Shift any factor slightly and Janssen would be something else entirely. It sits on a knife's edge between multiple possible states, maintained by the exact conditions it experiences. That precarious balance makes it scientifically invaluable. Understanding why Janssen's atmosphere survives teaches us about the boundaries of planetary habitability and the conditions necessary for atmospheres to persist. But there's something else Janssen reveals, something about the diversity of planetary outcomes in the universe. Before exoplanet discoveries began in the 1990s, our only examples were solar system worlds. We assumed other planetary systems would look similar. Rocky planets close to their stars, gas giants farther out, ice worlds at the edges. Janssen shatters that assumption. Super-Earths don't exist in our solar system. Tidally locked lava worlds weren't predicted by planetary formation models. The idea that a rocky planet could maintain an atmosphere while orbiting so close to its star contradicted theoretical expectations. Yet here it is. Real. Observed. Challenging us to expand our understanding of what planets can be. Every exoplanet discovery expands the catalog of known worlds, but some discoveries do more. They force us to reconsider fundamental assumptions about how planetary systems work. Janssen belongs to this second category. The 55 Cancri system contains multiple planets. Janssen orbits closest to the star, completing its circuit in less than 18 hours. Farther out are other worlds, Galileo, Brahe, Harriet, each occupying different orbital distances and exhibiting different characteristics. The system also includes a companion red dwarf star, 55 Cancri b, which hosts its own planets. This makes 55 Cancri one of the most populated planetary systems known outside our own. The architecture differs dramatically from our solar system. We have small rocky planets near the Sun, gas giants in the middle regions, and ice worlds at the outer edges. A clear pattern emerged from millions of years of gravitational sorting. 55 Cancri follows different rules. A super-Earth orbits where no planet should survive. Gas giants occupy unexpected positions. The whole arrangement challenges formation models based on solar system observations. Janssen's host star, 55 Cancri a, is a K-type star slightly cooler and smaller than our Sun. It's classified as Copernicus in the system's naming scheme, which honors historical astronomers and telescope pioneers. The star sits 41 light-years away in the constellation Cancer. Close enough that we can study it in detail. Far enough that we'll never visit. The star's composition matters for understanding Janssen. Spectroscopic analysis shows 55 Cancri a is relatively rich in heavy elements, particularly carbon. This chemical signature suggests the protoplanetary disk that formed the system contained higher proportions of carbon compounds than the disk that formed our solar system. That excess carbon might explain some of Janssen's unusual properties, including the diamond planet hypothesis. Several years ago, researchers proposed that Janssen might contain vast quantities of crystallized carbon in its interior. The idea emerged from density calculations and the star's carbon-rich composition. If true, Janssen's mantle could contain diamond layers hundreds of kilometers thick. Pressures and temperatures at those depths would force carbon into its densest crystalline form. The planet would literally be made partially of diamond. The hypothesis captured public imagination. Media reports dubbed it the Diamond Planet. But the reality is more complex and less certain. Recent observations suggest the magma ocean model better explains Jansen's observed properties. A diamond-rich interior remains possible but hasn't been confirmed. The planet's true composition likely lies somewhere between pure diamond and pure silicate rock, with carbon playing a significant but not dominant role. What we know for certain is that Jansen's discovery path was messy. The planet was first detected using radial velocity measurements, which tracked the star's subtle motion caused by orbiting planets. Early analysis suggested a planet with a 2.8-day orbital period. For several years, astronomers accepted this interpretation. Then Jack Wisdom reanalyzed the data in 2005. He argued the 2.8-day signal was an alias, a mathematical artifact created by combining the true orbital period with the observing schedule. He suggested the real period might be different. Other researchers published analyses supporting the 2.8-day planet. The debate continued. In 2010, Rebecca Dawson and Daniel Fabrici solved the puzzle. They demonstrated conclusively that the true orbital period was 0.7365 days, less than 18 hours. The 2.8-day signal was indeed an alias. This correction fundamentally changed our understanding of the planet. It moved Jansen from very close to extraordinarily close. The difference matters enormously when considering surface conditions and atmospheric survival. The transit discovery in 2011 confirmed the corrected orbital period. The MOST Space Telescope monitored 55 Cancri continuously for 2 weeks, capturing multiple transits exactly when Dawson and Fabrici's analysis predicted. Transit observations measure a planet's size by recording how much starlight it blocks. Combined with mass from radial velocity, this gives density. Density reveals composition. Jansen's density indicates it's rocky, not gaseous. But the exact internal structure remains debated. Is there a diamond layer? How thick is the magma ocean? Does a solid core exist beneath the molten mantle? These questions await better data. Temperature measurements added another layer of mystery. Spitzer Space Telescope observations in 2013 mapped Jansen's thermal emission using infrared light. The results showed something unexpected. The hottest point on the planet's day side was offset from the substellar point, the location directly facing the star. Instead of maximum temperature at the center of the day side, the hottest spot was shifted about 30 to 40 degrees eastward. Why? Something must be transporting heat across the surface. On a tidally locked world with no atmosphere, the hottest point should be directly under the star. The offset indicates active heat redistribution. Atmospheric winds could explain it. But at the time, scientists weren't sure Jansen had an atmosphere. Another possibility involved the planet's rotation. Tidal locking isn't always perfect. Some planets maintain slight rotational drift, which could shift the hottest spot. Or perhaps internal convection creates asymmetric heat flow that affects surface temperatures. The puzzle deepened when observations showed temporal variability. Jansen's thermal emission changed between different observing sessions. Sometimes it appeared brighter, sometimes dimmer. The variations were too large to be measurement noise. Something on or around the planet was changing. One explanation involves massive volcanic eruptions. If Jansen experiences supervolcanism, eruptions that dwarf anything on Earth, they could inject enormous dust clouds into the atmosphere. These clouds would temporarily block thermal emission, making the planet appear cooler. As the dust settled or dispersed, brightness would return to normal. Repeated eruptions would create the observed variability. Another hypothesis suggests a gas torus co-orbiting with Janssen. Picture a donut-shaped cloud of material surrounding the planet's orbit. Similar structures exist in our solar system. Jupiter's moon Io produces a plasma torus from its volcanic emissions. If Janssen continuously vents gas from its surface, some might remain in orbit around the star, creating a variable cloud that occasionally obscures the planet. These mysteries motivated the James Webb Space Telescope observations. Webb's unprecedented sensitivity and spectral resolution offered a chance to settle fundamental questions. Does Janssen have a real atmosphere? What is it made of? How does it survive? The observing campaign required meticulous planning. Webb observed the system from multiple complete orbits. Each observation lasted about 8 hours, nearly half of Janssen's orbital period. The telescope captured infrared light from the system both when the planet was visible beside the star and when it passed behind the star during secondary eclipse. Secondary eclipse occurs when the planet moves behind the star from our perspective. During eclipse, we see only starlight. Before and after eclipse, we see the combined light from both star and planet. Subtracting the eclipse measurement from the combined measurement isolates the planet's thermal emission. This technique is called secondary eclipse spectroscopy. The precision required is extraordinary. Janssen's thermal emission is thousands of times fainter than the star. Measuring it means detecting a tiny brightness change against an overwhelming background. Webb's instruments, NIRCam and MIRI, work at different infrared wavelengths. NIRCam covers 4 to 5 microns. MIRI extends from 5 to 12 microns. Together they provide a continuous spectrum showing how much light the planet emits at each wavelength. That spectrum reveals composition. Different molecules absorb and emit light at characteristic wavelengths. Carbon dioxide has a distinctive absorption feature around 4 to 5 microns. Carbon monoxide shows different patterns. Vaporized rock elements like silicon and iron would create yet another spectral signature. When the team analyzed Webb's data, they saw clear evidence for carbon-bearing gases. The spectrum showed reduced brightness between 4 and 5 microns, exactly where carbon dioxide and carbon monoxide absorb light. The signature didn't match vaporized rock. It matched volatile gases. This was the breakthrough. After years of debate, Webb provided definitive evidence that Janssen has a real atmosphere composed of actual gases, not just rock vapor. The atmosphere is likely dominated by carbon dioxide or carbon monoxide, probably both. These gases are continuously supplied by volcanic outgassing from the magma ocean below. The discovery settles one question but raises others. How thick is this atmosphere? How does its pressure compare to Earth's or Venus's? Does composition vary between dayside and nightside? Are there other gases present in smaller quantities? What about clouds or haze? Some answers will come from additional Webb observations. Others require different techniques. Future missions might directly image the planet, separating its light from the stars without relying on eclipses. Spectroscopy at higher resolution could detect trace gases and measure isotope ratios, revealing details about the atmosphere's chemistry and evolution. But the fundamental mystery is solved. Janssen has an atmosphere against all expectations. It survives in conditions that should strip it away within thousands of years. The magma ocean continuously replenishes lost gases, maintaining equilibrium between outgassing and escape. This mechanism allows the atmosphere to persist for billions of years despite hostile conditions. The implications extend far beyond one planet. If atmospheres can survive on worlds as extreme as Janssen, where else might they persist? What about planets slightly farther from their stars, where conditions are less hostile? Could super-Earths in intermediate environments maintain thick atmospheres for geological timescales? What does this mean for habitability across the galaxy? The discovery opens doors to understanding atmospheric evolution across the galaxy. Rocky planets exist in every configuration imaginable. Some orbit close like Janssen. Others circle at comfortable distances. Many fall somewhere between. Each environment tests different survival mechanisms. Janssen proves that extreme proximity doesn't automatically mean atmospheric death. The magma-ocean mechanism works. It maintains equilibrium between loss and replenishment. But does this mechanism scale? Could slightly cooler worlds with less volcanic activity still maintain atmospheres through similar processes? What about planets around different types of stars? Red dwarfs are smaller and cooler than our Sun, but they emit powerful stellar flares that could strip atmospheres more efficiently than steady radiation. Do magma-ocean planets around red dwarfs survive or succumb? These questions matter because red dwarfs make up roughly 70% of all stars in the galaxy. If their planets can't maintain atmospheres, that dramatically narrows the search for habitable worlds. Conversely, if Janssen's mechanism works around red dwarfs too, billions of additional worlds might retain atmospheres despite hostile conditions. The connection to Earth's past runs deeper than surface similarities. 4 billion years ago, our planet was a hellscape. Continuous asteroid bombardment kept the surface molten. The atmosphere was thick with carbon dioxide, water vapor, and other volcanic gases. No oxygen existed. No ozone layer protected the surface from radiation. Life had not yet emerged, or if it had, it clung to the most extreme refuges imaginable. That early Earth resembled Janssen in many ways. Not in temperature, Earth was cooler. But in the fundamental process of atmosphere formation through volcanic outgassing from a magma-covered world. Studying Janssen lets us observe this process happening now, 41 light-years away, rather than trying to reconstruct it from geological clues billions of years old. The insights apply to Venus too. Our sister planet may have started with oceans and a temperate climate. Runaway greenhouse warming turned it into an inferno with surface temperatures exceeding 860 degrees Fahrenheit. Venus today has a crushing carbon dioxide atmosphere 90 times thicker than Earth's. That atmosphere likely formed through volcanic outgassing, similar to the mechanism sustaining Janssen. Understanding how magma-ocean worlds generate and maintain atmospheres helps explain Venus's transformation. It might even reveal whether Venus could have remained habitable if certain conditions had been different. Mars presents a contrasting case. The red planet once had a thicker atmosphere and liquid water on its surface. Rivers carved channels. Lakes filled impact craters. The atmosphere was dense enough to support a water cycle. Then Mars lost most of its atmosphere to space. Without a strong magnetic field to deflect the solar wind, atmospheric gases were gradually stripped away over hundreds of millions of years. Today Mars has only a thin carbon dioxide atmosphere, about 1% the density of Earth's. Janssen's survival mechanism, continuous volcanic replenishment, is precisely what Mars lacked. Once Martian volcanism declined, the atmosphere couldn't be replenished fast enough to compensate for losses. The planet dried out and froze. Comparing these worlds reveals the delicate balance required for atmospheric persistence. Too little volcanic activity means gradual loss. Too much stellar radiation accelerates escape. A magnetic field helps but isn't always necessary if replenishment rates are high enough. Janssen demonstrates that extreme volcanism can compensate for extreme radiation, maintaining atmosphere despite lacking magnetic protection. The search for habitable worlds depends on understanding these boundaries. The habitable zone around a star is traditionally defined as the region where liquid water can exist on a planet's surface. Too close and water boils away. Too far and it freezes. But habitability requires more than temperature. It demands atmospheric stability over geological timescales. A planet in the habitable zone means nothing if it can't hold on to its atmosphere. Janssen teaches us that atmosphere retention is complex. It's not just about distance from the star or planetary mass. Volcanic activity, stellar radiation, magnetic fields, and internal heat all interact. Some planets in the habitable zone might lose their atmospheres. Others outside it might keep theirs through vigorous outgassing. The traditional habitable zone concept may be too simplistic. We need a more nuanced understanding that accounts for atmospheric dynamics, not just surface temperature. Future observations will refine our knowledge of Janssen's atmosphere. Webb can observe the planet again, measuring how its spectrum changes over time. Variability would indicate weather patterns, volcanic events, or atmospheric circulation. Long-term monitoring could reveal seasonal changes if the planet's orbit is slightly elliptical, though current evidence suggests it's nearly circular. Other instruments could contribute different perspectives. Radio telescopes might detect emissions from atmospheric chemistry. Optical telescopes could measure reflected starlight, revealing cloud properties or atmospheric hazes. Each observation adds another piece to the puzzle. The goal is building a complete atmospheric model: temperature structure, pressure profile, chemical composition, circulation patterns. That model would be the first comprehensive picture of a rocky exoplanet atmosphere. Beyond Janssen, dozens of other rocky exoplanets await similar scrutiny. Many orbit closer to their stars than Mercury does to our Sun. Some are larger than Earth but smaller than Neptune, occupying a size range with no solar system equivalent. These super-Earths and mini-Neptunes are common in the galaxy, yet we understand them poorly because we lack local examples. Do they have atmospheres? What are those atmospheres made of? How thick are they? Can they support liquid water despite high temperatures? Janssen provides a template for answering these questions. The techniques developed to study it, secondary eclipse spectroscopy, thermal phase curves, long-term monitoring, apply to other worlds. Each new observation expands our catalog of atmospheric types. Rocky planets with hydrogen atmospheres. Worlds with water vapor envelopes. Planets surrounded by carbon monoxide. The diversity is likely enormous, limited only by the laws of chemistry and physics. The technology enabling these discoveries barely existed a decade ago. Webb launched in late 2021. Its predecessors, Hubble, Spitzer, Kepler, laid groundwork but lacked the sensitivity and spectral resolution for rocky planet atmospheres. Webb's mirror is nearly 3 times wider than Hubble's, collecting much more light. Its infrared instruments operate at wavelengths ideal for thermal emission spectroscopy. And its position at the second Lagrange point, 1 million miles from Earth, provides a stable environment free from atmospheric interference. These advantages combine to make observations like Janssen's possible. Without Webb, we'd still be debating whether rocky exoplanet atmospheres could be detected at all. Now we know they can. The question shifts from whether to how many and what types. Next-generation instruments will push further. Ground-based telescopes with adaptive optic systems that compensate for atmospheric distortion are reaching unprecedented precision. Space missions under development target rocky planets specifically. Some will use star shades, giant structures flying separately from telescopes to block starlight, making planets visible. Others will employ coronagraphs, internal masks that achieve similar blocking. These techniques enable direct imaging rather than relying on transits or eclipses. Direct imaging reveals more detail, including atmospheric composition, cloud patterns, and surface features if resolution permits. The ultimate goal is finding another Earth. A rocky planet in a habitable zone with an atmosphere containing oxygen, water vapor, and other biosignatures. Life as we know it requires liquid water and produces oxygen through photosynthesis. Detecting both in an exoplanet atmosphere would strongly suggest biology. Janssen isn't that world. It's too hot, too hostile, too extreme. But every planet we study teaches us something about planetary diversity and atmospheric resilience. Janssen proves that atmospheres can survive in conditions once thought impossible. That expands the parameter space where we might find habitable worlds. If atmospheres persist around planets as extreme as Janssen, they might exist in many environments we haven't fully considered. The galaxy may be richer in atmospheric diversity than we imagined, with implications for where life might arise and endure. Standing back, the Janssen story reflects humanity's expanding vision. 40 years ago, we didn't know whether planets existed around other stars. The first exoplanet discovery came in 1992, orbiting a pulsar. The first around a sun-like star came in 1995. Now we know thousands of exoplanets, with more discovered every year. We've progressed from merely finding planets to characterizing their masses, sizes, orbits, and now atmospheres. Each advance reveals the universe in greater detail. Janssen represents the cutting edge of this progression, a world so alien yet so important for understanding how planets work. Its magma oceans, carbon-rich atmosphere, and extreme temperatures challenge our assumptions and expand our knowledge. In 41 years, light from Janssen reaches Earth, carrying information about a world that shouldn't exist by old rules but does by new understanding. That light, captured by our most sophisticated instruments, tells a story of resilience, complexity, and the endless capacity of nature to surprise us. The Janssen discovery arrives at a turning point in our understanding of what planets can be. For centuries, we built theories from 8 local examples. Mercury through Neptune. A handful of moons. 1 asteroid belt. Limited data breeding limited imagination. Then exoplanets shattered those constraints, revealing worlds that defy every category we'd constructed. Hot Jupiters orbiting closer than Mercury. Super-Earths with no solar system equivalent. Planets around binary stars, around pulsars, in configurations our models never predicted. Janssen sits at the extreme end of this spectrum. A world where rock boils. Where atmospheres persist through mechanisms we're only beginning to grasp. Where every measurement contradicts what textbooks said was possible. It's not just another data point. It's a fundamental challenge to planetary science orthodoxy. The implications ripple outward in unexpected directions. Consider the habitable zone concept. We've spent decades refining estimates of where liquid water can exist around different stellar types. But if atmospheric retention depends on volcanic vigor as much as stellar distance, those calculations need revision. A planet outside the habitable zone might maintain temperate surface conditions through internal heat and thick atmosphere. One inside might lose its air despite comfortable temperatures. Janssen proves the old boundaries were too rigid. Atmospheres survive where theory said they couldn't. Magma oceans sustain themselves for billions of years through tidal heating. Carbon dioxide and carbon monoxide circulate in environments hot enough to vaporize iron. The universe operates by different rules than we assumed, and each discovery reveals another layer of complexity we'd missed. The technological achievement deserves recognition too. Webb's instruments detected molecular absorption features in thermal emission from a rocky planet smaller than Neptune, orbiting a sun-like star 41 light-years away. The planet's contribution to total system brightness is infinitesimal. Yet Webb teased apart that faint signal, measured it across multiple wavelengths, and identified specific chemicals in an alien atmosphere. 20 years ago, this would have seemed impossible. 10 years ago, it was theoretical. Now it's routine. That progress accelerates. Webb will observe more rocky exoplanets, building a catalog of atmospheric types. Ground telescopes with 30-meter mirrors are under construction, capable of even finer measurements. Space missions in planning stages will directly image Earth-sized worlds around nearby stars. Within the next decade or two, we'll have spectroscopic data from dozens of rocky planets across a range of environments. Janssen is the first clear detection, but it won't be the last. Each atmosphere tells a story about planetary evolution. How did this world form? What was its early environment? Has its atmosphere changed over time? Is volcanic activity increasing or declining? These questions connect to the broader narrative of how planetary systems develop from protoplanetary disks into mature configurations. Janssen's carbon-rich atmosphere might reflect the unusual composition of its parent disk. Other planets will show different chemistries, revealing different formation histories. The connection to Earth's past grows stronger as we learn more. Our planet spent hundreds of millions of years as a magma ocean world. That phase determined what atmosphere we started with, which influenced how the surface eventually solidified and cooled. Water vapor condensing into oceans. Carbon dioxide dissolving into seawater. Nitrogen accumulating because it's chemically inert. These processes set the stage for everything that followed, including the emergence of life. We can't observe Earth 4 billion years ago. Those rocks are gone, subducted or eroded beyond recognition. But we can observe Janssen now, watching processes that mirror Earth's infancy. The magma ocean convection. The volcanic outgassing. The atmospheric chemistry under extreme conditions. It's a living laboratory for planetary formation, preserved by circumstances that prevent it from moving to the next evolutionary stage. Venus offers another parallel. The runaway greenhouse effect that created its hellish surface may have started from conditions similar to early Earth. Small differences in initial water content, volcanic activity, or atmospheric composition could determine whether a planet becomes habitable Earth or scorched Venus. Understanding how atmospheres form and persist on magma ocean worlds helps identify which factors matter most. That knowledge applies to every rocky planet in every system. Mars shows the opposite extreme. A world that lost its atmosphere because volcanic replenishment couldn't match escape rates. Janssen demonstrates that vigorous outgassing can maintain atmosphere despite extreme radiation. Mars lacked that vigor. Its smaller size meant faster interior cooling. Volcanism declined. The atmosphere thinned. Today we see the end result, a frozen desert with only wisps of air remaining. These comparisons reveal that atmospheric evolution isn't deterministic. Similar planets can follow divergent paths depending on subtle variations in initial conditions and subsequent history. Some retain thick atmospheres for billions of years. Others lose them within hundreds of millions. The galaxy likely contains examples of every intermediate state, each frozen at a different point in the progression from formation to final configuration. Finding habitable worlds requires understanding these pathways. We need to identify which planets can maintain atmospheres long enough for life to emerge and evolve. That means looking beyond simple temperature calculations. Volcanic activity matters. Stellar radiation matters. Planetary mass and composition matter. Magnetic fields help but aren't always necessary. The interactions between these factors create outcomes we're only beginning to map. Janssen expands that map into territory we previously marked as impossible. Atmospheres in extreme radiation environments. Magma ocean worlds maintaining volatile envelopes through continuous outgassing. Carbon-bearing gases surviving at temperatures that vaporize rock. Each observation adds nuance to our understanding of what's possible, pushing the boundaries of known atmospheric physics. The search continues with renewed purpose. Thousands of exoplanets await detailed characterization. Many are rocky. Many orbit in or near habitable zones. Some may harbor atmospheres with biosignatures, oxygen, methane, combinations of gases that suggest biological activity. Finding those signatures requires the techniques pioneered on worlds like Janssen. Secondary eclipse spectroscopy. Thermal phase curves. Long-term monitoring for variability. Future discoveries will surprise us. They always do. Each planet studied reveals unexpected features, challenges assumptions, forces theoretical revisions. Janssen challenged the assumption that rocky planets this close to their stars can't have atmospheres. What will the next discovery challenge? Perhaps we'll find atmospheric oxygen on a lifeless world, produced through non-biological chemistry. Or detect complex organic molecules in places we thought too extreme for chemistry to occur. Or discover that magnetic fields play different roles than we believed. The universe doesn't care what we think is possible. It operates according to physical laws, and those laws permit configurations we haven't imagined yet. Our job is observation, measurement, analysis. Build instruments sensitive enough to detect faint signals. Develop techniques clever enough to extract information from noise. Construct models flexible enough to accommodate new data without breaking. Janssen succeeds because it exists in a narrow parameter space where multiple extreme conditions align. Large enough to stay geologically active. Close enough to maintain surface melting. Tidally locked to create hemispheric extremes. Compositionally suited to supply carbon gases through outgassing. Change any variable and you get a different outcome. But in this exact configuration, the result is a magma ocean world with a carbon-rich atmosphere surviving against impossible odds. That survival teaches humility. Our theories predicted atmospheric loss would dominate. They were wrong. Nature found a mechanism we'd underestimated: continuous volcanic replenishment maintaining equilibrium with escape processes. The mechanism was there all along, operating on early Earth, on early Venus, on countless worlds across the galaxy. We just needed precise enough observations to confirm it. The James Webb Space Telescope provided those observations. Its infrared capabilities, its spectral resolution, its exquisite sensitivity combined to detect molecular absorption features in a rocky exoplanet atmosphere. The first clear detection of its kind. A milestone in exoplanet science. Proof that we can characterize rocky planet atmospheres despite their faintness and their distance. More milestones await. Direct imaging of Earth-sized worlds. Detection of water vapor on temperate planets. Identification of biosignatures in exoplanet atmospheres. Each achievement builds on previous ones, using techniques refined through observations like Janssen. The progression continues, limited mainly by technology and funding. As instruments improve, so does our ability to study ever more challenging targets. 41 light-years separates us from Janssen. Light traveling at 186,000 miles per second takes 41 years to cross that gulf. The photons Webb detected left Janssen in 1983, carrying information encoded in their wavelengths about a world that defies expectations. Those photons journeyed through interstellar space, arrived at our solar system, and entered Webb's optics to be recorded and analyzed. The information they carried changed our understanding of planetary atmospheres. Not through dramatic revelation, but through precise measurement of subtle spectral features. Science advances through exactly this process. Careful observation. Rigorous analysis. Gradual accumulation of evidence. Occasional surprises that force theoretical revisions. Janssen delivered one of those surprises. A rocky planet with an atmosphere in conditions that shouldn't permit one. The discovery proves that atmospheric science still has fundamental lessons to learn. Our models are incomplete. Our assumptions sometimes wrong. The universe more diverse than our limited sample suggested. That diversity is what makes exoplanet science compelling. Every world is an experiment in planetary physics. Different initial conditions. Different evolutionary paths. Different outcomes. Some produce Earths, temperate, wet, potentially habitable. Others become Venuses, scorched, hostile, shrouded in crushing atmospheres. Still others turn into Mars analogs, cold, dry, stripped of most air. And some become Janssens, extreme, unexpected, challenging everything we thought we knew. The galaxy contains hundreds of billions of stars. Most have planets. Rocky worlds number in the billions. Each one represents a unique combination of formation history, composition, stellar environment, and evolutionary trajectory. We've characterized perhaps a few dozen in detail. The sample is tiny. The lessons preliminary. But each observation adds to our knowledge, building toward comprehensive understanding of how planets work. Janssen's contribution to that understanding is clear. Atmospheres can survive extreme radiation through continuous volcanic replenishment. Magma ocean worlds maintain carbon-rich envelopes despite surface temperatures exceeding 6,000 degrees Fahrenheit. Tidally locked planets redistribute heat through atmospheric circulation even when that atmosphere shouldn't exist according to old theory. These aren't minor details, they're fundamental insights about planetary atmospheric physics. The knowledge applies beyond Janssen. Every ultra-hot rocky planet. Every tidally locked world. Every planet with active volcanism and strong stellar radiation. The mechanisms we've identified operate wherever similar conditions exist. That means potentially thousands of worlds across the galaxy, each maintaining atmospheres through processes we're only now beginning to understand. Looking forward, the questions multiply faster than answers. How common are magma ocean planets? Do they exist around different stellar types? Can slightly cooler versions maintain atmospheres through similar mechanisms? What about planets with different compositions, more water, less carbon, varying amounts of metals? How do magnetic fields influence atmospheric retention when volcanic activity is vigorous? Do some planets transition from magma ocean states to solid surfaces, and if so, How does that affect their atmospheres? Each question requires observations. More web time. Future missions. Continued monitoring of known worlds and characterization of newly discovered ones. The work spans decades, involves hundreds of scientists, demands billions in funding. But the payoff is understanding our place in the universe. Learning how common Earth-like worlds are. Discovering whether life exists elsewhere. Finding out if our planet's history is typical or exceptional. Jansen moves us one step closer to those answers. Not through being Earth-like, it's about as far from Earth as a rocky planet can get. But through demonstrating that planets operate under a wider range of conditions than we believed possible. If atmospheres survive at Jansen's orbital distance, they might persist in many environments we'd written off as too hostile. That expands the search space for habitable worlds and increases the odds that we'll eventually find one. The universe is vast. The number of planets staggering. Most will remain forever beyond our ability to study in detail. But the ones we can observe teach us principles that apply to all the others. Physical laws operate the same everywhere. The chemistry of planetary formation follows universal rules. Atmospheric physics doesn't change based on location. So every planet we characterize tells us something about countless others we'll never see. Jansen tells us that nature is more resourceful than our models predicted. That equilibrium can exist between opposing processes even under extreme conditions. That volcanic vigor can maintain atmospheres despite powerful escape mechanisms. These lessons apply to exoplanets we'll discover next year, next decade, next century. They become part of the framework we use to understand all rocky worlds. 41 light-years away, Jansen continues its 18-hour orbit. The magma ocean churns. Volcanic gases bubble to the surface. Stellar radiation strips away atmosphere as fast as outgassing replenishes it. The process has continued for billions of years and will continue for billions more. We've observed it for a few years at most. But those observations revealed something we'd never have predicted from theory alone. A world that shouldn't exist by old rules but does according to new understanding. That's how science progresses, one impossible planet at a time.
A world exists that orbits no star. Its surface, colder than anything you can imagine, receives no warmth from a distant sun. Deep beneath frozen layers measured in kilometers, residual heat from a violent birth billions of years ago might sustain something we'd hesitate to call life. This planet has been traveling through the void for longer than Earth has supported complex organisms, and recently, astronomers detected one of these wanderers closer than we've ever confirmed before. Rogue planets represent one of astronomy's most unsettling discoveries. These aren't comets or asteroids. They're full-scale worlds, some larger than Jupiter, drifting through interstellar darkness without gravitational allegiance to any star. Until recently, we assumed planets required stars. The very definition seemed to demand it. Then observations started revealing something unexpected. The galaxy is absolutely crowded with these orphaned worlds. The numbers are staggering in ways that fundamentally challenge our understanding of planetary demographics. The Milky Way might contain 8 trillion rogue planets. Let that settle for a moment. 8 trillion. Our galaxy has roughly 400 billion stars, which already seems incomprehensible. But for every star burning in the night sky, there could be 20 planets wandering alone through the darkness between stellar systems. On January 2, 2026, an international team announced they discovered a new rogue planet about 9,800 light-years from Earth. What makes this detection revolutionary isn't just that they found another wanderer. For the first time, astronomers obtained a direct mass measurement, not a statistical estimate based on probability distributions. They know for certain this object has a mass similar to Saturn. The discovery came through a microlensing event with the rather unglamorous designation KMT 2024 BLG 0792/OGLE 2024 BLG 0516. Multiple telescopes on the ground and in space watched simultaneously as this dark world passed between Earth and a distant background star, its gravity bending light in ways that revealed its presence and properties with unprecedented precision. But here's what keeps astronomers awake. We're only detecting the largest ones, and even then, only when they happen to pass directly between us and another light source. The smaller rocky worlds, the planets that might resemble Earth or Mars, remain completely invisible with current technology. They emit almost no infrared radiation, reflect no starlight, and only reveal themselves through gravitational effects that require extraordinary luck to observe. Think about the implications. Every planetary system that forms goes through a violent settling period. Computer simulations tracking the formation of 100 different solar systems, each containing 3 to 10 planets orbiting a sun-like star, revealed something disturbing when researchers let the equations run for 1 billion simulated years. For every stable system like ours that emerges, at least one gas giant gets ejected into interstellar space. And 5 to 10 smaller, rocky worlds get flung out alongside it. Our own solar system might have participated in this cosmic exile program. Some researchers theorize we once had a 5th giant planet alongside Jupiter, Saturn, Uranus, and Neptune. During a chaotic period called late instability, gravitational interactions between these massive worlds became unstable. The unfortunate 5th planet got accelerated to escape velocity and vanished into the dark. With the survivors, the planets that happened to find stable orbits after the violence settled. The ejection mechanisms are diverse and brutal. In systems with 2 stars orbiting each other, planets can get caught in gravitational tug-of-war scenarios that eventually tear them free. When stars pass unusually close to each other in wide binary systems, the orbital dynamics can shift so dramatically that planets get stolen or ejected entirely. But the most common mechanism is simpler and more direct: planet-planet scattering. Picture 2 planets whose orbits bring them too close. The gravitational interaction becomes chaotic. One planet, usually the less massive of the 2, gains enormous orbital energy in a single encounter. Within a few orbits, it's moving fast enough to break free from the star's gravity entirely. The other planet settles into a more stable orbit, its trajectory only slightly altered. One world continues its predictable life. The other begins a journey through darkness that might last billions of years. These ejected planets retain velocity signatures that tell their origin stories. Astronomers measure something called velocity dispersion, essentially how fast these objects move relative to surrounding stars. Rogue planets kicked out through planet-planet scattering travel at 8 to 16 kilometers per second. Those ejected through binary star interactions move 3 times faster. These velocities serve as fingerprints, revealing the violence of their exile long after the event occurred. Not all rogue planets started their existence orbiting stars. Some formed alone in interstellar space, condensing from clouds of gas and dust through processes more similar to star formation than traditional planet formation. These objects collapse under their own gravity, accreting material directly from surrounding nebulae, but never gathering enough mass to ignite fusion and become true stars. The International Astronomical Union proposed calling them sub-brown dwarfs to distinguish them from planets that formed in protoplanetary disks and were subsequently ejected. The distinction matters because it reveals fundamentally different formation pathways. An ejected planet carries with it the chemical signature of the stellar system where it formed. Its composition reflects the specific mix of elements present in that particular protoplanetary disk. A planet that formed alone in interstellar space would have a completely different chemical profile, one that reflects the average composition of the interstellar medium rather than a specific stellar environment. In 2025, astronomers observed something that challenged previous assumptions about these isolated worlds. They found a rogue planet designated CHA 1107 to 7626, located about 620 light-years away in the constellation Chameleon. This object has a mass 5 to 10 times that of Jupiter. But what stunned researchers was watching it actively accrete material from a surrounding disk of gas and dust at a rate of 6 billion tons per second. This represents the strongest accretion episode ever recorded for a planetary mass object. The discovery revealed that some rogue planets can exhibit star-like behavior during formation, with magnetic activity driving material infall in ways previously thought exclusive to stellar evolution. The planet is still forming, still growing, still pulling in matter from its environment despite having no parent star to organize that material into a traditional protoplanetary disk. Detecting these objects requires monitoring millions of stars continuously, watching for the brief moments when a rogue planet's gravity bends light from a background source. The technique, called gravitational microlensing, works because even planets have enough mass to warp spacetime according to Einstein's general relativity. When alignment occurs, the background star brightens temporarily, sometimes for just a few hours. The challenge is enormous. Only one star in 100,000 gets microlensed at any given time. To find planets, you need to observe millions of stars on timescales of several minutes, checking at least several times per hour. Survey teams aim their telescopes towards Sagittarius, which lies in the direction of our galaxy's dense center where about 400 million detectable stars cluster together. Even then, hundreds of events per year toward the galactic bulge still represent a tiny fraction of the actual population. The upcoming Nancy Grace Roman Space Telescope, scheduled to launch by May 2027, should revolutionize this field entirely. Scientists expect it will discover at least 400 more rogue planets, potentially several thousand. The telescope can image the entire sky 1,000 times faster than Hubble, using both microlensing and direct infrared imaging to find worlds potentially as small as Mars. But here's the question that shifts this from purely academic interest to something more immediate. What happens if one of these wanderers enters our solar system? The odds are extraordinarily low. Astronomers calculate roughly 1 in 1 trillion chance within the next 1,000 years. Space is vast enough that even with trillions of rogue planets wandering the Milky Way, the distances between objects make close encounters vanishingly rare. Yet the theoretical consequences are worth understanding because they reveal just how delicately balanced our solar system actually is. If a rogue planet approaching 13 times Jupiter's mass crossed into our solar system, the gravitational disturbance would begin long before any visible approach. Our planets orbit the Sun in relatively narrow bands we call the habitable zone, regions where conditions remain stable enough for liquid water and predictable seasons. Earth sits comfortably within this zone, neither too close to freeze nor too near to burn. But that comfortable position depends entirely on gravitational stability maintained over billions of years. The intruder would warp that stability immediately. Its gravitational field would reach outward like invisible fingers, tugging on objects billions of kilometers away. Neptune would feel the pull first, its orbit shifting microscopically at first, then more dramatically as the rogue planet advanced inward. Uranus would follow, then Saturn, then Jupiter. Each giant planet's orbit would stretch, becoming more elliptical, less circular. The perfectly synchronized dance that has kept our solar system stable since its formation would begin breaking down. Earth's orbit would change too. Not necessarily in ways that eject us from the habitable zone entirely, but in ways that fundamentally alter how we experience seasons and climate. Picture our planet's orbit stretching into an elongated ellipse. For part of the year, we'd swing closer to the sun than we've been in 4 billion years. Temperatures would spike dramatically during these brief summers, potentially reaching levels that make current heat waves seem mild. Ocean surfaces would heat rapidly. Ice caps would melt at accelerated rates. Weather patterns would destabilize completely. Then the orbit would carry us outward again. These winters would last far longer than the summers, plunging Earth into extended cold periods that could span years or decades depending on the severity of orbital disruption. Agriculture would collapse almost immediately. Crops require specific growing seasons, predictable temperatures, stable water cycles. When summer lasts only a fraction of its normal duration, and winter extends indefinitely, food production becomes impossible at scale. Within a single orbital period, humanity would face resource shortages unlike anything in recorded history. But orbital disruption represents just one category of threat. The rogue planet's passage would also destabilize the asteroid belt between Mars and Jupiter. This region contains millions of rocky bodies, most following stable orbits that keep them safely distant from inner planets. Gravitational perturbation from a massive intruder would send countless asteroids careening in unpredictable directions. Some would fall toward the sun. Others would be flung outward into deep space. And some would find trajectories that intersect with Earth's orbit. The bombardment wouldn't happen all at once. Instead, we'd face an extended period of elevated impact risk lasting potentially thousands of years as the disturbed asteroid population gradually restabilized. Each impact would carry consequences proportional to the impactor's size. Small asteroids would burn up in the atmosphere or create localized damage. Larger ones would generate regional devastation. And the largest could trigger mass extinction events comparable to the impact that ended the dinosaurs 66 million years ago. The outer solar system would experience even more dramatic effects. The Kuiper belt and Oort cloud contain trillions of icy bodies, most in stable distant orbits that keep them far from the inner planets. These regions function as cosmic deep freezers, preserving pristine samples of material from the solar system's formation. When a rogue planet passes through, it doesn't just disturb a few objects. It reorganizes entire populations, sending waves of comets toward the inner solar system. Historical records show that even minor perturbations in the Oort cloud can increase comet activity measurably. A full-scale disruption would unleash a comet storm lasting millions of years. The night sky would fill with visible comets, dozens at a time, their tails stretching across the heavens. Beautiful from a distance. Terrifying when you realize each represents a potential impact threat moving at tens of kilometers per second. Yet direct collision with the rogue planet itself would dwarf all these other scenarios. The kinetic energy involved defies comprehension. A Jupiter-mass object moving at typical interstellar velocities, somewhere between 50 and 200 kilometers per second, carries momentum that makes terrestrial disasters seem insignificant by comparison. If Earth happened to lie directly in its path, the collision wouldn't just destroy our planet. It would vaporize it completely. The impact would release more energy than all nuclear weapons ever built, multiplied by billions. Both worlds would transform instantly into expanding clouds of superheated plasma, temperatures reaching millions of degrees, hot enough to strip electrons from atoms. The debris cloud would glow brighter than the sun briefly before beginning its long cooling process. Over millions of years, this material might eventually coalesce into new bodies. But nothing resembling Earth would remain. No fossils. No geological record. No evidence that our planet ever existed beyond chemical signatures in the debris field. The probability of such a direct collision remains vanishingly small. Space is vast. Even within our solar system, the distances between objects dwarf the sizes of the objects themselves. A rogue planet could pass through the solar system and miss every planet purely by chance, simply because empty space dominates the architecture. The odds of threading the needle to hit Earth specifically are so low that astronomers calculate perhaps one such event per trillion years. But near misses carry their own dangers. The rogue planet doesn't need to hit Earth to devastate it. A close approach, even one that misses by millions of kilometers, would generate tidal forces powerful enough to stress our planet's interior. Imagine Earth's entire mass being pulled unevenly, the near side attracted more strongly than the far side. This differential force, called a tidal gradient, can trigger geological activity on unprecedented scales. Volcanic eruptions would increase in frequency and intensity as the planet's mantle convects more vigorously under tidal heating. Earthquake activity would spike globally. Tectonic plates would shift more rapidly than normal, potentially triggering mega-earthquakes that make the most powerful historical quakes seem minor. Coastlines would experience massive tsunamis as ocean water responds to the changing gravitational field. The planet wouldn't tear apart, but it would experience geological violence concentrated into a brief period rather than spread across millions of years. Then there's the Moon. Our natural satellite orbits at a distance where Earth's gravity dominates, but that dominance isn't absolute. A massive object passing nearby could perturb the Moon's orbit significantly, potentially even capturing it entirely if the geometry aligned precisely. Losing the Moon would alter Earth's axial tilt over time, destabilizing climate patterns that depend on that tilt remaining relatively constant. Tides would weaken dramatically, affecting ocean circulation patterns that regulate global temperature distribution. Research into these scenarios isn't purely academic. Scientists study them to understand the limits of planetary system stability, the frequency of catastrophic events over cosmic timescales, and the resilience of life under extreme conditions. The models they build require simulating gravitational interactions between multiple massive bodies over millions of years, tracking how small perturbations compound into large-scale reorganization. These simulations reveal something crucial about our solar system's architecture. The current configuration isn't random. It represents the stable endpoint of billions of years of gravitational evolution. Early in the solar system's history, planetary orbits were far less regular. Planets migrated inward and outward. Some collided. Others were ejected entirely. The NICE model, named after the French city where researchers developed it, suggests that our gas giants once occupied completely different orbital positions before gravitational interactions shuffled them into their current locations. That early chaos may have ejected a fifth giant planet entirely. Computer models show that systems starting with 5 gas giants tend to eject one, leaving 4 in stable orbits that match what we observe today. If true, our solar system has already experienced the kind of gravitational violence that creates rogue planets. We may have contributed to the population of wanderers drifting through the galaxy. Somewhere out there, a Jupiter-sized world might be traveling alone through the darkness, carrying with it chemical signatures that would identify it as having formed in our solar system billions of years ago. Understanding rogue planet encounters also helps astronomers estimate how common such events are throughout the galaxy. If systems typically eject multiple planets during formation, and if billions of systems have formed over the galaxy's lifetime, then trillions of rogue planets represent a natural consequence of planet formation itself. The process is violent and chaotic, with only a fraction of formed planets remaining gravitationally bound to their parent stars. That chaos produced something else beyond ejected planets. It created a testing ground for understanding how gravitational interactions scale across different masses and distances. When astronomers model rogue planet encounters, they're not just calculating abstract trajectories. They're mapping the boundaries between stability and catastrophe, between systems that endure and systems that disintegrate. The math reveals patterns that hold true regardless of scale, from moons orbiting planets to planets orbiting stars to stars orbiting galactic centers. These patterns explain why certain orbital configurations persist while others collapse rapidly. Resonances matter enormously. When two orbits have periods that form simple ratios, 3:2 or 2:1, the bodies repeatedly align at the same points in their orbits. These alignments accumulate gravitational nudges that either stabilize the system or destabilize it, depending on the specific geometry. Jupiter and Saturn demonstrate this principle. Their orbital periods nearly form a 5:2 ratio, close enough to create significant long-term effects but far enough from exact resonance to avoid catastrophic instability. A rogue planet passing through disrupts these delicate balances. Even a relatively distant encounter can perturb orbital periods enough to shift a stable resonance into an unstable one. The effect cascades. Jupiter's orbit changes slightly. That alters its gravitational influence on Saturn. Saturn's shifted orbit affects Uranus. The inner planets feel the effects later but inevitably. Over thousands or millions of years, orbits that appeared stable reveal themselves to be metastable, waiting for a trigger to push them into new configurations. This vulnerability explains why finding rogue planets matters beyond academic curiosity. Each discovery provides data points for estimating encounter frequencies. Astronomers can calculate how many rogue planets exist within certain distance ranges, how fast they typically travel, and therefore how often close approaches occur statistically. The numbers suggest that over the lifetime of a typical planetary system, at least one moderately close encounter with a rogue planet is more likely than not. But what constitutes close in cosmic terms? A rogue planet passing within 1 light-year would have minimal effect. At that distance, even a massive interloper exerts negligible gravitational influence over the brief time it takes to pass. Move that encounter to within 100 astronomical units, roughly 3 times Neptune's orbital distance, and the story changes. Now the rogue planet spends years or decades within the outer solar system's gravitational sphere of influence, plenty of time for orbital perturbations to accumulate. The difference between a harmless distant passage and a system-disrupting encounter comes down to velocity and trajectory. A fast-moving rogue planet on a perpendicular trajectory might slice through the outer solar system in just a few years, limiting the time available for gravitational interactions. A slower object on an aligned trajectory could remain gravitationally engaged for decades or centuries, maximizing the cumulative perturbations. The geometry matters as much as the mass. Detecting such an encounter in advance presents technological challenges that current capabilities barely address. Rogue planets emit almost no light. They don't reflect starlight because they're not near stars. Their thermal emission peaks in infrared wavelengths, but even then, a Jupiter-mass object several hundred astronomical units away would appear incredibly faint. Current surveys might detect it a few years before closest approach, not the decades or centuries that would allow meaningful preparation. That detection gap creates an uncomfortable situation. We know rogue planets exist in large numbers. We understand the potential consequences of close encounters. Yet we have no systematic early warning system capable of identifying incoming objects with sufficient lead time. The upcoming Nancy Grace Roman Space Telescope will improve this situation dramatically. Scheduled to launch by May 2027, it will conduct a galactic bulge time domain survey, potentially discovering hundreds to thousands of rogue planets and refining mass estimates across the population. Roman's capabilities extend beyond simple detection. By observing microlensing events where rogue planets pass in front of background stars, astronomers can measure not just presence but mass with unprecedented accuracy. The January 2026 discovery of a Saturn-mass rogue planet roughly 9,800 light-years away demonstrated this technique's power. For the first time, researchers obtained a direct mass measurement rather than statistical estimates. That single data point improved population models significantly. More discoveries like that one will paint a clearer picture of the rogue planet population structure. Are most ejected worlds small rocky planets, or do gas giants dominate? Do formation mechanisms leave distinctive signatures in the mass distribution? How does ejection velocity correlate with planet type? These questions matter for risk assessment. A galaxy filled with Earth mass rogues presents different statistical risks than one dominated by Jupiter mass wanderers. The former are more numerous but less gravitationally disruptive. The latter are rarer but capable of greater orbital perturbations. Understanding the population structure also illuminates planet formation physics. Computer simulations suggest that for every solar system like ours, at least one gas giant and 5 to 10 smaller rocky worlds get ejected during formation. Those numbers come from modeling hundreds of systems with varying initial conditions, then running the physics forward for billions of simulated years. The simulations consistently show that ejection isn't occasional. It's standard. Most planetary systems shed members during their chaotic early evolution. This raises a peculiar question about our own history. If ejection is standard, did our solar system expel worlds during its formation? The NICE model suggests yes. Named after the French city where researchers developed it, this model proposes that our gas giants once occupied different orbital positions. Gravitational interactions shuffled them into their current locations, potentially ejecting a fifth giant planet entirely in the process. Evidence supporting this scenario includes the orbital distributions of asteroids and comets, the late heavy bombardment that scarred the Moon roughly 4 billion years ago, and the unusual orbits of certain Kuiper belt objects. If we did eject a planet, it's out there somewhere. It would carry chemical signatures linking it to our solar system, isotopic ratios that formed in our protoplanetary disk. Finding such an object would confirm the NICE model directly and demonstrate that even stable-appearing systems like ours experienced violent gravitational upheavals. The search for our hypothetical lost sibling represents one of astronomy's more speculative pursuits, but improving detection methods make it incrementally less impossible. Meanwhile, the search for Planet 9 continues. This hypothetical massive planet in the outer solar system could explain the peculiar clustering of certain trans-Neptunian object orbits. These extreme objects, orbiting beyond Neptune at distances averaging more than 250 astronomical units, tend to make their closest solar approaches in one sector. Their orbits tilt similarly. Random distribution would spread them more evenly. Something massive appears to be shepherding them gravitationally. Planet 9, if it exists, would have a mass roughly 10 times Earth's and orbit about 20 times farther from the Sun than Neptune. Several formation scenarios could produce such an object. It might be the core of a gas giant that Jupiter ejected during the solar system's youth. It could be a rogue planet that our Sun captured from interstellar space. Or it might have formed on a distant orbit and been pulled into its current eccentric path by a passing star. The capture hypothesis particularly intrigues researchers. Studies show that the Sun's gravitational field, combined with galactic tidal forces, creates regions where passing objects can become permanently trapped through a mechanism called permanent weak capture. An interstellar object entering these zones might remain on a chaotic orbit for millions of years before settling into a stable configuration. The Sun could potentially collect passing rogue planets and hold them at the solar system's outskirts, occasionally trading them with neighboring star systems like Alpha Centauri. This capture mechanism depends on precise conditions. The incoming object needs the right velocity and trajectory to dissipate enough orbital energy without escaping entirely. Galactic tides help by subtly altering the object's motion as it travels through regions where the Milky Way's gravitational field varies. These variations are tiny, but over millions of years, they can shift an initially unbound orbit into a bound one. The process works in reverse too, potentially releasing captured objects after long periods of gravitational confinement. Whether Planet 9 is a captured rogue or a native object, finding it would answer fundamental questions about solar system architecture. The Vera C. Rubin Observatory, currently under construction in Chile, should either detect it or rule out its existence within a few years through comprehensive sky surveys. The observatory's wide field of view and sensitive detectors will image the entire visible sky repeatedly, tracking anything that moves against the background stars. If Planet 9 lurks out there, Rubin will spot it. That pending discovery or non-discovery represents a broader shift in astronomy. We're moving from an era where we knew our immediate neighborhood reasonably well but understood little about the wider galaxy to one where we're cataloging thousands of exoplanets, detecting rogue planets light years away, and mapping the galaxy's structure in unprecedented detail. Each discovery refines our understanding of how planetary systems form, devolve, and sometimes disintegrate. The technology driving these discoveries has evolved dramatically. Finding rogue planets requires detecting objects that emit virtually no light and reflect nothing from nearby stars. They're invisible in traditional surveys. Microlensing changed everything. The technique exploits Einstein's general relativity. Any massive object warps spacetime around it, bending light that passes nearby. When a rogue planet drifts between Earth and a distant star, it acts as a gravitational lens, briefly magnifying the background star's light. The effect lasts hours to days depending on the planet's mass and velocity. Astronomers monitoring millions of stars can catch these fleeting signals. The practical challenges are staggering. Only 1 in 100,000 stars undergoes microlensing at any moment. Survey teams point their telescopes toward the galactic bulge in Sagittarius, where 400 million detectable stars cluster densely. Even there, finding planets requires observing millions of targets multiple times per hour. The OGLE and MOA projects identified hundreds of candidate events by 2007. Most were stellar lenses, but occasionally a light curve showed the characteristic spike indicating a planetary companion. Coordinated telescope networks spanning the globe enable continuous coverage, preventing observers from missing brief events that occurred during daylight hours at any single site. January 2026 brought a breakthrough that refined these techniques dramatically. An international team announced detecting a Saturn-mass rogue planet 9,800 light-years away through microlensing event KMT 2024 BLG 0792. What made this discovery extraordinary was simultaneous observation from ground-based telescopes in space. The parallax measurements from different viewing angles allowed direct mass calculation rather than statistical estimates. For the first time, astronomers knew a rogue planet's mass with certainty. The object weighed approximately 95 Earth masses, placing it firmly in the gas giant category. Previous detections relied on models comparing light curve characteristics to simulations. This measurement established a new standard for confirmation. But mass alone doesn't reveal origin stories. Velocity provides crucial forensic evidence about how these worlds became orphans. Ejected planets retain significant excess velocities, typically 8 to 16 kilometers per second above the background motion of stars in their birth regions. This speed difference acts as a fingerprint. Planets ejected through interactions with binary companions move even faster, roughly 3 times the velocity of worlds expelled through planet-planet scattering. These measurements let astronomers reconstruct the gravitational violence that launched specific objects into interstellar space. Each rogue planet carries evidence of its past encoded in its trajectory. Some rogue planets might never have had parent stars. Isolated formation theory proposes these objects form like stars do, from collapsing gas clouds, but halt at planetary scales. Insufficient initial cloud mass or external disruptions truncate accretion before the object can grow large enough for fusion. Turbulence within molecular clouds generates density perturbations that fragment into multiple low-mass clumps. These cores collect gas directly from surrounding nebulae, building planetary mass bodies without protoplanetary disks. The International Astronomical Union proposed calling such objects sub-brown dwarfs to distinguish them from ejected planets. Whether this distinction matters philosophically or just taxonomically remains debated. Another 2025 discovery challenged assumptions about rogue planet behavior. Astronomers identified CHA 1107 to 7626, located 620 light-years away in Chameleon constellation. This free-floating planet exhibits a mass 5 to 10 times Jupiter's and displays something unprecedented, an enormous growth spurt. The object accretes gas and dust from surrounding material at 6 billion tons per second, the strongest episode ever recorded for planetary mass bodies. This rogue planet possesses its own accretion disk, behaving more like a young star than a typical planet. Magnetic activity appears to drive material infall in ways previously thought exclusive to stellar evolution. The discovery suggests rogue planets can remain dynamically active long after ejection or formation. These findings reveal how violent planetary system formation actually is. Computer simulations model this chaos systematically. Researchers created 100 virtual planetary systems, each containing 3 to 10 planets on near-circular coplanar orbits around Sun-like stars. Running the equations forward for 1 billion simulated years produced consistent results. For every stable system like ours that forms, at least one gas giant and approximately 5 to 10 smaller rocky worlds get ejected into interstellar space. The process is standard, not exceptional. Ejection represents a normal byproduct of gravitational interactions during the first several million years when systems haven't settled into stable configurations yet. Binary star systems amplify these dynamics. Planets in binary systems experience more complex gravitational perturbations than those orbiting single stars. Even wide binaries contribute. Passing stars can perturb the eccentricity of stellar orbits, occasionally sending binary companions close together. These encounters trigger planetary ejections or even steal planets from one star's gravitational sphere. Research focusing on circumbinary systems, planets orbiting both stars in a binary, shows that misaligned orbital planes create instabilities ejecting planets with much greater frequency. Given that binary stars comprise more than half of all stellar systems, they likely contribute disproportionately to the rogue planet population. Planet-planet scattering in single-star systems follows predictable patterns. When two planets approach too closely, gravitational interactions transfer orbital energy between them. Usually the less massive planet gains energy, accelerating to escape velocity while its massive companion's orbit shrinks slightly. The exchange conserves momentum but redistributes it dramatically. Close encounters during migration through gas-rich protoplanetary disks can trigger these events. Planets forming in compact configurations face higher collision and ejection probabilities. Our solar system possibly experienced such violence. Some researchers theorize we once had a fifth giant planet alongside Jupiter, Saturn, Uranus, and Neptune during a chaotic period called late instability. Gravitational interactions with other giants would have exiled this unfortunate world. The Nancy Grace Roman Space Telescope, launching by May 2027, will revolutionize rogue planet studies. Its wide field of view images the entire sky 1,000 times faster than Hubble. The Galactic Bulge Time Domain Survey will detect several hundred to several thousand free-floating planets, providing a robust statistical sample. Roman will employ both microlensing and direct infrared imaging, potentially finding planets as small as Mars. Mass measurements from parallax observations will become routine rather than exceptional. Within a few years, astronomers expect to understand rogue planet mass distributions and spatial distributions throughout the galaxy with unprecedented precision. Roman's survey scope extends beyond planets. The low mass range includes ejected planets. Brown dwarfs occupy the middle ground, too massive for planets, insufficiently massive for fusion-like stars. The high end encompasses stellar corpses, neutron stars, and black holes. Astronomers estimate our galaxy contains approximately 100 million stellar mass black holes, but isolated ones remain invisible. Roman's mass-dependent detection method will find them even without nearby matter to illuminate their presence. This comprehensive census of dark objects will reveal the hidden population of massive bodies lurking between stars. How likely is a rogue planet encounter threatening Earth? The odds within the next 1,000 years sit at approximately 1 in 1 trillion. Space's vastness provides protective buffering. Even with trillions of rogue planets wandering the Milky Way, typical distances between objects make close encounters extraordinarily rare. Our solar system occupies a relatively sparse region. Stellar density near the galactic core increases encounter probabilities, but we orbit 26,000 light-years from that dangerous neighborhood. The emptiness between stars shields us far more effectively than any planetary defense system could. But theoretical scenarios illuminate what could happen if one arrived. A rogue planet 13 times Jupiter's mass would gravitationally disrupt every planetary orbit in our system. Earth's path would become more elliptical, carrying us closer to the Sun during perihelion and farther during aphelion. We orbit within the narrow habitable zone where liquid water exists. Increased orbital eccentricity might not push us outside this zone permanently, but it would create extremely short, hot summers followed by prolonged, frigid winters. Compressed growing seasons would devastate agriculture. By the first never-ending winter's end, food shortages could threaten civilization itself. The gravitational architecture would fundamentally transform. Direct collision with Earth would vaporize both worlds, creating debris clouds of molten rock and gas eventually coalescing into new bodies. The kinetic energy from an object moving hundreds of kilometers per second would release energy equivalent to billions of nuclear weapons. Impact temperatures would reach solar surface levels. Any life would be instantly annihilated. More likely, though, a massive intruder would pass through without colliding, scattering inner planets, destabilizing asteroid and comet orbits, and potentially ejecting smaller worlds entirely. The solar system's current configuration represents billions of years of gravitational settling. One massive visitor would reset everything. Our solar system already possesses capture capability under specific circumstances. Research describes permanent weak capture where interstellar objects become trapped in the Sun's orbit through combined gravitational effects from both the Sun and the entire Milky Way galaxy. The mechanism works when an object enters specific regions where the Sun's gravitational influence dominates, particularly around Lagrange points where gravitational forces balance in complex ways. The object initially follows a chaotic orbit, remaining unstable for extended periods before eventually settling into a stable, long-term path. Think of it like a ball rolling on a complex landscape with valleys and hills, eventually finding a stable valley to rest in. The Sun could theoretically collect passing rogue planets and hold them at the solar system's outskirts for millions of years, occasionally trading them with Alpha Centauri, our nearest stellar neighbor. It's entirely possible captured rogue planets already exist in our system's distant reaches, invisible and undetected. This brings us to one of astronomy's most intriguing mysteries. Planet 9. The hypothetical ninth planet lurking in our solar system's outer region has generated fierce scientific debate. Its existence remains unconfirmed, but the evidence supporting it keeps mounting. Astronomers noticed something peculiar about extreme trans-Neptunian objects, bodies beyond Neptune orbiting the Sun at distances averaging more than 250 astronomical units. These distant objects cluster in unusual ways. They tend to make their closest approaches to the Sun in one sector, and their orbits tilt similarly. Random distribution would create scattered orientations. Instead, they align. Something massive appears to be shepherding them gravitationally. Planet 9 would have a mass about 10 times Earth's and orbit roughly 20 times farther from the Sun than Neptune does. At that distance, it would take between 10,000 and 20,000 years to complete a single orbit. Astronomers Konstantin Batygin and Michael Brown proposed several origin scenarios. Perhaps Planet 9 represents a giant planet's core ejected from its original orbit by Jupiter during the solar system's violent youth. Or maybe we captured it from another star during a close stellar encounter billions of years ago. Here's where it gets interesting. Planet 9 might be a rogue planet we captured. The captured rogue planet hypothesis elegantly explains several puzzling features. First, the extreme orbital distance makes sense if the object originated elsewhere and was caught in a weak gravitational trap. Second, the tilted orbit relative to the solar system's plane fits better with capture than with formation in our protoplanetary disk. Third, the mass range matches typical rogue planets detected elsewhere in the galaxy. But finding Planet 9 has proven extraordinarily difficult. The Kuiper belt stretches vast and dark. Any planet at those distances would reflect minimal sunlight, appearing as an incredibly faint dot moving imperceptibly slowly against background stars. Astronomers have conducted large-scale sky surveys and targeted searches based on predicted positions. Both approaches have come up empty so far. Some researchers question whether Planet 9 exists at all. They argue the clustering of trans-Neptunian object orbits might result from observational biases. We discover and track these objects during limited portions of each year when they're visible from Earth. Perhaps the apparent clustering reflects when and where we're looking rather than real gravitational influence from an undiscovered planet. The Vera C. Rubin Observatory, currently under construction in Chile, will settle this debate. Starting operations soon, it will conduct comprehensive sky surveys with unprecedented sensitivity and coverage. Within a few years, Rubin will either find Planet 9 or definitively rule out its existence in the predicted mass and distance ranges. The waiting continues. Whether Planet 9 exists or not, the broader implications remain fascinating. Our solar system's architecture might not be as stable and unchanging as we once assumed. Planets can be captured from interstellar space. Giant worlds might lurk in the darkness beyond Neptune's orbit. The solar system we see today represents just the survivors of a far more chaotic past. What about conditions on rogue planets themselves? Would anything survive there? Without starlight, rogue planets exist in extraordinary cold and darkness. The outer layers, exposed directly to space, reach temperatures just a handful of degrees above absolute zero. At those temperatures, molecules barely move. Chemistry essentially stops. Any water would be frozen harder than granite. Atmospheres, if they existed initially, would condense and freeze solid on the surface, creating bizarre landscapes of nitrogen ice and frozen carbon dioxide. But deep beneath the surface, conditions differ dramatically. Planetary formation releases enormous heat. Large planets contain radioactive elements whose decay generates warmth for billions of years. Tidal heating from internal friction can add energy if the planet has large moons. These internal heat sources persist regardless of whether a star shines overhead. Scientists theorize that sufficiently large rogue planets might maintain subsurface liquid water oceans insulated by thick ice shells. Similar oceans exist beneath the ice covering Jupiter's moon Europa and Saturn's moon Enceladus, kept liquid by tidal heating despite surface temperatures around -200 degrees Celsius. A rogue planet's internal heat could sustain comparable environments. Could life exist in those dark oceans? On Earth, entire ecosystems thrive around deep-sea hydrothermal vents, completely independent of sunlight. Chemosynthetic bacteria derive energy from chemical reactions between vent minerals and seawater. Complex organisms have evolved to exploit these bacteria, creating food webs in absolute darkness. A rogue planet's subsurface ocean might host similar chemistry. Hydrothermal vents could form where the molten core's heat reaches the ocean floor. Dissolved minerals would provide chemical energy. Life wouldn't need photosynthesis, just chemistry. The same fundamental processes that began life on Earth billions of years ago could operate beneath a rogue planet's frozen surface. This possibility transforms our understanding of habitability. We've focused intensely on planets orbiting within their star's habitable zone where surface temperatures permit liquid water. But if life can exist in subsurface oceans heated by internal planetary processes, habitability extends throughout the galaxy. Every sufficiently large rogue planet becomes potentially habitable regardless of distance from any star. Billions to trillions of rogue planets wander our galaxy. If even a tiny fraction harbor subsurface biospheres, life might be far more common than we've imagined. The galaxy might teem with living worlds we can't even detect from Earth because they emit no light and reflect none from nearby stars. Detection remains the critical challenge. How do you find life on a dark, frozen world drifting through interstellar space? Traditional biosignatures like oxygen or methane in atmospheres don't work because rogue planet atmospheres freeze solid. Remote sensing can't detect subsurface oceans through kilometers of ice. Even if we identified a rogue planet passing relatively nearby, sending a probe would require decades or centuries of travel time. The best near-term hope might be detecting heat signatures. Large rogue planets with active internal geology should emit detectable infrared radiation. Future space telescopes optimized for infrared detection might catalog thousands of rogue planets based on their thermal emissions. Analyzing those heat signatures could reveal which planets likely maintain internal warmth sufficient for subsurface liquid water. Beyond detection, the philosophical implications stagger the imagination. If life commonly exists on rogue planets, it evolved in eternal darkness, powered by planetary heat rather than starlight. Such life would have no concept of day or night, seasons, or the sky. Their entire universe would be the ocean they inhabit, bounded by ice above and rock below. They would never see stars. Would such life develop intelligence? Could technological civilization emerge in a subsurface ocean with no access to fire, metals, or the night sky that inspired human astronomy? These questions remain purely speculative, but they challenge our assumptions about life's requirements and possibilities. The rogue planet phenomenon forces us to reconsider everything we thought we knew about planets, habitability, and our place in the cosmos. These worlds represent a hidden population potentially outnumbering conventional planets around stars. They demonstrate that planet formation is far more violent and chaotic than we imagined, regularly casting worlds into the void. They might harbor life in forms we've never considered, thriving in darkness and cold on chemistry alone. As detection capabilities improve and our catalog of rogue planets expands, we'll answer fundamental questions about planetary demographics, formation mechanisms, and habitability limits. The Nancy Grace Roman Space Telescope will provide unprecedented statistical data. Future infrared observatories will probe their physical characteristics. Eventually, we might even send probes to study nearby examples directly. The rogue planet story represents more than just astronomical curiosity. It's a window into the violent chaos underlying cosmic order. Consider what happens during planet formation. You picture a serene disk of gas and dust gradually coalescing into worlds. The reality involves gravitational warfare. Planets collide, merge, scatter each other like cosmic billiard balls. Some grow massive enough to dominate. Others get flung into the void at thousands of kilometers per second. Computer simulations reveal the brutality. Researchers modeled 100 planetary systems, each containing 3 to 10 planets in stable circular orbits around Sun-like stars. They ran the physics forward for 1 billion simulated years. Nearly every system eventually destabilized. Close encounters between planets triggered cascading chaos. The typical outcome: at least one gas giant ejected. 5 to 10 smaller rocky worlds cast into darkness. Our solar system probably followed this pattern. Evidence suggests we once had a 5th giant planet. During a chaotic period astronomers call late instability, gravitational interactions with Jupiter, Saturn, Uranus, and Neptune shifted this world's orbit. Eventually, those same giants exiled it completely. That lost planet now wanders interstellar space, a frozen monument to our system's violent youth. Binary star systems produce even more chaos. When 2 stars orbit each other, any planets face competing gravitational influences. Passing stars can perturb those wide binary orbits, occasionally sending the pair much closer together. The resulting gravitational turbulence ejects planets or even steals worlds from one star and gives them to its companion. More than half of all star systems are binary. The rogue planet production rate might dwarf single-star systems like ours. But here's where it gets stranger. Some rogue planets never orbited any star. They formed alone in interstellar space through processes resembling star formation. Collapsing clouds of gas and dust contract under their own gravity, accreting material directly from surrounding nebulae. They just don't gather enough mass to ignite fusion. Instead, they halt at planetary scales, becoming objects the International Astronomical Union calls sub-brown dwarfs. How do you tell these formation pathways apart? Velocity provides the crucial fingerprint. Ejected planets retain significant excess speeds, typically 8 to 16 kilometers per second. That's much higher than normal stellar velocities in star-forming regions. Planets ejected by binary star interactions move even faster, roughly 3 times the velocity of those scattered by planet-planet collisions. These measurements let astronomers reconstruct each world's origin story from its current motion alone. The numbers grow more staggering the deeper you examine them. Current estimates suggest 7 rogue planets per star in our galaxy. With 400 billion stars, that implies nearly 3 trillion wandering worlds. Some researchers propose even higher ratios, potentially 20 rogue planets per star. 8 trillion dark spheres drifting through the Milky Way. More planets floating free than orbiting stars. This fundamentally rewrites planetary demographics. We've spent decades cataloging exoplanets around other stars. Thousands discovered. Potentially billions waiting. But the true planetary population might lie hidden in darkness, vastly outnumbering conventional worlds. Most planets in the galaxy could be rogues. Recent discoveries confirm their abundance. In January 2026, astronomers announced finding a Saturn-mass rogue planet about 9,800 light-years away. What makes this discovery revolutionary? For the first time, researchers directly measured a rogue planet's mass rather than making statistical estimates. The observation combined ground telescopes and space instruments to triangulate distance and calculate mass with unprecedented precision during a microlensing event. Another 2025 discovery revealed truly bizarre behavior. A rogue planet designated Cha 1107 to 7626 sits about 620 light-years away in Chameleon. Its mass is 5 to 10 times Jupiter. And it's eating. This world accretes gas and dust from surroundings at 6 billion tons per second, the strongest accretion episode ever recorded for any planetary mass object. It behaves more like a forming star than a planet, with magnetic activity driving material infall in ways previously thought exclusive to stellar evolution. These discoveries raise profound questions about what defines a planet. If objects form through star-like processes but halt at planetary masses, are they really planets? If worlds wander freely never having orbited stars, do they count? Traditional definitions centered on objects orbiting stars. Rogue planets demolish those boundaries. The categories blur. We need new frameworks. Detection remains extraordinarily difficult. Rogue planets emit virtually no light. They reflect none from nearby stars because there are no nearby stars. Microlensing offers the primary technique. When a rogue planet passes directly between Earth and a distant star, its gravity bends the star's light, briefly magnifying its brightness. These events last hours to days maximum. You must monitor millions of stars continuously to catch them. Survey teams point telescopes toward Sagittarius, looking toward our galaxy's dense central bulge where 400 million detectable stars crowd together. Just 1 in 100,000 stars undergoes microlensing at any moment. You need massive statistical samples. In 2007, the OGLE project identified 611 candidate events. MOA found 488. Those numbers have grown as detection networks expanded, but identifying the brief signature of a planet within stellar microlensing events requires extraordinary precision. The microlensing light curve reveals mass, but distance remains approximate. When dealing with objects tens of thousands of light-years away, uncertainties span thousands of light-years themselves. You know a planet exists. You know its approximate mass. But pinpointing its location stays frustratingly vague. Everything changes with the Nancy Grace Roman Space Telescope launching by May 2027. This instrument images the entire sky 1,000 times faster than Hubble. Roman's Galactic Bulge Time Domain Survey should detect several hundred to several thousand rogue planets, providing the first comprehensive statistical census. The mission will employ both microlensing and direct infrared imaging, potentially finding worlds as small as Mars. Roman will also catalog the broader population of dark objects lurking between stars. Beyond rogue planets lie brown dwarfs, objects too massive for planets but insufficient for stellar fusion. Beyond those sit stellar corpses, neutron stars, and black holes. Astronomers estimate 100 million stellar mass black holes drift through our galaxy, but we've never definitively found one floating alone because they're invisible. Roman's mass-based detection will find them regardless of nearby matter revealing their presence. This comprehensive dark object census will answer fundamental questions about galactic structure. How much unseen mass fills interstellar space? How violent was early planet formation across the galaxy? What fraction of planets get ejected versus remaining in stable systems? These answers reshape our understanding of cosmic architecture. The threat assessment remains clear. Odds of a rogue planet entering our solar system within the next 1,000 years. Approximately 1 in 1 trillion. Space is incomprehensibly vast. Even with trillions of rogue planets wandering the Milky Way, distances between objects make close encounters vanishingly rare. The emptiness serves as natural protection. Our solar system remains effectively isolated despite the hidden population surrounding us. But what if? If a rogue planet did enter our system, consequences would depend entirely on mass, trajectory, and approach distance. A Jupiter-mass world passing through the outer solar system might only slightly perturb orbits. A super-Jupiter 13 times more massive could fundamentally reshape everything. Earth's orbit might become more elliptical, shifting us closer to the Sun during perihelion and farther during aphelion. Even without direct collision, orbital changes would prove catastrophic. Shorter, hotter summers. Longer, frozen winters. Growing seasons collapse. Food production fails globally. Civilization faces extinction not from impact but from climate chaos induced by gravitational perturbation alone. If we were unlucky enough to face direct collision. Complete annihilation. Both worlds vaporize. The energy release would match billions of nuclear weapons simultaneously detonating. Yet our solar system might already host captured rogues. Research suggests the Sun can permanently trap passing interstellar objects through a mechanism called permanent weak capture. Combined gravitational effects of the Sun and the entire Milky Way galaxy can draw objects into chaotic orbits that eventually stabilize. These captured worlds might orbit at extreme distances, occasionally trading with nearby Alpha Centauri through complex gravitational interactions. Planet 9 could represent exactly this scenario. A hypothetical world 10 times Earth's mass orbiting 20 times farther than Neptune might explain the peculiar clustering of extreme trans-Neptunian objects. These bodies beyond Neptune orbit at distances averaging more than 250 astronomical units, and their orbits cluster suspiciously. Some astronomers propose Planet 9 was captured from another star. Others suggest it formed in our system but got kicked to distant orbits. The Vera Rubin Observatory under construction in Chile should either find it or definitively rule out its existence within years. Rogue planets force us to confront how little we actually know about our cosmic neighborhood. The galaxy contains hidden populations vastly outnumbering visible objects. Most planets might wander in eternal darkness. Some potentially harbor life in subsurface oceans heated by internal geology rather than starlight. We've built our understanding of habitability around stars, but the true story might unfold in places we can't even see. The darkness between stars isn't empty. It's filled with exiled worlds carrying the scars of ancient violence, drifting through the void as silent testimony to the chaos underlying cosmic order. Every planet we've ever studied orbits a star. Every definition of habitability we've constructed assumes stellar energy. Our entire framework for understanding planetary systems depends on gravitational hierarchies centered on fusion-powered spheres of plasma. Rogue planets demolish these assumptions completely. They represent a population potentially outnumbering conventional planets by factors we're only beginning to grasp. 8 trillion wandering worlds might drift through our galaxy alone. More planets floating free than orbiting stars. Most of the galaxy's planetary population exists in permanent darkness, following trajectories determined by violent ejections billions of years ago. Think about what that means for the search for life. We've focused exclusively on planets within habitable zones around stars, narrow bands where surface temperatures permit liquid water. But if large rogue planets maintain subsurface oceans heated by internal geology, habitability extends throughout interstellar space. Every sufficiently massive rogue becomes potentially habitable regardless of stellar proximity. Life on Earth began in darkness. Hydrothermal vents on the ocean floor supported entire ecosystems before photosynthesis even evolved. Those same chemical processes could operate beneath kilometers of ice on rogue planets, powered by planetary heat rather than sunlight. If even a small fraction of wandering worlds harbor such biospheres, life might be far more common than every optimistic estimate we've made based on stellar habitable zones. We'd never detect it with current methods. These hypothetical organisms would exist in sealed environments completely isolated from space. No atmospheric biosignatures to detect. No reflected starlight to analyze. Just dark frozen spheres drifting through the void, potentially teeming with alien chemistry in oceans we can't observe from trillions of kilometers away. The Nancy Grace Roman Space Telescope will transform this field when it launches. Hundreds or thousands of new detections. Direct mass measurements becoming routine rather than exceptional. Statistical distributions revealing formation mechanisms and ejection dynamics. Within a decade, we'll understand rogue planet demographics with precision currently impossible. But understanding population statistics differs dramatically from studying individual worlds up close. Sending probes to nearby rogue planets requires technology we don't yet possess. Interstellar travel at meaningful speeds remains firmly in the realm of theoretical physics. Even identifying which nearby rogue planets might harbor subsurface oceans presents challenges requiring infrared observatories we haven't built yet. The philosophical implications cut deeper than detection challenges. If technological civilizations can emerge in subsurface oceans on rogue planets, they develop completely different relationships with the cosmos than we have. No sky to observe. No stars to navigate by. No concept of day or night, seasons, or the broader universe beyond their frozen shell. Their entire cosmology would center on the ocean they inhabit, bounded by ice above and rock below. Would they ever develop astronomy? Could they even discover they existed on a planet without external reference points? The night sky inspired humanity's earliest scientific questions. What happens to curiosity about the universe when you live in eternal darkness with no universe visible? Our own solar system carries scars from the same violence that creates rogue planets. We probably ejected a fifth giant planet during late instability. The asteroid belt structure reflects ancient gravitational chaos. The late heavy bombardment that scarred the moon resulted from orbital reshuffling among our gas giants. We're survivors of the same chaotic processes that filled the galaxy with wanderers. Planet 9, if it exists, might represent a captured rogue. Or perhaps a native world kicked to extreme distances. Either way, its potential presence reveals how dynamic and unstable even mature planetary systems remain. The solar system we observe today isn't frozen in place. It's a temporary configuration that will eventually change again given enough time. The statistical risk remains infinitesimal. 1 in 1 trillion chance of a rogue planet entering our solar system within the next 1,000 years. Space's vastness protects us far more effectively than any defense system. But the theoretical consequences illuminate just how delicately balanced our existence actually is. Earth's stable orbit within the habitable zone depends on gravitational architecture that took billions of years to establish. One massive intruder could reset everything. We don't need to worry about rogue planets destroying Earth. We need to understand them because they represent the majority of our galaxy's planetary population. They reveal how violent and chaotic planet formation actually is. They potentially harbor life in forms we never considered. They challenge every assumption we've made about what planets are and where they can exist. The darkness between stars isn't empty void. It's filled with worlds. Some larger than Jupiter. Others smaller than Earth. all carrying chemical signatures from their birth systems, all following trajectories determined by gravitational violence that occurred when their parent systems were young and unstable. They're monuments to chaos, frozen in time, drifting through the galaxy as permanent reminders that the ordered solar system we inhabit represents a rare exception rather than the cosmic norm. Detection methods will improve. Catalogs will expand. Eventually, we'll understand rogue planet populations with the same precision we currently understand exoplanets around stars. The Nancy Grace Roman Space Telescope starts this process. Future infrared observatories will continue it. Decades from now, we might even send probes to study nearby examples directly, analyzing their composition and searching for signs of subsurface oceans. But the fundamental revelation has already occurred. Most planets in the galaxy don't orbit stars. They wander alone through interstellar space, ejected during the violent formation of planetary systems or formed independently in collapsing gas clouds. The universe contains far more dark worlds than illuminated ones. We've spent centuries studying the exceptions while remaining completely ignorant of the rule. Rogue planets aren't anomalies. They're the norm. The galaxy is filled with orphaned worlds drifting through darkness, and we're only beginning to understand what that means for planet formation, the prevalence of life, and our place in a cosmos far stranger than we imagined. Right now, there's something lurking 26,000 light-years away that's warping the fabric of space and time itself. This object contains 4 million times the mass of our Sun compressed into a region smaller than Mercury's orbit. We've known it existed for decades, but we only saw its face for the first time in 2022. At the heart of our galaxy sits Sagittarius A star, the supermassive black hole that anchors the Milky Way. Everything in our cosmic neighborhood, including our Sun and the billions of stars around us, orbits this invisible monster. But calling it invisible isn't quite accurate anymore. Scientists recently captured an image that changed everything we thought we understood about the center of our galaxy. The story begins not with cutting-edge technology, but with a crackling radio signal detected in 1933. Karl Jansky, working at Bell Telephone Laboratories, was trying to track down sources of static that interfered with radio communications. He built an antenna system and started scanning the sky. What he found was completely unexpected. A persistent radio signal kept appearing from the direction of Sagittarius. It wasn't random noise. It wasn't interference. The signal was coming from space itself, specifically from the center of our galaxy. Jansky had accidentally discovered radio astronomy, and he pointed us toward one of the most profound mysteries in the universe. For decades, that radio source remained just that. A mystery. A bright spot on radio telescopes with no clear explanation. Scientists knew something unusual sat at the galactic center, but they couldn't see it, couldn't measure it, couldn't understand what it was. Then in 1974, Bruce Ballack and Robert Brown made a discovery that would eventually win others a Nobel Prize. Using the baseline interferometer at the National Radio Astronomy Observatory, they detected something remarkable. Within that larger radio source Jansky had found, there was a compact, incredibly bright component. Something small. Something intense. Something unlike anything they'd seen before. Robert Brown gave it a name that stuck. Sagittarius A star. The asterisk wasn't random. In atomic physics, excited states are marked with asterisks. Brown thought this radio source was exciting. He had no idea how right he was. Throughout the 1980s, evidence mounted. This wasn't just an unusual radio source. The emissions, the brightness, the compact nature of the object, everything pointed toward a single conclusion. A black hole. Not just any black hole, but a supermassive one, sitting right at the gravitational anchor point of our entire galaxy. But here's where it gets interesting. You can't actually see a black hole. Light can't escape it. So how do you prove something exists when it's fundamentally invisible? You watch what dances around it. Stars near the galactic center move in ways that defy normal explanation. They whip around an invisible point at velocities that should be impossible. Star S2, one of the closest stars to Sagittarius A star, completes an orbit in just 16 years. That might sound slow until you realize its orbit is elliptical, bringing it screaming past the black hole at nearly 5,000 kilometers per second. Scientists tracked S2 and other stars for decades. They measured positions. They calculated velocities. They mapped orbits with obsessive precision. What they found was undeniable. These stars were orbiting something with a mass of roughly 4.3 million suns, confined in a volume no larger than 17 light-hours across. Nothing else could explain it. No cluster of dead stars. No exotic form of matter. Only a supermassive black hole could pack that much mass into that small a space without collapsing into something even stranger. Reinhard Genzel and Andrea Ghez spent years on this work. 16 years of tracking stellar orbits. Thousands of observations. Complex calculations. Their teams worked independently, using different telescopes, different methods. They both reached the same conclusion. In 2020, they shared the Nobel Prize in Physics for proving Sagittarius A star is a supermassive compact object, and that a black hole is the only possible explanation. But proving it exists and actually seeing it are two different challenges entirely. The problem is scale. Sagittarius A star sits 26,000 light-years away. From Earth, it appears smaller than a grain of salt viewed from New York to Los Angeles. To photograph something that tiny at that distance requires a telescope the size of Earth itself. We don't have a telescope the size of Earth. We can't build one. Physics won't allow it. So scientists did something audacious instead. They built a virtual telescope using 8 radio observatories scattered across the planet, from Hawaii to Antarctica, from Chile to Spain. The Event Horizon Telescope isn't a single instrument. It's a coordinated network synchronized to within a fraction of a millimeter using atomic clocks locked to GPS time standards. When all 8 telescopes observe the same target simultaneously, their data can be combined to create an image with resolution 4,000 times better than Hubble. The technical challenges were staggering. Each telescope generated petabytes of data. Internet speeds couldn't handle the transfer, so hard drives were physically shipped to a central processing facility. The observations happened in 2017. It took 5 years of calculations to process the data into a single image. On May 12, 2022, the world saw Sagittarius A star for the first time. Not the black hole itself, which remains invisible, but the glowing ring of superheated matter spiraling around it just outside the event horizon. A donut of light, bent and twisted by gravity so intense it warps spacetime into knots. The image shows a bright, thick ring roughly 52 million kilometers in diameter. That's larger than Mercury's entire orbit around the Sun. The ring isn't uniform. It has brightness variations, regions where matter glows more intensely as it accelerates toward the point of no return. What you're seeing isn't the black hole. It's the shadow of the event horizon surrounded by photons that barely escaped. Some of that light orbited the black hole multiple times before reaching us, bent around by gravity in ways that seem to violate common sense but perfectly match Einstein's predictions. The interior of that ring appears dark, not because nothing is there, but because any light crossing the event horizon can never come back. That darkness is the most direct view we have of the boundary between our universe and whatever lies beyond. Scientists compared this image to one captured 3 years earlier. M87 star, a supermassive black hole in a galaxy 55 million light-years away. M87 star is a monster, containing 6.5 billion solar masses, more than 1,000 times heavier than Sagittarius A star. It could swallow our entire solar system without noticing. The two black holes look nearly identical. Same ring structure. Same shadow. Same basic geometry. This tells us something profound about the universe. General relativity works. Black holes of vastly different sizes, in completely different environments, separated by millions of light-years, all follow the same rules. Gravity doesn't care about scale. But Sagittarius A star revealed something unexpected in follow-up observations. When astronomers examined it in polarized light, they detected organized magnetic fields spiraling from the edge of the event horizon. Strong fields. Structured fields. Fields that look remarkably similar to those around M87 star. This matters because M87 star shoots jets of matter thousands of light-years into space, powered by those magnetic fields. Sagittarius A star shows no obvious jets. It's quiet by comparison, feeding on material at a rate scientists compare to a human eating 1 grain of rice every million years. Yet those magnetic fields suggest Sagittarius A star might have a hidden jet. Something we haven't detected yet. Something subtle. The similarity to M87 star implies that strong, organized magnetic fields might be universal to all supermassive black holes, regardless of how actively they're feeding. Recent observations added another surprise. Sagittarius A star is spinning. Fast. Analysis of X-ray and radio data shows it rotating at roughly 60% of the maximum possible speed for a black hole. That spin warps spacetime so severely that the black hole's shape distorts from a sphere into something more like a football. This rotation creates a region called the ergosphere, where spacetime itself is dragged around the black hole. Nothing inside the ergosphere can remain stationary. Everything, even light, is forced to move in the direction of the spin. The faster a black hole rotates, the larger and more powerful this region becomes. The spin also tells us about Sagittarius A star's history. Black holes gain angular momentum by consuming matter that orbits in a preferred direction. The fact that our black hole spins so rapidly suggests it's been fed by accretion disks aligned in roughly the same plane for billions of years. But here's what makes Sagittarius A star truly fascinating for scientists. It's not just the closest supermassive black hole. It's close enough that we can watch individual stars orbit it. We can measure how gravity affects the flow of time near the event horizon. We can test Einstein's predictions under the most extreme conditions nature allows. When star S2 made its closest approach in 2018, scientists detected gravitational redshift. The star's light was stretched to longer wavelengths as it climbed out of the black hole's gravitational well, exactly as general relativity predicts. Time literally runs slower near Sagittarius A star than it does here on Earth. These observations push physics to its limits, probing the boundary between the quantum world and the cosmic one. And as our instruments improve, we're discovering that the galactic center is far stranger than anyone expected. In 2023, scientists using the Atacama Large Millimeter Array discovered something they weren't expecting. Space tornadoes. Massive vortices of gas and dust swirling around Sagittarius, a star, invisible to optical telescopes but blazing in radio wavelengths. These aren't gentle spirals. They're violent cyclones of superheated matter, rotating at tremendous speeds, turning the space around the black hole into a cosmic storm system. The discovery changed how we think about so-called quiet black holes. Sagittarius, a star, may eat slowly, but it's anything but calm. The tornadoes stretch across light years of space, powered by magnetic fields and the black hole's rotation. They create turbulence in the accretion disk, stirring matter like a cosmic blender. This turbulence explains something that had puzzled astronomers for years. Why does Sagittarius, a star, flare so unpredictably? The black hole produces 5 to 6 major flares every day, plus countless smaller ones. Each flare is a burst of radiation, sometimes in X-rays, sometimes in infrared, sometimes in radio waves. The flares are erratic. No pattern. No predictability. Observations in 2023 and 2024 showed that the black hole looks different almost every time you observe it. One day it's bright in one wavelength. The next day, completely different. The space tornadoes drive this chaos. They create pockets of hot, dense gas that spiral inward. When these pockets cross the event horizon, they release bursts of energy. The timing depends on turbulence patterns that shift constantly. It's like trying to predict exactly when a specific wave will break on a stormy ocean. You know waves are coming, but the details are impossible to forecast. The James Webb Space Telescope caught one of these flares in mid-infrared light in 2022, the first detection at that wavelength. The flare lasted about an hour, bright enough to stand out against the background glow of the galactic center. What causes the flare itself? Material falling toward the event horizon accelerates to a significant fraction of light speed. Friction heats it to millions of degrees. At those temperatures, atoms are stripped of their electrons. The resulting plasma radiates intensely before vanishing forever beyond the point of no return. But here's what makes the recent discoveries truly unsettling. Sagittarius, a star, wasn't always this quiet. January 2026 brought a revelation that rewrote our understanding of the black hole's recent history. The XRISM Space Telescope, launched in 2023 with unprecedented X-ray resolution, detected something extraordinary while observing a giant gas cloud near the galactic center. The cloud was glowing in X-rays. Not from its own energy, but reflected light. Light that originated from Sagittarius, a star, centuries ago. The cloud acts as a cosmic mirror, showing us what the black hole looked like in the past. And what XRISM revealed is startling. Within the last few hundred to 1,000 years, Sagittarius, a star, erupted with ferocious intensity. An outburst that made it shine in X-rays 10,000 times brighter than today. 10,000 times. For perspective, that would make it visible across the entire galaxy, a beacon of high-energy radiation flooding the Milky Way's central regions. What triggered such an eruption? We don't know for certain. One possibility is that a large object, maybe a gas cloud tens or hundreds of times more massive than G2, fell into the accretion zone all at once. When massive amounts of material suddenly become available, the accretion disk can enter a different regime entirely. Instead of the slow, steady trickle we see today, the disk becomes thick, hot, and chaotic. Material piles up faster than it can fall in. The result is an outburst, a phase where the black hole feeds ravenously before settling back into dormancy. These outbursts might be common over long timescales. We're just seeing Sagittarius A star during a quiet phase, a lull between feeding frenzies that could last centuries or millennia. This RISM data provides something no direct observation ever could. A window into the black hole's behavior before humans had telescopes. Before we knew black holes existed. The X-ray echo traveled through space for hundreds of years before reaching the gas cloud and bouncing toward Earth. It's like receiving a letter from the past, written in high-energy photons. This discovery raises an immediate question. If Sagittarius A star erupted that violently so recently in cosmic terms, will it happen again? And if it does, what would that mean for Earth? At 26,000 light-years away, we're safe from direct harm. The black hole's gravity doesn't reach us. Neither does the radiation from normal flaring activity. But an eruption 10,000 times more powerful. That changes the calculation. High-energy X-rays and gamma rays from such an event could, in theory, affect Earth's upper atmosphere. Not catastrophically. We're too far away for that. But measurably. Some scientists speculate that ancient cosmic events might be recorded in ice cores or geological layers, subtle signatures of radiation bursts from the galactic center. No one has found definitive evidence yet. But we're looking. The space tornado's discovery connects to another mystery. The stability of stellar orbits near the black hole. Recent observations using the ERIS instrument at the Very Large Telescope revealed that several dusty objects follow stable orbits around Sagittarius A star, some for potentially thousands of years. These aren't normal stars. They're compact, dense structures, possibly young stars still forming or exotic objects we don't fully understand. Earlier theories predicted they'd be torn apart or consumed quickly. Instead, they persist. Their stability suggests that the region immediately around the black hole, despite the tornadoes and flares, maintains a kind of dynamic equilibrium. Chaos at small scales. Order at larger ones. This challenges our mental models. We tend to think of black holes as cosmic vacuum cleaners, consuming everything nearby. But Sagittarius A star demonstrates something more subtle. Less than 1% of material that enters the black hole's gravitational influence actually crosses the event horizon. The rest is ejected, blown away by magnetic fields and radiation pressure, or simply fails to lose enough angular momentum to fall in. The black hole is picky. It's surrounded by swirling matter, but most of that matter never gets consumed. It orbits, radiates, heats up, and eventually escapes or settles into stable configurations. The 2014 encounter with gas cloud G2 illustrated this perfectly. Astronomers predicted fireworks. A massive cloud, 3 times Earth's mass, was on a collision course with the accretion zone. Models suggested we'd see a dramatic brightening, maybe a sustained outburst lasting months or years as the cloud was shredded and consumed. Instead, nothing happened. The cloud passed through its closest approach. Sagittarius A star barely reacted. Some scientists called it a flop. But it wasn't a failure of prediction so much as a revelation about how black holes actually feed. The cloud stretched, distorted by tidal forces, but didn't dump its material into the black hole all at once. Most of it stayed in orbit or was blown outward. Only a tiny fraction, if any, crossed the event horizon. This tells us that accretion is a delicate process. You can't just throw matter at a black hole and expect it to fall in. The matter has to lose angular momentum. It has to cool. It has to navigate magnetic fields and radiation pressure. All of these factors act as barriers, filtering what reaches the event horizon. Sagittarius A star sits in the middle of a vast reservoir of potential fuel, but it's starving because the delivery mechanisms are inefficient. It's like being surrounded by food you can't quite reach. Which brings us back to the question of jets. M87 star shoots jets tens of thousands of light-years into space. Those jets are powered by magnetic fields anchored in the accretion disk and twisted by the black hole's spin. The fields act like particle accelerators, launching matter outward at nearly the speed of light. Sagittarius A star has the same magnetic field structure, the same spin. So where are its jets? One possibility is that they exist but are too faint to detect easily. The black hole's low accretion rate means less material available to fuel the jets. They might be there, just weak and hard to see against the bright background of the galactic center. Another possibility is orientation. If the jets point toward or away from us rather than perpendicular to our line of sight, they'd be much harder to observe. Or maybe the jets are intermittent. During quiet phases like now, they shut down completely. During outbursts like the ones RISM detected, they roar to life, pumping energy into the surrounding galaxy before fading again. This would make Sagittarius A star a variable jet source, active only during specific feeding events. If that's true, we might never see strong jets in our lifetimes. Or we might see them suddenly appear if the black hole enters another eruption phase. The uncertainty is part of what makes this object so compelling. We're watching a system that operates on timescales far longer than human civilization, trying to understand its behavior from a handful of snapshots. The magnetic fields themselves are a subject of intense study. They're not static. They twist, reconnect, and reconfigure constantly, driven by the motion of ionized gas in the accretion disk. When field lines reconnect, they release enormous amounts of energy, possibly triggering some of the flares we observe. This process, called magnetic reconnection, is the same phenomenon that powers solar flares on the Sun. But near a black hole, the energies involved are millions of times greater. The fields can also launch winds, streams of charged particles blown outward from the disk. These winds carry away angular momentum, allowing fresh material to spiral inward. Without the winds, the accretion disk would choke on its own rotation. Understanding these processes requires observations across the electromagnetic spectrum. Radio telescopes see the cool outer regions of the accretion disk. Infrared instruments detect warm dust and gas slightly closer in. X-ray observatories probe the hottest material near the event horizon. Each wavelength reveals a different part of the story. Combine them, and you start to see how the whole system operates, how energy flows from the outer disk inward, how matter heats and radiates, how magnetic fields shape and control the chaos. Sagittarius A star is a laboratory for extreme physics, accessible in ways no other supermassive black hole can match. And the more we learn, the stranger it becomes. One detail makes this especially puzzling: the black hole's spin. Sagittarius A star rotates at about 60% of the theoretical maximum speed. That's fast enough to drag spacetime itself into a vortex around the event horizon. This rotation warps the fabric of reality into what physicists call the ergosphere, a region where nothing can stay still. Even light gets swept along by the current. Spin matters because it determines how efficiently a black hole can launch jets. The faster it rotates, the stronger the magnetic fields can become, and the more energy can be extracted from the rotation itself. This process, called the Blandford's-Najek mechanism, converts rotational energy into electromagnetic radiation and particle acceleration. It's one of the most efficient energy conversion processes in the universe. Sagittarius A star has the spin. It has the magnetic fields. So why the silence? Maybe we're asking the wrong question. Instead of wondering why the jets are weak, perhaps we should ask what makes M87 star's jets so strong. That black hole weighs over 1,000 times more than ours. Its accretion disk is enormous, a swirling reservoir of matter extending billions of kilometers. Material pours in constantly, maintaining high densities and strong magnetic fields throughout the disk. Sagittarius A star's accretion disk is tiny by comparison. The material feeding it comes in fits and starts, never forming the kind of sustained, organized flow needed to power persistent jets. What fuel does arrive gets consumed quickly, leaving gaps between feeding events. During those gaps, the magnetic field structure might partially collapse, only to rebuild when fresh material arrives. This creates a feedback loop. Weak accretion leads to weak magnetic fields. Weak fields can't sustain strong jets. Without jets to carry away angular momentum, material can't fall in efficiently, keeping accretion weak. The system locks itself into a low-energy state. But that's not the whole story. In 2025, astronomers using the Atacama Large Millimeter Array discovered something unexpected. Space tornadoes. Spiral structures in the gas surrounding Sagittarius A star, rotating at tremendous speeds. These weren't jets exactly, but they weren't ordinary accretion disk turbulence either. They were organized, coherent flows of material being flung outward by magnetic forces. The discovery changed how we think about quiet black holes. Even when not producing classical jets, they're far from inactive. Energy and matter move in complex patterns, driven by magnetic fields that constantly reconfigure themselves. The tornadoes might be failed jets, structures that start to form but can't quite break free of the disk's gravity. Or they might be a different kind of outflow entirely, one we hadn't recognized before because we were looking for the wrong signatures. What makes these tornadoes possible? The answer lies in magnetic reconnection. When field lines twisted by the black hole's rotation and the disk's turbulence intersect, they can snap and reconnect in new configurations. This releases energy explosively, heating gas and accelerating it outward. The process happens constantly throughout the accretion disk, creating pockets of intense activity embedded in otherwise calm regions. Each reconnection event is like a miniature explosion. Too small to see individually from Earth, but collectively they produce the flares we observe. Some flares are minor, barely detectable. Others reach X-ray energies, bright enough to stand out against the background radiation of the galactic center. And occasionally, very rarely, something much larger happens. This rhythm detection of that ancient eruption tells us Sagittarius A star is capable of violence we haven't witnessed directly. Within the last few hundred to 1,000 years, it's shown 10,000 times brighter than today. That level of luminosity requires a massive influx of material, far more than the black hole currently receives. Something had to deliver a huge amount of gas to the inner accretion disk all at once. What could cause that? One possibility is a stellar disruption event. A star wandering too close to the black hole gets torn apart by tidal forces. The debris forms a temporary accretion disk, much denser and hotter than normal. As this material spirals inward, it releases enormous amounts of energy before disappearing beyond the event horizon. The whole process might last months or years, producing a dramatic flare visible across the galaxy. Another possibility is the collision of gas clouds. The galactic center is crowded with molecular clouds, massive concentrations of hydrogen and dust. If two clouds collide near the black hole, the impact could compress the gas, causing it to lose angular momentum and fall inward rapidly. Again, you get a temporary surge in accretion and a corresponding burst of radiation. Or maybe it's something more gradual. Small disruptions accumulating over time, each one adding material to the accretion disk until it reaches a critical threshold. Then the disk becomes unstable, dumping its contents onto the black hole in a feeding frenzy. This kind of cyclic behavior is seen in other accreting systems, from young stars to white dwarfs. There's no reason black holes should be immune. Whatever the cause, the eruption left evidence scattered throughout the surrounding space. X-rays from the event traveled outward at the speed of light, eventually striking clouds of gas located thousands of light-years away. When those X-rays hit the clouds, they ionized the gas, causing it to glow. That glow is what SRISM detected. Not direct emission from the black hole, but an echo reflected off distant material. The clouds act as time machines of a sort. By measuring the properties of the reflected X-rays, astronomers can reconstruct what the original eruption looked like. How bright it was, how long it lasted, what kind of spectrum it produced. It's like finding a mirror that shows you an event from centuries ago, preserved in the light still bouncing around the galaxy. This technique, called X-ray echo mapping, only works because the galactic center is so densely packed with gas. In a quieter region of space, the X-rays would travel outward forever, never encountering anything to reflect them. But near Sagittarius, a star, clouds are everywhere, creating a natural network of reflectors. Each cloud captures a slightly different view of the same event, like witnesses standing at different positions around a crime scene. Comparing these different views reveals details impossible to see any other way. The geometry of the eruption. Whether it was symmetric or directional. How the radiation output changed over time. All of this information remains encoded in the echoes, waiting to be decoded by sensitive instruments like SRISM. The discovery raises a critical question. If Sagittarius, a star, erupted that violently just a few centuries ago, could it happen again? And if it did, what would the consequences be for life in the galaxy? The answer depends on how far the effects reach. X-rays from the black hole don't travel in all directions equally. They're beamed preferentially along certain paths, shaped by the geometry of the accretion disk and any jets or winds present during the eruption. If Earth happened to lie along one of those beams, we'd receive a much higher dose of radiation than if we were off to the side. At our distance of 26,000 light-years, even a major eruption probably wouldn't sterilize the planet. Earth's atmosphere and magnetic field provide significant shielding. But there could be subtle effects. Increased ionization in the upper atmosphere. Disruption of radio communications. Possible impacts on satellite systems. Nothing catastrophic, but noticeable. Closer to the galactic center, the story would be different. Stars within a few thousand light-years of Sagittarius, a star, could receive dangerous levels of radiation during a major outburst. Any planets orbiting those stars might lose their atmospheres or suffer mass extinctions. The region immediately surrounding the black hole becomes temporarily uninhabitable, sterilized by high-energy photons. This has implications for where life can exist in the galaxy. The galactic center, despite its abundance of stars and raw materials, might be too violent to support stable biospheres. Eruptions from the central black hole, combined with frequent supernovae from massive stars, create an environment of chronic radiation exposure. Life might emerge there, but it wouldn't last long. Our position in a quieter spiral arm starts to look less random. Perhaps there's a habitable zone in galaxies just like there's a habitable zone around stars. Too close to the center and radiation becomes a problem. Too far out and heavy elements become scarce. Somewhere in between lies the sweet spot where civilizations can develop without being periodically sterilized by their own galactic core. This RISM discovery forces us to reconsider what we thought we knew about galactic habitability. For decades, astronomers assumed the habitable zone in galaxies was purely a function of heavy element abundance. You need metals to build rocky planets. You need carbon, nitrogen, and oxygen for organic chemistry. The outer regions of galaxies, where few stars have lived and died, lack these ingredients. Therefore, life should cluster toward the galactic center where generations of stellar nucleosynthesis have enriched the interstellar medium. But radiation changes everything. What good is having the right chemistry if periodic eruptions sterilize your planet every few thousand years? The galactic center might be materially rich but energetically hostile. It's like trying to build a house in a war zone. You have all the materials you need, but the environment keeps destroying your work. This realization reshapes our understanding of where to search for extraterrestrial intelligence. SETI programs have traditionally focused on sun-like stars regardless of their galactic location. The assumption was that any stable star with the right temperature could potentially host life. We're starting to see why that might be naive. Stars near the galactic center face challenges beyond just the occasional black hole eruption. The stellar density there is orders of magnitude higher than in our neighborhood. Close encounters between stars are common. Gravitational perturbations can disrupt planetary orbits, sending worlds careening into their suns or flinging them into interstellar space. Any civilization trying to develop there would face constant astronomical chaos. Then there's the matter of supernovae. Massive stars live fast and die young, exploding as supernovae that release enormous amounts of gamma radiation. Near the galactic center, where massive stars are abundant, these explosions happen frequently. A civilization within a few thousand light-years of the core might face a nearby supernova every few million years. That's not enough time for complex life to recover between events. The picture emerging is one of concentric zones. An inner region, extending perhaps 5,000 light-years from Sagittarius A star, where conditions are simply too violent for stable biospheres. Regular black hole eruptions, frequent supernovae, and gravitational chaos create an environment where life might spark occasionally but never endures long enough to develop intelligence. Beyond that lies a transition zone. Still dangerous, but with longer periods of calm between catastrophes. Life could potentially develop here, but it would face periodic resets. Civilizations might rise and fall repeatedly, never quite achieving the stability needed for long-term technological development. And then there's our region. About 26,000 light-years from the center, far enough that black hole eruptions are mere background noise. Supernova rates are low. Stellar encounters are rare. The galaxy provides abundant heavy elements without the accompanying radiation hazards. It's not that we're in a special place. It's that life capable of asking these questions can only arise in places like this. This brings us back to the original mystery. Why is Sagittarius A star so quiet now if it was so active just centuries ago? The answer lies in understanding what triggers these eruptions in the first place. Black holes don't decide to erupt. They respond to their feeding patterns. When a large amount of material suddenly falls toward the event horizon, it releases tremendous energy. The material doesn't fall straight in. It spirals, forming an accretion disk where friction heats the gas to millions of degrees. Most of the time, Sagittarius A star feeds on a thin trickle of material. Stellar winds from nearby stars. Diffuse gas from the interstellar medium. This steady diet produces the low-level activity we observe today. But occasionally, something more substantial wanders too close. A gas cloud. A disrupted star. When that happens, the feeding frenzy begins. The recent discovery of space tornadoes around Sagittarius A star adds another layer to this story. Using the Atacama Large Millimeter Array, astronomers detected massive rotating structures in the gas surrounding the black hole. These aren't tornadoes in the atmospheric sense. They're magnetic whirlwinds, channeling material toward and away from the event horizon in complex spiraling patterns. What makes these structures remarkable is their persistence. They exist even during Sagittarius A star's quiet periods, suggesting they're a permanent feature of the environment near the black hole. The magnetic fields threading through the gas create these rotating structures, and the rotation helps explain why so little material actually reaches the event horizon. Think of it this way. Material falling toward a black hole carries angular momentum. It can't just drop straight in because physics won't allow it. Instead, it has to lose that angular momentum somehow, and magnetic fields provide the mechanism. The rotating structures we observe are essentially cosmic drains, allowing material to slowly spiral inward while shedding its angular momentum through electromagnetic interactions. But here's what's fascinating. These same magnetic structures also provide an ejection mechanism. Not all material falling towards Sagittarius A star makes it past the event horizon. A significant fraction gets redirected, flung back out into space at high velocities. This creates a feedback loop. The black hole feeds, but it also pushes material away, limiting its own growth rate. The implications extend beyond our galaxy. If magnetic tornadoes are a common feature around supermassive black holes, they help explain why these objects grow so slowly. Sagittarius A star weighs about 4 million solar masses. That sounds enormous, but it's actually quite modest for a galactic center black hole. Some supermassive black holes exceed 10 billion solar masses. Why the huge variation? Part of the answer might be feeding efficiency. Black holes with stronger magnetic fields or more organized rotating structures might eject more material, growing slower as a result. Those with weaker fields or more chaotic environments might feed more efficiently, ballooning to enormous sizes. The details of the magnetic environment could determine the ultimate mass a black hole achieves. This connects to another puzzle: the relationship between black hole mass and galaxy properties. Astronomers have known for decades that there's a tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of stars in its bulge. Bigger galaxies have bigger black holes, in very predictable ratios. But why? The traditional explanation invoked feedback. As black holes feed, they emit radiation and drive winds that heat the surrounding gas, preventing it from cooling and forming new stars. This regulates both the black hole's growth and the galaxy's star formation, creating the observed correlation. The discovery of magnetic structures around Sagittarius A star suggests the process might be more complex. What if the magnetic fields themselves play a regulatory role? As a galaxy grows and more material funnels toward the center, the magnetic field strength increases. Stronger fields create more efficient ejection mechanisms, limiting how much material actually reaches the black hole. The system self-regulates through electromagnetic processes, not just radiation pressure. Testing this idea requires observations of many different black holes at various stages of activity. Sagittarius A star provides one data point, currently in a quiet phase but with evidence of recent violent activity. M87 star, the other black hole we've imaged directly, represents the opposite extreme. It's actively feeding, driving powerful jets visible across millions of light-years. Comparing the magnetic structures around these two objects reveals how different feeding modes produce different electromagnetic geometries. The polarized light observations of both black holes show remarkably similar magnetic field patterns despite the thousand-fold mass difference. This suggests that the basic physics governing these structures remains consistent across enormous scales. Whether you're dealing with a 4 million solar mass black hole or a 6 billion solar mass monster, the magnetic fields organize themselves in similar ways. That universality is what makes Sagittarius A star such a valuable laboratory. We can study it in detail precisely because it's relatively small and close. The phenomena we observe there likely occur around every supermassive black hole, but most are too distant or too massive to examine with the same precision. Our galactic center becomes a template for understanding black hole behavior throughout the universe. Which brings us to perhaps the most important question. What will Sagittarius A star do next? The X-ray echo observations prove it can erupt violently. The magnetic tornado discoveries show it's constantly processing material in complex ways. The flare observations demonstrate it's perpetually active on small scales. Put all this together and you have a system that's fundamentally unpredictable. Black holes don't operate on human timescales. An eruption that occurred 500 years ago is essentially yesterday in cosmic terms. The fact that we haven't seen another major outburst in recorded history means nothing. The next one could happen tomorrow or 10,000 years from now. We simply don't know enough about the triggering mechanisms to make predictions. What we do know is that monitoring needs to continue. Every observation adds another piece to the puzzle. The observational campaigns tracking Sagittarius A star involve technology operating at the absolute limit of what's physically possible. Consider what's required to watch individual stars orbiting the black hole. These aren't leisurely observations through a backyard telescope. They demand decades of continuous monitoring using the world's largest optical instruments, coordinated across multiple sites, operating in wavelengths blocked by Earth's atmosphere. The Keck Observatory in Hawaii and the Very Large Telescope in Chile have tracked these stellar orbits since the 1990s. That's over 30 years of accumulated data, capturing positions accurate to within milliarcseconds. To put that precision in perspective, it's like measuring the width of a human hair from 2,000 miles away. The stars themselves move at thousands of kilometers per second, completing orbits in timeframes ranging from a few years to several centuries. Star S2, the poster child of these observations, completes one orbit every 16 years. Astronomers have now watched it complete more than 2 full trips around the black hole. Each passage provides another test of general relativity, another measurement of the black hole's mass, another constraint on alternative theories of gravity. The data quality improves with every orbit as detector technology advances and analysis techniques become more sophisticated. But S2 isn't the speed demon of the galactic center. That distinction belongs to S4714, which screams past Sagittarius A star at nearly 8% the speed of light. Its orbit brings it to within 12 astronomical units of the event horizon, closer than Saturn orbits our Sun. At that proximity, relativistic effects become impossible to ignore. Time dilation, gravitational redshift, orbital precession. All the exotic predictions of Einstein's theory manifest in measurable ways. Tracking these stars requires adaptive optics, a technology that compensates for atmospheric turbulence in real time. Earth's atmosphere constantly shifts and warps, blurring astronomical images. Adaptive optic systems measure these distortions hundreds of times per second and adjust the telescope's mirror to counteract them. The result is images nearly as sharp as if the telescope were floating in space, revealing details that would otherwise remain hidden. The technical achievement becomes even more impressive when you consider the environment being observed. The galactic center is one of the most crowded regions in the sky, packed with millions of stars separated by distances smaller than our solar system. Picking out individual stellar orbits from this stellar traffic jam requires not just sharp images but sophisticated computer algorithms that can track specific stars across decades of observations. Those algorithms face a particular challenge. Stars occasionally disappear behind dust clouds, or their light gets confused with nearby companions. The tracking software must maintain identity across observation gaps, sometimes spanning years, while the stars continue moving along their predicted paths. Any error in identification corrupts the orbital data, potentially invalidating years of careful measurements. Beyond the stellar orbits, understanding Sagittarius, a star, requires simultaneous observations across the entire electromagnetic spectrum. Radio telescopes track the compact radio emission from the immediate vicinity of the event horizon. Infrared observations penetrate the dust and reveal hot gas swirling inward. X-ray detectors catch the high-energy flares produced when magnetic field lines reconnect. Each wavelength tells a different part of the story. The coordination required is staggering. When Sagittarius, a star, produces a flare, astronomers want to catch it simultaneously in radio, infrared, and X-rays. This means scheduling telescope time across facilities on different continents, operated by different organizations, often booked years in advance. A single coordinated observation campaign might involve a dozen telescopes and hundreds of people. These multi-wavelength campaigns have revealed something unexpected about how material flows toward the black hole. The traditional model pictured a relatively smooth accretion disk, with matter spiraling gradually inward like water circling a drain. The reality appears far more chaotic. Material clumps into dense blobs that orbit for a while before either falling in or getting ejected. The magnetic fields threading through this material create turbulence that churns the disk continuously. Understanding this turbulence matters because it determines how efficiently the black hole can feed. If the magnetic fields are too strong, they prevent material from settling into a stable disk, instead driving it away in winds and jets. If they're too weak, they can't transport angular momentum effectively, causing material to pile up rather than flow smoothly inward. Sagittarius, a star, appears to operate in a middle regime where feeding is possible but highly inefficient. That inefficiency explains why our galactic center is so quiet compared to active galactic nuclei in other galaxies. Some black holes shine with the luminosity of 1 trillion suns, visible across billions of light years. Sagittarius, a star, barely radiates more than an ordinary star, despite having 4 million times the sun's mass. The difference lies entirely in the feeding efficiency. Active black holes are gorging. Ours is barely nibbling. Yet even that minimal feeding produces measurable effects throughout the inner galaxy. The radiation and winds from Sagittarius, a star, heat the surrounding gas, preventing it from cooling and forming new stars. This creates a dead zone around the galactic center, a region where star formation has essentially stopped. The feedback mechanism operates even at low accretion rates, demonstrating how black holes influence their surroundings regardless of their activity level. The recent discovery of magnetic tornadoes adds another layer to this picture. These structures aren't metaphorical. They're actual rotating columns of magnetized gas, extending outward from the black hole like enormous whirlwinds. The ALMA observations that detected them operate at millimeter wavelengths, specifically chosen to trace the distribution of dust and molecules in the immediate vicinity of the black hole. What makes the tornado analogy APT is the rotational structure. The magnetic fields spiral around the black hole's rotation axis, creating a helical pattern that looks remarkably similar to atmospheric tornadoes on Earth. The physics is completely different, of course. These aren't pressure-driven vortices, but magnetic structures shaped by the black hole's spin and the angular momentum of infalling material. The tornadoes might explain another puzzle. How does Sagittarius A star manage to eject so much material despite being relatively inactive? The answer could lie in these magnetic structures, which act like cosmic conveyor belts, lifting material away from the black hole before it crosses the event horizon. This process removes angular momentum from the disk while simultaneously preventing most of the material from actually feeding the black hole. Testing this hypothesis requires detailed comparison between observations and simulations. Computational models of magnetized accretion have become increasingly sophisticated, running on supercomputers and incorporating the full complexity of general relativistic magnetohydrodynamics. These simulations can reproduce many features seen in actual observations, from the overall structure of the accretion flow to the timing and brightness of individual flares. But simulations have limitations. They require assumptions about initial conditions, magnetic field strengths, and turbulent viscosity. Different choices produce different outcomes, and it's not always clear which assumptions best match reality. This is where multi-wavelength observations become crucial. They provide independent constraints that help narrow down the parameter space, ruling out models that don't match the data. The flare observations are particularly constraining. Sagittarius A star produces 5 to 6 major flares per day, each lasting anywhere from minutes to hours. The exact timing and brightness distribution of these flares depends on the physical conditions in the accretion flow. Models that predict too many flares, or flares that are too bright, can be eliminated. Models that match the statistical properties provide insight into the underlying physics. Recent observations from the James Webb Space Telescope added a new dimension to flare studies by detecting mid-infrared emission for the first time. This wavelength regime traces slightly cooler material than the near-infrared observations that have been standard for years. The Webb detection suggests that flares involve larger volumes of gas than previously thought, extending further from the black hole and cooling as they expand. All these observations feed into a growing realization. Sagittarius A star isn't just a point mass sitting quietly at the galaxy's center. It's an active, dynamic system constantly processing material through complex electromagnetic interactions. The fact that we can study it in such detail, watching individual flares and tracking the motion of gas clouds week by week, represents an unprecedented opportunity in astrophysics. No other black hole can be studied with comparable resolution. Even M87 star, despite being imaged first and producing spectacular jets, remains too distant for the kind of detailed time-resolved observations possible with Sagittarius A star. Our galactic center provides the only laboratory where we can watch black hole physics unfold in real time, testing theoretical predictions against direct observations. Which raises an important question about the future. What comes next in our study of the galactic center? The technology continues improving. Adaptive optics systems become more sophisticated. Interferometric arrays add more telescopes and longer baselines. X-ray observatories achieve better sensitivity and time resolution. Each advance reveals finer details, pushing our understanding deeper. One instrument on the horizon deserves special attention. The next generation Event Horizon Telescope, currently in planning stages, will incorporate more stations, wider frequency coverage, and improved sensitivity. This enhanced array could produce movies instead of static images, tracking the motion of hot spots as they orbit the black hole. Imagine watching plasma blobs spiral inward, frame by frame, as they approach the point of no return. The scientific value would be extraordinary. But there's a challenge unique to Sagittarius A star that makes imaging harder than you'd expect. The black hole's accretion flow varies on timescales of minutes. During the hours needed to collect data from telescopes around the globe, the source changes its appearance. It's like trying to photograph someone who won't hold still. The image you eventually reconstruct represents an average over time, blurring out rapid variations that might reveal crucial physics. M87 star, despite being vastly more distant, actually proved easier to image because its accretion disk evolves much more slowly. The larger mass means longer orbital periods and more stable emission. For Sagittarius A star, the rapid variability requires new analysis techniques that can account for time-dependent structure. Researchers have developed methods to model the changing brightness patterns, essentially creating multiple snapshots from the same dataset and stitching them together into a coherent picture. The next decade will likely bring several major advances. Orbital monitoring will continue, with star S4714 providing particularly interesting data as it makes repeated close approaches. Each pass tests general relativity under increasingly extreme conditions. If deviations from Einstein's predictions exist, they should show up in the precise timing and trajectory of these ultra-close orbits. Flare monitoring will become more systematic. Instead of occasional observations when telescope time becomes available, dedicated programs will track Sagittarius A star continuously for extended periods. This sustained coverage will capture the full statistical distribution of flare properties, constraining models of magnetic reconnection and particle acceleration near the event horizon. Polarization observations will map magnetic field structure in unprecedented detail. The Event Horizon Telescope can already measure polarization, but future observations with improved calibration and more stations will produce sharper maps showing exactly how magnetic fields thread through the accretion flow. This addresses one of the biggest unknowns in black hole physics, the role of magnetic fields in controlling matter inflow and outflow. Gravitational wave astronomy might even contribute. Current detectors aren't sensitive to the frequencies that stellar mass objects orbiting Sagittarius A star would produce, but future space-based observatories could potentially detect gravitational radiation from inspiraling compact objects. This would provide a completely independent measurement of the black hole's mass and spin, cross-checking results from electromagnetic observations. All these future observations connect to bigger questions about galaxy evolution. Supermassive black holes don't exist in isolation. They grow alongside their host galaxies through complex feedback processes that we're only beginning to understand. The black hole's gravity influences stellar orbits out to large distances. Jets and winds, when active, can heat or expel gas that might otherwise form stars. The relationship between central black hole mass and galaxy properties hints at deep connections between these phenomena. Sagittarius A star's current quiescence makes it unusual among supermassive black holes. Most galaxies at similar distances show evidence of more vigorous accretion, with bright nuclei and sometimes spectacular jets. Our black hole seems to be starving, fed only by occasional stellar winds and small gas clouds wandering too close. Why? Part of the answer might lie in the Milky Way's history. Major galaxy mergers tend to funnel gas toward the center, feeding the central black hole and triggering intense activity. The Milky Way hasn't experienced a major merger in several billion years, leaving Sagittarius A star with limited fuel. Small satellite galaxies have merged with us more recently, but they don't deliver enough gas to the very center to wake the black hole from its slumber. The recent discovery of an ancient eruption changes this picture somewhat. A few hundred to 1,000 years ago, Sagittarius A star blazed 10,000 times brighter than today. What triggered that outburst? Perhaps a gas cloud or disrupted star provided temporary fuel, or maybe we're seeing the tail end of episodic accretion cycles that occur naturally in low-luminosity systems. The XRISM observations that revealed this event represent just the beginning of studying the black hole's past behavior through light echoes. Understanding these eruptions matters for galactic evolution. Even brief periods of enhanced activity can significantly impact the surrounding environment. High-energy radiation and particle outflows heat nearby gas, potentially suppressing star formation in the central region. Over cosmic time, multiple such episodes could shape the distribution of matter throughout the inner galaxy. Looking even further ahead, new technologies will enable observations currently impossible. Quantum sensors might detect subtle gravitational effects with unprecedented precision. Neutrino telescopes could potentially observe high-energy neutrinos produced in the accretion flow, providing a completely different window into the physics near the event horizon. Advances in computing power will allow ever more detailed simulations, incorporating additional physics and running at higher resolution. One particularly exciting prospect involves using pulsars as probes of spacetime. Several pulsars orbit in the galactic center region, though none as close as the stars being tracked optically. If a pulsar were discovered in a tight orbit around Sagittarius A star, its radio pulses would provide exquisitely precise measurements of orbital motion and gravitational effects. The regular ticking of a pulsar acts like a natural atomic clock, revealing tiny deviations caused by the black hole's gravity. The search for such objects continues. Pulsars are faint and easily missed in surveys, especially in the crowded and obscured galactic center. Dedicated radio monitoring programs sweep the region regularly, looking for the characteristic periodic signals. Finding even one pulsar in a close orbit would revolutionize black hole studies, enabling tests of general relativity far more stringent than anything currently possible. Beyond pure science, Sagittarius A star serves another role. It anchors our understanding of cosmic scales and the nature of extreme physics. Every measurement, every image, every observation contributes to humanity's expanding knowledge of the universe. The black hole at our galaxy's heart represents the nearest example of phenomena that occur throughout the cosmos, from the centers of distant quasars to the merging black holes that produce gravitational waves. As technology progresses and observations accumulate, our picture of Sagittarius A star will continue evolving. What seems mysterious today might become routine tomorrow. Phenomena we haven't yet imagined could emerge from future data. The history of astronomy teaches that every improvement in observational capability reveals unexpected discoveries. Consider how far we've come. Less than a century ago, the existence of black holes was pure speculation. 50 years ago, we didn't know for certain that our galaxy harbored a supermassive black hole. 20 years ago, we couldn't track individual stars orbiting it. Today we have an image of the event horizon itself and are mapping magnetic tornadoes in the accretion flow. What will the next 20 years bring? Perhaps movies of the accretion disk. Maybe detection of gravitational waves from inspiraling objects. Possibly evidence of a weak jet or detailed measurements of spacetime curvature. The only certainty is that Sagittarius A star will continue surprising us, revealing new aspects of black hole physics with each technological advance. The black hole at our galaxy's center stands as both a destination and a beginning. Every answer generates new questions. Every observation opens new avenues of investigation. This 4 million solar mass object, sitting 26,000 light-years away, represents one of the richest laboratories in all of astrophysics. And we've only just started exploring it. The story of Sagittarius A star is far from finished. We've spent decades discovering what it is, years learning how it behaves, and we're only now beginning to understand what it means. This black hole doesn't exist as some isolated curiosity at the galaxy's center. It's the gravitational anchor for everything around us, the central mass that keeps hundreds of billions of stars, including our own sun, locked in their cosmic orbits. Every observation reveals something unexpected. The magnetic tornadoes weren't predicted by theory. The ancient eruption caught everyone by surprise. The similarity between our relatively tiny black hole and the monster at M87 center challenges assumptions about how these objects work. Even the simple fact that Sagittarius A star remains so quiet despite sitting in a region rich with potential fuel continues puzzling researchers. What makes this ongoing investigation so valuable is proximity. At 26,000 light-years away, Sagittarius A star sits close enough that we can resolve details impossible to see in more distant black holes. We can track individual stars completing their orbits in real time. We can watch flares emerge and fade over the course of hours. We can measure how spacetime curves near the event horizon with precision unmatched anywhere else in the universe. Other galaxies host larger black holes, more active black holes producing spectacular jets visible across cosmic distances. But none of them can be studied with the intimacy our galactic center allows. M87 star, despite its fame as the first black hole ever imaged, remains a distant giant. We see its overall structure but miss the fine details that reveal how black holes actually work moment to moment. The discoveries keep coming because the technology keeps improving. The Event Horizon Telescope will add more stations, improving resolution and enabling time-resolved imaging. Adaptive optics systems will achieve sharper views of the stellar orbits. X-ray observatories will track flares with better sensitivity. Each improvement pushes our understanding deeper into the physics of extreme gravity. But perhaps the most important realization is this. Sagittarius A star represents a system fundamentally different from what early theories predicted. Black holes were once thought to be simple objects, described completely by just their mass and spin. The reality involves complex magnetic fields, turbulent accretion flows, episodic eruptions, and feedback mechanisms that regulate feeding efficiency. The magnetic tornadoes demonstrate that even quiet black holes maintain complex electromagnetic structures. The ancient eruption proves that current behavior doesn't predict future activity. The similarity to M87 star suggests universal principles governing all supermassive black holes despite vast differences in mass and environment. These aren't isolated facts, but pieces of a larger picture still coming into focus. Looking forward, the questions multiply faster than answers arrive. Will we detect a hidden jet once instruments become sensitive enough? What triggers the episodic eruptions that apparently occur every few centuries? How do the magnetic fields actually transport angular momentum through the accretion disk? Can we find a pulsar in a close orbit to provide even more precise tests of general relativity? Each question leads to others. Understanding the magnetic field structure requires better polarization measurements, which demand improvements to interferometric techniques. Predicting future eruptions means modeling the supply of gas to the inner accretion zone, which requires mapping the distribution of material throughout the central parsec. Every advance opens new territory for investigation. The broader implications extend beyond our galaxy. Supermassive black holes occupy the centers of most large galaxies throughout the universe. Understanding Sagittarius A star provides insights into how these objects form, grow, and influence galactic evolution everywhere. The feedback mechanisms operating in our galactic center probably operate in distant galaxies billions of light-years away, shaping cosmic structure on the largest scales. There's something profound about studying an object we'll never visit, never sample directly, never examine except through photons that travel 26,000 years to reach our instruments. Everything we know about Sagittarius A star comes from watching light that began its journey toward Earth before human civilization existed. The photons captured by the Event Horizon Telescope left the galactic center while mammoths still walked the Earth. Yet from those ancient photons, we've reconstructed the geometry of spacetime near the event horizon. We've measured the black hole's mass to exquisite precision. We've mapped magnetic fields and tracked plasma motions. We've tested Einstein's theory under conditions he never imagined. The black hole reveals itself not through direct observation but through its influence on everything around it. That's the nature of studying extreme physics. You can't bring a black hole into the laboratory. You can't experiment with different parameters to see what happens. The universe provides the laboratory, and we observe what nature chooses to reveal. Sagittarius A star happens to be positioned perfectly for detailed study, close enough to resolve, massive enough to be interesting, yet quiet enough that the surrounding environment remains stable. The coming decades will bring observations that seem impossible today. Technology marches forward relentlessly. Detectors become more sensitive. Telescopes achieve better resolution. Analysis techniques grow more sophisticated. What we learn from the next generation of observations will likely reshape our understanding as profoundly as the Event Horizon Telescope image did. But some mysteries might persist. We may never witness another major eruption like the ones RISM detected through its light echo. Human lifetimes, even human civilizations, represent mere instants compared to the timescales on which Sagittarius A star operates. We're studying a system that changes on scales of centuries, millennia, millions of years. Our observations capture brief snapshots of a process vastly longer than recorded history. That limitation makes every observation more precious. We can't run the experiment again. We can't ask the black hole to repeat an interesting behavior. We get one chance to capture each event, and if we miss it, the opportunity vanishes perhaps for thousands of years. This urgency drives the continuous monitoring campaigns, the coordinated observations, the push for better instruments. The black hole at our galaxy's center will outlive our sun. Long after Earth becomes uninhabitable, long after the sun exhausts its nuclear fuel, Sagittarius A star will continue orbiting through the galaxy, occasionally feeding on whatever material wanders too close, erupting when circumstances align just right. It's existed for billions of years and will exist for trillions more, an almost eternal fixture of our cosmic neighborhood. Yet for this brief moment in cosmic history, we're here to observe it. An intelligent species evolved on a planet orbiting an ordinary star in one of the galaxy's spiral arms, and that species developed the technology to peer into the heart of its galaxy and understand what lurks there. We're watching the black hole that holds our galaxy together, measuring its properties, testing fundamental physics in its vicinity. Future observers, whether human descendants or entirely different intelligences, will build on what we've learned. They'll have better instruments, more complete theories, deeper understanding. But they'll also look back at these early observations, the first image, the first detection of magnetic tornadoes, the first stellar orbit measurements, as the foundation everything else was built upon. We're living through the opening chapter of humanity's relationship with the black hole at our galaxy's center, and that story has barely begun.
Right now, 642 light-years away, a star is dying. Not gradually fading over billions of years, but preparing for one of the most violent events the universe can produce. And we're watching it happen in real time. Betelgeuse. The name alone carries weight in astronomy circles. This red supergiant marks the shoulder of Orion, visible to anyone who looks up on a winter night. For thousands of years, it glowed steadily. Then in late 2019, something changed. The star dimmed, dramatically. Astronomers scrambled to their instruments, because they knew what this might mean. A supernova. An explosion so powerful it would briefly outshine every other star in our galaxy combined. Visible during the day, casting shadows at night. A celestial event that happens maybe once per century in a galaxy like ours, and we might be about to witness it. But here's what makes this genuinely unsettling. We have no idea when. Could be tonight. Could be 100,000 years from now. The light we see left Betelgeuse in the 1380s, when the Ming Dynasty was just beginning. If it exploded tomorrow, it actually happened during the Renaissance, and we're only now receiving the news. The star itself is almost incomprehensible in scale. Place it where our Sun sits, and its surface would extend past the orbit of Jupiter. Every second, Betelgeuse burns through mass equivalent to Earth's moon. It's so large that its outer atmosphere is actually cooler than the deeper layers we can detect, creating convection cells the size of our entire solar system. Scientists discovered something else recently. The dimming in 2019 wasn't just a fluke. Betelgeuse had ejected a massive chunk of its own surface into space. A piece of star, flung outward, temporarily blocking our view. The sheer violence required to tear that much material away from a supergiant's gravity suggests internal processes we're only beginning to understand. Stellar physics gives us the framework. Betelgeuse is fusing heavier and heavier elements in its core. Hydrogen is long gone. Helium, exhausted. Now it's burning carbon, oxygen, silicon. Each stage happens faster than the last. Silicon fusion, the final step before catastrophe, takes about 1 day. 1 day between normalcy and detonation. The core contracts under its own gravity. Temperatures spike. Pressures mount. Eventually, even silicon can't hold back the collapse. In less than a second, the core implodes, then rebounds. The shock wave tears through millions of kilometers of stellar material. What took millions of years to build destroys itself in hours. That's the supernova. But the story doesn't end with the explosion. What remains is stranger. The core, compressed beyond anything we experience in everyday physics, becomes either a neutron star or a black hole. In Betelgeuse's case, given its mass, we're likely looking at a black hole. A point in space where gravity is so extreme that not even light escapes. The entire mass of a star, compressed into a region smaller than a city. Meanwhile, the outer layers race outward at roughly 10% the speed of light. This expanding shell carries every element the star forged over its lifetime. Iron, gold, uranium, everything heavier than helium. These materials will eventually seed new star systems, new planets, possibly new life. Every atom in your body heavier than hydrogen was created in a star that died before our sun was born. The supernova remnant becomes a nebula. Glowing debris spreading across light years, enriching the interstellar medium. Within these clouds, gravity begins pulling material together again. The cycle continues. Now consider what this means for us. At 642 light-years, Betelgeuse is close. Not dangerously close, but close enough to matter. When it goes, we'll see effects beyond just a bright light in the sky. The explosion releases more than visible light. Gamma rays, X-rays, ultraviolet radiation, all pour out in the initial burst. Earth's atmosphere will absorb most of this, but satellites might not fare as well. Communication systems could experience disruptions. GPS might lose accuracy. Nothing catastrophic, but noticeable. Then there's the neutrino flux. These ghostly particles barely interact with matter, but a supernova produces them in staggering numbers. Trillions will pass through your body every second for weeks. Detectors worldwide will register the surge, giving astronomers unprecedented data about the explosion's mechanics. The visible brightness is what captures imagination, though. At peak, Betelgeuse will reach apparent magnitude -12, roughly as bright as a half-moon. You'll see it during the day. At night, it'll cast noticeable shadows. For weeks, possibly months, our sky will have two moons, one white, one red. Cultures throughout history have marked supernovae. The 1006 event was recorded on three continents. The 1054 explosion created the Crab Nebula and appeared in Chinese and Middle Eastern texts. Native Americans left pictographs depicting it. These weren't just scientific observations but events that shaped mythology and worldview. What happens to us when Betelgeuse goes? Nothing physically dangerous, but something profound psychologically. We'll have front-row seats to cosmic violence on a scale that makes our largest nuclear weapons look like firecrackers. It'll be a reminder, visible every night, that the universe operates on timescales and energy scales that dwarf human concerns. Astronomers are preparing. Telescopes across every wavelength stand ready. When the light arrives, we'll have perhaps hours of warning from neutrino detectors before the visible light reaches us. Every major observatory will pivot to Orion. This will be the most studied astronomical event in human history. The data will be invaluable. We've never observed a supernova this close with modern instruments. Our models of stellar evolution, nuclear physics, even general relativity, will face their most rigorous test. Whatever we think we know about how massive stars die, Betelgeuse will either confirm it or force us back to the drawing board. There's also the question of what we'll find afterward. The neutron star or black hole left behind will be young, hot, energetic. We might detect pulsar emissions, jets of material shooting from the poles at near light speed. The nebula itself will be a laboratory for studying shock physics, dust formation, and chemical enrichment of space. But I mentioned earlier that the timing is uncertain. Let's dig into why that's so frustrating. Stellar models tell us Betelgeuse is near the end. Its behavior, the dimming events, the mass loss, all point to a star in its final stages. But final stages, for a supergiant, might mean tomorrow or 100,000 years from now. The physics becomes chaotic. Small changes in core conditions produce wildly different outcomes. We're essentially trying to predict the exact moment a Jenga tower falls. We know it's unstable. We can see pieces missing. But that final trigger, the precise instant when structural integrity fails completely, that's incredibly difficult to forecast. The 2019 dimming gave us hope for better predictions. If we could understand what caused it, maybe we could identify pre-supernova signatures. The research that followed revealed the surface ejection, but also showed us how much we still don't know. Betelgeuse is variable on multiple timescales. It pulsates. It sheds mass irregularly. Separating normal variability from end-stage behavior is like diagnosing a patient whose symptoms keep changing. Some astronomers think we're seeing the final centuries. Others argue we might have tens of thousands of years left. The uncertainty stems from how we measure stellar evolution. We can't watch a single star age. We observe millions of stars at different life stages and piece together the sequence. It's like understanding human aging by taking snapshots of random people and arranging them by apparent age. You'll get the general progression right, but predicting any individual's remaining lifespan becomes much harder. Recent observations added another wrinkle. Betelgeuse might have a companion star. If true, the dynamics change completely. Binary interactions can trigger supernovae earlier than expected, or delay them, or create entirely different outcomes. We thought we understood this star, and then realized we might have been looking at a system, not a singleton. The implications stretch beyond academic curiosity. Understanding supernovae helps us understand galactic evolution, element formation, even cosmology. Type Ia supernovae, a different class from what Betelgeuse will produce, serve as distance markers across the universe. They helped us discover that cosmic expansion is accelerating, leading to the concept of dark energy. Getting the physics right matters for our entire picture of how the universe works. And there's something else. Something that connects directly to why this particular star captures our attention beyond the scientific interest. Human timescales collide with cosmic timescales in strange ways. Betelgeuse might explode while you're reading this. Or it might wait until our civilization is dust. From the universe's perspective, there's no difference. A few thousand years either way is a rounding error. But for us, the difference between witnessing this event and having it remain theoretical is everything. We stand at a unique moment. We had the technology to study a nearby supernova in detail, but we lack the ability to predict when it'll happen. Our instruments are ready. Our models are sophisticated. But nature keeps its schedule, indifferent to our preparations. There's a philosophical tension here that's worth examining. We study the universe by observing light that left its source years, centuries, or millennia ago. When we look at Betelgeuse, we're seeing photons that began their journey around 650 years ago, give or take. The star might have already exploded. The shockwave could be racing toward us right now, and we wouldn't know until the light arrives. This isn't speculation. It's the fundamental constraint of information traveling at light speed. We're always looking backward in time. That delay creates an odd psychological state. Astronomers monitoring Betelgeuse know that the supernova they're waiting to observe might have already happened during the Middle Ages. The light carrying that information could arrive next week, or next century. There's no way to check. No faster-than-light telephone line to call and ask if the star is still there. We wait, instruments ready, knowing that the event we're preparing for might be a historical fact we just haven't learned about yet. Let's shift perspective for a moment. What would it actually look like from Earth? The first indication would come from neutrinos. These ghostly particles barely interact with matter, which means they stream out from the core collapse essentially unimpeded. Neutrino detectors around the world, designed primarily for particle physics research, would register a sudden spike. These facilities are networked specifically for this purpose. When one detector sees an anomalous burst, it alerts the others. If multiple detectors confirm simultaneously, astronomers worldwide get an automated notification. Supernova imminent. Look up. The neutrino warning would give us maybe a few hours head start. Possibly a day. Then the light would arrive. Not gradually. Supernovae brighten dramatically, exponentially. Within hours, Betelgeuse would go from roughly magnitude 0 to potentially magnitude -11 or 12. For context, the full moon sits at magnitude -13. We're talking about a single point of light nearly as bright as the moon, visible in broad daylight. Orion would be unrecognizable. The constellation would have a second sun blazing where the hunter's shoulder used to be. That peak brightness would last weeks, maybe months, then a slow decline over years. But even after fading, Betelgeuse would remain visible to the naked eye for potentially decades. The expanding debris cloud would eventually form a nebula, visible through telescopes for thousands of years. This isn't a brief light show. It's a multi-generational transformation of our night sky. The scientific return would be staggering. Every telescope on Earth and in orbit would immediately swing toward Orion. We'd capture the light curve with unprecedented detail, tracking how brightness changes second by second. Spectroscopy would reveal the composition of ejected material, testing our models of nucleosynthesis. Did the supernova produce the expected ratios of elements? Are there surprises in the chemical signature? X-ray and gamma-ray observations would probe the shock wave physics. Radio telescopes would track the expanding shell as it plows into surrounding material. And then there's the neutrino data itself. These particles carry information about the core collapse that light cannot provide. Light gets trapped, bounced around, delayed by the dense stellar material. Neutrinos escape immediately, carrying direct information about nuclear reactions in the collapsing core. Detecting them in large numbers would let us peer into physics we can't access any other way. The temperature, the density, the exact sequence of nuclear processes, all encoded in the neutrino spectrum and timing. Previous nearby supernovae were observed with far more primitive instruments. Supernova 1987A in the Large Magellanic Cloud, while spectacular, occurred before we had modern detector networks. We caught neutrinos, which was revolutionary, but with limited sensitivity. We got optical observations, but without the resolution and wavelength coverage we have now. Betelgeuse would be the first nearby supernova in the era of space telescopes, gravitational wave detectors, and coordinated global observation networks. The data haul would rewrite textbooks. But there's something else happening alongside the scientific opportunity: cultural impact. Betelgeuse going supernova would be the most dramatic astronomical event in human history, at least in recorded history. The 1006 supernova was brighter, but occurred before the scientific revolution. Ancient observers recorded it with awe but without understanding. The 1054 supernova created the Crab Nebula. Chinese astronomers documented it. Indigenous peoples across the Americas incorporated it into their traditions. But again, no scientific apparatus to study it properly. A supernova in Orion would reach everyone. You can't miss Orion. It's visible from almost everywhere on Earth. Every culture recognizes it. Suddenly, that familiar pattern would change. Children would grow up with a sky that looks different from the one their parents knew. Photographers would capture the light illuminating landscapes. Artists would respond. Writers would find metaphors. The supernova would become part of human culture in ways we can't fully predict. There's precedent for celestial events capturing public imagination, though nothing quite at this scale. Comet Hale-Bopp in 1997 became a cultural phenomenon. People who never looked up started watching the skies. But Hale-Bopp was a visitor, here and gone. Betelgeuse would be a permanent change. The supernova would fade, but the sky would remain altered. We'd live with the consequence, the glowing remnant, for the rest of our species' existence. Now, let's address something often glossed over in popular discussions. Could this actually be dangerous? The short answer is no, but the reasoning matters. Supernovae release tremendous energy, including gamma rays. At close range, within a few dozen light years, a supernova could potentially damage a planet's atmosphere. The gamma rays would interact with atmospheric molecules, creating nitrogen oxides that deplete ozone. Without ozone protection, surface life would face increased ultraviolet radiation from the star. Betelgeuse is too far away for this to be a concern. The inverse square law is brutal. Intensity drops with the square of distance. At 650 light-years, the gamma-ray flux reaching Earth would be negligible. Detectable, certainly. Scientifically valuable, absolutely. But not hazardous. We'd receive more radiation from eating a banana than from Betelgeuse's supernova. This isn't speculation. We can calculate these things precisely. The physics is well understood. Some articles sensationalize this, either through misunderstanding or for clicks. You'll see headlines about killer stars or cosmic threats. It's nonsense. Real astronomers aren't concerned about danger. They're excited about the scientific opportunity. The distinction matters because public misconceptions about astronomy can undermine science communication. We need people to understand that space, while genuinely dangerous in many ways, doesn't threaten us with random nearby supernovae. The galaxy isn't that hostile. What could genuinely affect us is more subtle. The supernova's effect on the solar wind dynamics, perhaps. Earth's magnetosphere protects us from charged particles streaming from the sun. A supernova would add a temporary burst of high-energy particles to the cosmic ray background. Our magnetosphere would handle it, but satellites might experience slightly elevated radiation. Nothing catastrophic. Maybe some temporary communication disruptions. GPS might lose accuracy. ISS would need to monitor exposure levels. Astronauts might need to shelter in more shielded areas during peak flux. Again, manageable. Not apocalyptic. The real challenge would be observation coordination. Every major observatory would want time on every major telescope. Conflicts would arise. Who gets priority? How do you balance spectroscopic observations against photometric monitoring, against polarimetry, against imaging? Normally, telescope time is allocated months or years in advance through competitive proposals. A supernova would trigger directors' discretionary time at every facility, overriding scheduled observations. Some astronomers would be thrilled. Others, whose carefully planned observations get bumped, less so. There's also the amateur astronomy community to consider. Betelgeuse is bright enough that backyard telescopes could contribute real data. In fact, amateur observations might prove crucial for continuous monitoring. Professional telescopes can't watch one target constantly. They need to split time between multiple objects, multiple projects. Amateurs, coordinating globally, could maintain near-continuous coverage. We saw this work effectively with other transient events. The amateur community has become genuinely valuable for time-domain astronomy. Social media would transform the experience compared to historical supernovae. Real-time updates, images, data, all shared instantly worldwide. Scientists could communicate findings directly to public audiences. Misinformation would also spread rapidly, of course. Distinguishing signal from noise would be challenging. But overall, the transparency would be unprecedented. You'd be able to follow the supernova's evolution as it happens, explained by experts, discussed by millions. Educational impact deserves mention. A visible supernova would provide a teaching moment like no other. Students could observe with their own eyes a phenomenon they'd only read about. Teachers could connect textbook physics to something happening overhead. The abstract becomes concrete. Kai ban ko the chi te veo no. Bao tung qua ha kasi ze dung kak kuok trian lam. Kak kung thien van se kap not kak bui trin dying qua ho. Su kien nai se trian kam hung cho mot the he kak na thien van hoc. Jong nu chuang trin apollo de trian kam hung cho kak the he na qua hoc va ky su truok day. But we keep circling back to the central frustration. When? We have this extraordinary opportunity ahead of us, maybe. Or maybe not for 100,000 years. The uncertainty undermines planning. Observatories can't keep resources on standby indefinitely. Research teams can't maintain readiness for decades. Funding agencies want timelines. Yet the universe doesn't provide them. Betelgeuse will explode on its own schedule, indifferent to our preparations or impatience. We've built the instruments. We've developed the theory. We've coordinated the networks. Now we wait. And waiting, in astronomy, often defines the job more than the observations themselves. What we do know is that Betelgeuse isn't behaving like other red supergiants we've studied. Most stars in this phase show relatively predictable brightness variations. Long-period pulsations, yes. But within expected ranges. Betelgeuse keeps surprising us. The great dimming of 2019 to 2020 caught everyone off guard. The star's brightness dropped to around 40% of normal. Some astronomers genuinely wondered if we were watching the prelude to explosion. Spectroscopic analysis eventually revealed the truth. Betelgeuse had ejected material that condensed into dust, temporarily blocking our view. The star itself hadn't actually dimmed that dramatically. We were seeing an obscuration event. But that explanation raises its own questions. Why did Betelgeuse eject that much material at that particular time? Red supergiants lose mass continuously through stellar winds. The rate varies, certainly, but that particular ejection seemed unusually vigorous. Was it a surface convection event? Some models suggest that massive convection cells in red supergiant envelopes can bring hot material to the surface, creating localized bright spots. When those regions rotate out of view, the star appears dimmer. Combine that with dust formation and you get dramatic brightness changes. Except we're not entirely certain that's what happened. Alternative models exist. Maybe the dimming involved magnetic activity. Betelgeuse does have a magnetic field, though measuring it precisely is difficult. Could magnetic loops trap material, then release it suddenly? Solar flares operate on this principle, scaled way down. A stellar version might produce the observed effects. We're speculating, though. The truth is we saw something unprecedented and we're still working out what it meant. This uncertainty pervades supernova prediction. We're trying to forecast an event we've never actually witnessed up close in real time with modern instruments. SN 1987A happened in a large Magellanic Cloud, 168,000 light-years away. Close enough to study extensively, far enough that resolution was limited. Betelgeuse at 550 light-years would give us detail we've never had before. But only if it explodes while we're ready. The waiting game has psychological dimensions worth examining. Astronomers dedicate careers to studying objects that might not do anything interesting during their professional lifetime. You could spend 30 years developing expertise in supernova physics and never witness the one event that would define your field. That's the gamble. Some researchers pivot to other topics, hedging their bets. Others commit fully, accepting that the universe operates on timescales indifferent to human careers. There's nobility in that commitment. Also frustration. Imagine explaining to funding committees why your telescope time should go toward monitoring a star that probably won't explode this year. Or next year. Or the year after that. Competing proposals promise guaranteed results. Yours offers a possibility. Funding agencies generally prefer certainty. Yet Betelgeuse observations continue. Not constantly, but regularly. The star remains on monitoring lists. Photometry gets collected. Spectra get recorded. Data accumulates slowly, building a baseline against which any future changes will be measured. That baseline has value regardless of whether Betelgeuse explodes soon. We're learning about red supergiant behavior in unprecedented detail. The variations, the mass loss, the atmospheric dynamics, all of it contributes to stellar evolution models. When the next red supergiant explodes somewhere else, we'll understand it better because of Betelgeuse. The question of what we'd actually see during the explosion deserves more detailed exploration. The initial brightening would be gradual, probably over hours. Neutrinos would arrive first, traveling essentially at light speed and passing through matter almost without interaction. Neutrino observatories around the world maintain constant vigilance for the characteristic burst signature. They'd detect it before anyone saw anything visually. Minutes to hours later, the shock wave from the core collapse reaches the stellar surface. The star's outer layers begin exploding outward. This is when brightness starts increasing dramatically. Over the course of a day or so, Betelgeuse would brighten from magnitude 0.5 to perhaps magnitude -11 or -12. Roughly the brightness of a half-moon, concentrated in a single point. You could read by it at night. Easily. During the day, it would be visible to the naked eye, a bright star hanging in daylight sky. The color would shift too. Betelgeuse appears reddish now because its surface temperature is relatively cool for a star, around 3,500 Kelvin. During the supernova, the expanding material heats up. The color would shift toward white, maybe even slightly blue. The expanding debris would be glowing from the energy of the explosion itself, not from fusion anymore. Peak brightness would last weeks, maybe a couple months. Then gradual fading over years. But even after fading below naked eye visibility, the supernova remnant would remain a target for telescopes for centuries. The expanding shell of debris, glowing in various wavelengths, would evolve constantly. Radio observations would track the shock wave as it plows through surrounding space. X-ray telescopes would study the hot interior regions. Infrared would pierce any dust that forms. Optical telescopes would monitor the overall structure. Each wavelength reveals different physics. The remnant would become a laboratory for studying extreme conditions we can't replicate on Earth. Nuclear physics, particle acceleration, shock wave dynamics, all happening in real time at scales we can actually resolve. Most supernova remnants we study are ancient, their explosions having occurred thousands of years ago. A fresh one at Betelgeuse's distance would be transformative. Consider the scientific papers that would emerge. Hundreds in the first year alone. Thousands over the following decade. Every subfield of astronomy would find something relevant. Stellar evolution theorists would refine their models of red supergiant death. Galactic chemical evolution researchers would study how the explosion enriches surrounding space with heavy elements. Particle physicists would analyze neutrino data to constrain physics beyond the standard model. Cosmologists would use it to calibrate distance measurements, since Type II supernovae serve as standardizable candles under certain conditions. The interdisciplinary reach would extend beyond astronomy. Geologists would look for isotopic signatures in ice cores or sediment layers, markers of cosmic ray exposure from the supernova. Historians might correlate the event with cultural responses, studying how different societies interpret and record the phenomenon. Artists would create works inspired by it. Musicians might compose pieces. The cultural impact would ripple outward in ways we can't predict. But there's a darker consideration that occasionally surfaces. What if we're wrong about the safety? Not about the distance, that's measured reliably, but about the radiation effects. Current models say we're safe. Models have been wrong before. The ozone layer might be more vulnerable than we think. Or the magnetosphere less protective? Unlikely, yes. Our understanding of these systems is solid. But certainty in science always comes with error bars. The responsible position is acknowledging what we don't know while being clear about what we do. We're confident Earth is safe from catastrophic effects. Confident, not absolutely certain. That distinction matters. Scientists who claim absolute certainty lose credibility when exceptions emerge. Better to be honest about uncertainty while explaining why we consider the risk negligible. Public communication requires that balance. Climate scientists face this challenge constantly. How do you convey high confidence without claiming perfection? How do you acknowledge uncertainty without undermining the message? With Betelgeuse, the stakes are lower because we're not asking anyone to change behavior. No policy decisions hinge on supernova predictions. But the communication challenge remains. Media coverage of Betelgeuse tends toward sensationalism. Headlines scream about stars exploding near Earth, implying danger where none exists. Scientists issue corrections. The cycle repeats. Each brightening fluctuation triggers another round. After a while, public attention drifts. The boy who cried wolf effect takes hold. When the supernova actually happens, will people care? Or will they assume it's another false alarm? Maintaining public interest over uncertain timelines is nearly impossible. The first few times Betelgeuse dims or brightens unusually, media covers it extensively. By the 10th time, it's old news. Editors reject the story. The public assumes nothing real is happening. Then one day, it actually explodes, and everyone's surprised despite decades of warnings. This dynamic frustrates science communicators. How do you keep people informed without exhausting their attention? Some researchers have stopped doing media interviews about Betelgeuse entirely. The questions are always the same. Is it exploding now? When will it explode? What will we see? The answers never satisfy because they involve uncertainty. Journalists want definitive statements. Scientists offer probabilities and caveats. The disconnect is fundamental. Yet when the explosion happens, those same researchers will be flooded with interview requests. Everyone will want expert commentary. The preparation happening now, the monitoring, the theoretical work, the instrument development, all of it will suddenly become urgent and newsworthy. The irony is that the real scientific value lies in the preparation, not the event itself. The supernova will be spectacular, certainly. But the decades of work leading up to it, building our understanding of stellar evolution, developing detection capabilities, training new generations of astronomers, that's where the lasting impact lives. Betelgeuse will eventually teach us something we can't predict. Every major astronomical event does. When gravitational waves were first detected, nobody expected the precision with which we could measure neutron star mergers. The technology worked better than anticipated. The data revealed phenomena theorists hadn't considered. Supernova 1987A taught us about neutrino physics in ways no one foresaw. The neutrino burst arrived hours before the light, exactly as predicted. But the detailed measurements refined our understanding of particle interactions inside collapsing stars. Models improved. New questions emerged. Betelgeuse will do the same, just in different ways. Perhaps we'll discover unexpected asymmetries in the explosion. Maybe the dust production will challenge our models of element formation. The neutrino signal might contain surprises. We won't know until it happens. This uncertainty is what makes the event scientifically valuable. If we could predict everything perfectly, there'd be no point in observing. Science advances through surprises, through data that doesn't quite match expectations. Those mismatches force us to reconsider assumptions, revise theories, build better models. The process is iterative and endless. Consider the stellar evolution models we use. They're sophisticated, incorporating decades of research. But they're still approximations. Real stars are messier than equations suggest. Convection patterns inside Betelgeuse are turbulent and chaotic. Our models smooth them out, treating them statistically. That works for predictions but misses fine details. When Betelgeuse explodes, we'll see whether those details mattered. Did the asymmetric convection create asymmetric explosions? Did rotation play a bigger role than we thought? These questions have answers we can't access until the event occurs. Some researchers are already planning follow-up studies for decades after the supernova. The expanding remnant will be visible for centuries. Its evolution will test our understanding of how supernova remnants interact with surrounding material. Currently, we study old remnants from supernovae that exploded centuries or millennia ago. With Betelgeuse, we'll watch one develop from the beginning. That temporal coverage is rare and valuable. The remnant will sweep up surrounding gas, heating it, compressing it, possibly triggering new star formation. These processes occur in every supernova remnant. But observing them in real time, with modern instruments, will provide unprecedented detail. Computer simulations can be compared directly to observations. Models will improve. Future predictions will become more accurate. There's also the question of what Betelgeuse leaves behind. Supernovae from stars this massive typically produce neutron stars. But some create black holes instead. The boundary between these outcomes isn't perfectly understood. It depends on the star's exact mass, its composition, how much mass it lost before exploding, and details of the collapse process. Current estimates suggest Betelgeuse might be right on that boundary. If it produces a neutron star, we'll have a new pulsar to study. If it forms a black hole, that's equally interesting. Either way, the remnant will teach us about the final moments of massive stellar cores. Neutron stars are extreme physics laboratories. Densities exceed atomic nuclei. Magnetic fields reach unimaginable strengths. Matter behaves in ways we can't reproduce on Earth. Every new neutron star adds to our understanding. Black holes are equally fascinating but harder to study directly. We'd infer its presence through effects on surrounding material. Gas falling toward it would heat up, emitting X-rays. Over time, the black hole might accrete enough material to become visible through those emissions. But that takes years or decades. Immediate detection would rely on gravitational wave observatories. If Betelgeuse's core collapse is asymmetric enough, it might produce detectable gravitational waves. Current detectors probably aren't sensitive enough at that distance. But future observatories might be. LIGO and Virgo are upgrading. New detectors are being built. By the time Betelgeuse explodes, we might have the capability to detect its gravitational wave signature. That would be extraordinary. We've never detected gravitational waves from a supernova. The asymmetry required is substantial. Most supernovae probably don't produce detectable signals. But if Betelgeuse does, it would open an entirely new window into core collapse physics. We'd learn about the exact moment the core fails, how matter falls inward, how the bounce generates the explosion. These are processes hidden inside the star, invisible to traditional telescopes. Gravitational waves carry information directly from the core. They're not blocked by overlying material. This makes them uniquely valuable for studying supernova interiors. Neutrinos serve a similar purpose. They interact so weakly that they escape the collapsing core almost immediately. The neutrino burst from Betelgeuse will arrive before the light, just like with 1987A. But this time, our neutrino detectors are far more sophisticated. IceCube in Antarctica can detect thousands of neutrinos if predictions hold. Super Kamiokande in Japan will see them too. Multiple detectors worldwide will triangulate the signal, pinning down the exact timing and direction. That coordination will happen automatically once the first detector alerts the network. Within seconds, astronomers globally will know Betelgeuse has exploded. They'll point every available telescope at it. The race will be on to capture the earliest moments. Amateur astronomers will contribute significantly. Professional telescopes can't cover the entire sky simultaneously, but thousands of amateur observers can. The first visible light detection might come from someone's backyard telescope. That's how supernovae are often discovered. Automated surveys catch many now, but amateurs still find them regularly. With Betelgeuse, the amateur community will be watching closely. Many have already planned their observation strategies. They know what equipment to use, what filters to apply, how to record data properly. When the moment comes, they'll be ready. This democratization of astronomy is relatively recent. Decades ago, meaningful contributions required access to major observatories. Now, affordable equipment can capture scientifically valuable data. Amateurs discovered comets, tracked asteroids, monitored variable stars. They've become essential parts of the astronomical community. Betelgeuse's supernova will showcase this collaboration beautifully. Professional astronomers will coordinate with amateur networks. Data will flow in from every continent. The global effort will be unprecedented in scale. And it needs to be. The first hours and days are crucial. That's when the shock wave breaks through the star's surface. That's when we see the initial flash, the rapid brightening, the spectrum changing minute by minute. These early moments constrain models of the explosion mechanism. Missing them means losing irreplaceable information. Automated systems will help. Robotic telescopes can respond within seconds of an alert. They'll begin collecting data before humans even know the supernova started. But human judgment matters too. Deciding which observations to prioritize, which instruments to use, how to adapt to unexpected developments. These decisions require expertise and intuition. The combination of automated systems and human oversight will maximize the scientific return. We're not just waiting passively. Preparations continue constantly. Observation plans are refined. Software is updated. Detector calibrations are checked. Communication networks are tested. When Betelgeuse explodes, everything needs to work perfectly. There's no second chance. Some might wonder why we invest so much effort into one star. The answer is that Betelgeuse represents an entire class of objects. What we learn applies to red supergiants everywhere. These stars are crucial for galactic chemical evolution. They produce and distribute heavy elements. Understanding their life cycles and death throes helps us understand galaxies themselves. Every galaxy contains stars like Betelgeuse. Most are too distant to study individually, but Betelgeuse is close enough for detailed observation. It's a proxy for countless others. The investment in studying it pays dividends across multiple fields. Beyond the science, there's something profound about witnessing cosmic events in human timescales. Most astronomical processes unfold over millions or billions of years. We see only snapshots. Stellar evolution happens too slowly to watch. But supernovae are different. They're fast. A human lifetime might encompass the entire visible phase. That connection between cosmic and human time makes supernovae special. We can experience them, not just study them abstractly. When Betelgeuse explodes, people worldwide will look up and see something genuinely new in the sky. That shared experience will be remarkable. Different cultures will interpret it differently. Some will see it as an omen, others as a spectacle. Scientists will see it as data. All perspectives are valid. The night sky belongs to everyone. Throughout history, bright astronomical events have left marks on human culture. Supernovae recorded by ancient astronomers influenced art and mythology. The 1054 supernova that created the Crab Nebula was documented across multiple civilizations. Betelgeuse will be brighter and closer. Its cultural impact could be substantial. Modern astronomers might create detailed records, but they'll also capture something previous generations couldn't: real-time public engagement. Social media will light up instantly. Images will spread globally within minutes. The scientific community will share observations openly, faster than ever before. This transparency changes how discoveries unfold. Previous supernovae occurred before the Internet age. News traveled through traditional channels, slowly. Professional papers took months or years to publish. By contrast, Betelgeuse's explosion will be documented second by second online. Live streams will show telescopes tracking it. Data will be posted immediately. The entire process becomes visible. Some worry this openness might spread misinformation. Fair concern. Spectacular events attract wild speculation. We'll see claims about danger, about cosmic rays, about effects on Earth. Most will be nonsense. The challenge is separating signal from noise. Education becomes critical. Astronomical organizations are dechuan by kak chien dike thon tin som som. Kai siu tan tin zara, thon tin chin zak kan ko san nai lap tuc. En hung jai tik ro ran v en hung gi dang zara, no ko nia la gi, en hung muan noi him nao kong tun tai. Su min bok fu dao lam jiam su hom lon vanam lan. Because there will be questions. Lots of them. Can the supernova harm us? No, the distance is far too great. Will it affect our weather? Not measurably. Could radiation reach Earth? Negligible amounts, harmless. These answers need to be ready, accessible, repeated often. The physics is straightforward but counterintuitive. 600 light-years sounds close astronomically. In human terms, it's incomprehensibly distant. Light from the explosion travels for 6 centuries before reaching us. Any dangerous radiation disperses across that vast gulf. By the time it arrives, it's weaker than cosmic rays we experience constantly. Neutrinos will arrive first, actually. They pass through matter easily, so they escape the collapsing core before light does. Detectors worldwide will register a sudden burst of neutrinos. This signal arrives hours before the visible brightening. It's the earliest warning possible. Neutrino detectors are already monitoring constantly. They're designed to catch exactly this scenario. When Betelgeuse collapses, detectors will see the neutrino pulse and send alerts automatically. Astronomers will have precious hours to prepare before the light reaches us. Those hours matter immensely. Telescopes can be pointed, exposure started, spectrographs readied. The very first light from the shock breakout is scientifically valuable. It happens fast, just minutes or hours. Being prepared means capturing data that would otherwise be lost forever. This coordination represents decades of planning. Alert systems connecting neutrino detectors to telescopes. Automated response protocols. International agreements on data sharing. All built specifically for rare transient events like this. Betelgeuse will test whether these systems work as designed. Beyond the immediate explosion, there's the aftermath. The supernova remnant will evolve over years and centuries. Initially, it expands rapidly, plowing into surrounding material. This creates shock waves, heating gas to millions of degrees. The remnant glows in X-rays and radio waves. Betelgeuse has already shed significant mass through stellar winds. That material surrounds the star in shells and clumps. When the supernova ejecta slams into this material, complex interactions occur. Shocks reflect and refract. Instabilities develop. The remnant won't be smooth or symmetrical. Studying these interactions reveals how supernovae inject energy into their surroundings. This feedback affects star formation in galaxies. Supernova shocks compress nearby gas clouds, sometimes triggering new stars to form. Other times, the energy disperses clouds, preventing star formation. Both processes shape galactic evolution. Betelgeuse's remnant will be uniquely observable. Most supernova remnants are ancient and distant. We see them thousands of years after the explosion. Betelgeuse offers the opposite, a remnant we can watch from birth. Imaging it yearly will show expansion, structural changes, emission variations. This time-lapse view is unprecedented. Infrared observations will be particularly revealing. Dust forms in the cooling ejecta within months or years of the explosion. This dust glows in infrared, creating a spectacular expanding shell. The dust composition tells us what elements were synthesized in the star and during the explosion itself. Speaking of elements, the periodic table owes much to stars like Betelgeuse. Hydrogen and helium came from the Big Bang. Almost everything else was forged in stars. Carbon, nitrogen, oxygen, iron, gold, uranium. All created through nuclear fusion or supernova explosions. Red supergiants produce elements through multiple processes. Fusion in the core generates elements up to iron. During the supernova, explosive nucleosynthesis creates heavier elements. The shock wave compresses material, driving reactions that wouldn't occur otherwise. Elements beyond iron, those requiring energy input rather than releasing it, form exclusively in these conditions. When Betelgeuse explodes, roughly 10 solar masses of processed material will be ejected. That's an enormous chemical payload. The ejecta will enrich the interstellar medium, mixing into gas clouds. Future generations of stars will incorporate these elements. Planets forming around those stars will contain atoms forged in Betelgeuse. This is how galaxies become chemically enriched over cosmic time. Early generations of stars contained only hydrogen and helium. They produced heavier elements and distributed them via supernovae. Subsequent stellar generations had more metals, enabling different types of stars and planetary systems. Our solar system contains elements from countless previous supernovae. Betelgeuse will continue this cycle. Somewhere, millions of years hence, a planet might form containing atoms from this star. Perhaps that planet will host life. Perhaps beings there will study astronomy, unaware that their very bodies contain material from a star humans once watched. The interconnectedness is profound. We're not separate from cosmic processes. We're participants. The calcium in our bones, the iron in our blood, all created in stellar furnaces and scattered by supernovae. When we observe Betelgeuse, we're studying our own origins. This perspective shifts how we think about astronomy. It's not just distant objects unrelated to us. It's our history, our context, our extended environment. The universe isn't something we live in passively. It's an active, evolving system, and we're part of it. Betelgeuse's supernova will make this tangible. Watching a star die, knowing it's producing elements essential for life, creates a visceral connection. This isn't abstract physics. It's the mechanism that made our existence possible. Educational opportunities abound. Kai siu tan tin zara, wa quan tam den thien van hoc si tang vot. Kak truong hok se dua no veo chuan trin jan day. Kak kung thien van se tau ra kak chuang trin dac beat. Kak by John son so misi lap day kak thin fong. Koen kok nai ko the trian kam hung cho mot the he kak na kwa hok. History shows that astronomical events influence career choices. Many astronomers trace their interest to a specific observation or discovery that captivated them young. Betelgeuse could be that catalyst for thousands of people. The timing is unpredictable, but the impact will be lasting. Some of those inspired individuals might make future discoveries. They might solve problems we haven't identified yet. Science advances through accumulated effort across generations. Betelgeuse's supernova will feed into that ongoing process. There's also artistic inspiration. Throughout history, cosmic events have influenced art, literature, music. The night sky has always been a muse. A bright new star will spark creativity across cultures and disciplines. We'll see paintings, poems, compositions, all responding to this celestial event. Different artistic traditions will interpret it uniquely. Western perspectives might emphasize scientific understanding. Other cultures might focus on spiritual or philosophical dimensions. Indigenous traditions might connect it to existing cosmologies. Each response enriches our collective understanding. Because science doesn't have a monopoly on meaning. Supernovae can be approached from multiple angles. The astrophysics is one layer. The cultural significance is another. The personal, emotional response is yet another. All are legitimate. When Betelgeuse explodes, some people will cry. The night sky they've known their entire lives will change suddenly. A familiar constellation will look different. There's genuine loss in that, even if the star is unimaginably distant. Orion won't be the same. Others will feel excitement, wonder, curiosity. A rare event happening in their lifetime. Something their descendants will ask about. The chance to witness cosmic change directly. Both reactions are valid. The universe doesn't care how we feel about it. But our feelings matter to us. They're part of how we process and integrate experiences. Betelgeuse's supernova will be an experience, not just an observation. Preparation continues. The astronomical community remains vigilant. Betelgeuse could explode tonight. Or it might wait another 100,000 years. Statistically, sooner seems more likely than later, but statistics don't determine individual events. What we do know is that when it happens, we'll be ready. The infrastructure exists. The expertise is available. The coordination is practiced. This will be the most thoroughly documented supernova in history. And then comes the question everyone asks eventually: what happens after? After the initial explosion, after the brightness fades, after the remnant disperses. What's left? At the center, probably a neutron star. Chi loi sup du, kak proton va electron by engian nat voi now, tau ton kak neutron. Ket kwa mot vet the ron koang 20 kilometers, chua koi luong lan han mat troi, duok due tri boi ap sut sui bien neutron. Dula mot trong en hung vet the dai dac not ko the coma kong tiro ton mot lo den. Neutron stars are bizarre. Mot thiat sa phi vat lu sa neutron se non han tai ten tren tre dat. Tron luke bi mat man den muc kak gon nui chi ko the chow vi millimet truok kai sup du. Kak tu truong man not trong vu true. Mot so sa neutron que hong tram lon wa jie. Betelgeuse's neutron star will initially be hot, glowing in X-rays. Over millennia, it will cool and fade. Eventually, it becomes a cold, dark remnant. Still there, still massive, but invisible except through gravitational effects. Unless it becomes a pulsar. Some neutron stars emit beams of radiation from their magnetic poles. As they rotate, these beams sweep through space like lighthouse beams. If a beam is directed toward Earth, we will detect regular pulsations. Hence the name. Whether Betelgeuse's remnant will be a pulsar depends on details we can't predict: the core's rotation rate, the magnetic field strength, the viewing angle. We'll find out when it happens. The supernova remnant itself will expand for tens of thousands of years. Eventually, it merges with the interstellar medium, becoming indistinguishable from the general background. The atoms it scattered will drift through space, perhaps eventually condensing into new stars. Human impact category, minimal. The carbon in those future stars might eventually form planets. On those planets, life might emerge. Intelligent beings might look up at their sky and wonder about the universe. Inside them, atoms that once burned in Betelgeuse. The cosmic recycling program operates on timescales that make human history look like a blink. But here's something most people miss about supernovae. They're not endings. They're transformations. The star doesn't cease to exist, it changes form. Energy, matter, information, all continue. Just differently arranged. Betelgeuse right now contains the future. Elements waiting to be comprehensive. Energy waiting to be released. Stories waiting to be told. When it explodes, none of that disappears. It just moves elsewhere. This connects to something deeper about existence itself. Nothing truly ends. It transforms. The atoms in your body were once inside stars. After you die, they'll become something else. Trees, soil, water, air. Eventually, perhaps, other living things. The boundaries we draw between self and universe are convenient fictions. At the atomic level, we're continuous with everything. Betelgeuse reminds us of this. A star that will die so that new things can live. Not metaphorically. Literally. The supernova creates the raw materials for future complexity. Without stellar death, only hydrogen and helium would exist. No carbon, no oxygen, no iron. No planets, no life, no consciousness. We exist because stars die. That's not poetic language. That's physics. Every element heavier than helium was forged inside stars or during their explosive deaths. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all came from supernovae. We're not just in the universe. We're made of it. Literally composed of stellar corpses. Betelgeuse will add to that treasure. When it exploded, it created elements that don't currently exist anywhere nearby. Those atoms will drift through space for millions of years. Some will be incorporated into new structures. And somewhere, unbelievably in the future, something will exist because Betelgeuse is dead. The scale of this is difficult to internalize. We think in days, years, decades. Maybe centuries if we're historically minded. But stellar evolution operates on timescales where our entire species is a rounding error. Betelgeuse has been a star for roughly 8 million years. It might exist as a neutron star for trillions of years. Our entire civilization could rise, peak, and vanish in the gap between two of its heartbeats. Yet here we are, contemplating it. Tiny creatures on a small planet, understanding something greatly larger and older than ourselves. That's remarkable. We're the universe trying to understand itself. Atoms arranged in such a way that they can contemplate other atoms. Consciousness emerged from matter, then turning around to study the matter it came from. Betelgeuse doesn't know we exist. It's not aware of anything. It's just physics, chemistry, nuclear reactions following inevitable rules. But we're aware of it. We've studied it, predicted its fate, prepared to observe its death. In a sense, we're giving meaning to something that has none inherently. The supernova will happen whether we watch or not. But by watching, we transform it from a physical event into a human experience. We make it mean something. That's what consciousness does. It takes raw existence and converts it into meaning, understanding, story. Some people find this terrifying. The idea that meaning isn't inherent, that we create it ourselves. If the universe doesn't care, if there's no cosmic purpose, what's the point? But consider the alternative. If meaning were predetermined, fixed, universal, we'd be passive recipients. Instead, we're active creators. Every observation, every thought, every response adds to the universe's complexity. Betelgeuse will explode. That's determined by physics. But what it means, how we respond, what we learn, those are up to us. The universe provides raw material. We provide interpretation. And interpretation matters. The way we frame cosmic events shapes how we see ourselves. If we view supernovae as death and destruction, we emphasize loss, endings, fear. If we view them as transformation and creation, we emphasize change, renewal, possibility. Both perspectives describe the same physics, but they lead to different psychological spaces. The scientific perspective offers something valuable here. It doesn't say supernovae are good or bad. It says they're necessary. Without them, we wouldn't exist. They're not tragic or triumphant. They're functional. Part of how the universe operates. There's something freeing in that. Betelgeuse's explosion isn't personal. It's not happening to us or for us. It's just happening. We get to witness it because we exist in the right time and place. That's privilege, not punishment. The countdown continues. Each day, Betelgeuse converts helium to carbon, carbon to oxygen, and oxygen to silicon. Each day, the core shrinks a little. Each day, the outer layers shed more mass. Each day, the inner clock ticks closer to zero. We can't stop it. We can't speed it up. We can only observe and understand. In a universe that often feels chaotic and arbitrary, there's something satisfying about predictable processes. We know what will happen. We just don't know when. That uncertainty is important, though. If we knew the exact date, the supernova would become just another scheduled event. Mark your calendar, set a reminder, watch it happen. But the not knowing keeps us alert. Every clear night could be the night. Every observation could be the last one before everything changes. Amateur astronomers check Betelgeuse regularly. Has it dimmed? Brightened? Changed color? Mostly, it looks the same. But that could change tonight. Or tomorrow. Or next year. The very act of vigilance becomes meaningful. We are observing the universe, maintaining a connection to something far greater than our everyday concerns. When it finally happens, the response will be global. Instant communication means everyone will know within minutes. Social media will explode, though not as dramatically as Betelgeuse. News organizations will scramble to explain what's happening. Scientists will rush to their telescopes. And billions of people will look up, trying to find it in the sky. For a few weeks, astronomy will dominate conversations. People who never think about stars will suddenly care. Children will learn about supernovae in school. Artists will create inspired works. Writers will craft stories. The event will ripple through culture in unpredictable ways. Then, gradually, it will fade from attention. Supernovae will still be visible, but familiarity breeds indifference. Other news will dominate. Life will return to normal. For a year, most people won't think about it often. In 10 years, it will be a historical footnote. For 100 years, just another entry in the astronomical catalog. But the impact won't disappear. Everyone who witnesses it will carry that memory. The night the sky changed. The moment we watched a star die. That becomes part of personal history, woven into identity. And the science continues. Long after public attention fades, researchers will still be analyzing data, refining models, testing theories, the supernova becomes a permanent fixture in astronomical literature. Papers will reference it for centuries. It becomes the standard against which other supernovae are measured. Betelgeuse's death will advance our understanding of stellar evolution. We'll learn things impossible to discover any other way. The data will be scrutinized, debated, reinterpreted. New questions will emerge. Some will be answered. Others will persist for decades. That's how knowledge grows. Not through sudden revelations, but through accumulated observations, tested against predictions, refined through debate. One supernova won't solve everything, but it'll move us forward. That's enough. The universe doesn't reveal itself all at once. It requires patience, persistence, careful attention. Betelgeuse is teaching us even before it explodes. About stellar structure, mass loss, nucleosynthesis. The explosion will be the final exam, testing whether we understood the lesson. We're as ready as we'll ever be. Devices are built. Teams are trained. Protocols are established. When Betelgeuse explodes, humanity will react with coordinated precision. Thousands of people work towards a shared understanding. That coordination itself is remarkable. A global species acting in harmony, focused on pure knowledge. No profit motive drives this. No territorial advantage. Just curiosity. The desire to understand. In a world often fractured by competing interests, astronomy offers rare unity. Everyone benefits from the knowledge. No one loses when we learn. Betelgeuse doesn't care about any of this. It doesn't perform for us. It's just a star, subject to the laws of physics. But we care. We've invested time, resources, and attention. We've built our understanding around stars like this. When it explodes, we'll watch, not because we have to, but because we want to. That wanting matters. It's what makes us human. The drive to understand, even when understanding serves no immediate practical purpose. We study supernovae because they're there, because we can, because the knowledge itself is valuable. And when that light finally arrives, when Betelgeuse's death announcement reaches Earth, we'll be here. Watching. Recording. Understanding. Adding one more piece to the infinite puzzle of existence. The star will die. We'll learn. The universe will continue. And somewhere in that continuation, meaning emerges. Not given. Created. By us. Right now. As we wait for the sky to change. So we stand here, citizens of a moment, watching a star that might already be dead. The light that reaches our eyes tonight left Betelgeuse before Columbus set sail. We are seeing history, not current events. That time lag creates a strange relationship with reality. Somewhere in the vastness between here and there, photons are traveling. Maybe they're the last normal ones, carrying an image of Betelgeuse as it was. Maybe others follow, carrying the flash, the explosion, the transformation. We won't know until they arrive. This is astronomy's fundamental constraint. We're always looking backward. The present is inaccessible. We study the past and call it observation. Betelgeuse could have exploded last week. The information simply hasn't reached us yet. No way to check. No faster channel exists. Light speed is the universe's speed limit, and we're bound by it. That limitation used to frustrate early astronomers. Now we've accepted it. We built our entire field around it. We turned the constraint into methodology. We can't see the present, so we study how the past becomes the present. We measure time through light's journey. When Betelgeuse's supernova light arrives, it'll be carrying a message 6 centuries old. The star made a decision in the 1400s. We're waiting for the announcement. The explosion has happened, or it hasn't. Both possibilities exist simultaneously in our experience until the light resolves the uncertainty. Quantum mechanics talks about superposition. States exist simultaneously until measurement collapses them into a single reality. Betelgeuse is our macroscopic version. Simultaneously exploded and unexploded, depending on your frame of reference. From the star's perspective, it was either one or the other. From our perspective, it's both. That's not mysticism. That's relativity. Information can't travel faster than light, so distant events haven't happened to us yet, regardless of what happened there. Our present doesn't include Betelgeuse's present. They are disconnected, separated by distance and the speed limitations of causality. This creates odd implications. If Betelgeuse exploded yesterday, it's already a supernova. Just not for us. For someone positioned differently, maybe closer, it already happened. For someone farther away, it won't happen for centuries. The event's timing depends on where you're standing. There's no universal now. People struggle with this. We want objective reality, fixed facts, definite answers. The universe doesn't provide them. It offers perspectives, reference frames, relative truths. What's simultaneous for you isn't for someone moving differently. What's now for you is past or future for someone positioned differently. Betelgeuse forces us to confront this. We're waiting for information about something that either has or hasn't occurred, and we genuinely don't know which. Both possibilities are real until light arrives and shatters our uncertainty. The philosophical implications extend beyond astronomy. How we understand time, causality, existence itself, all get challenged by cosmic distances. We think we inhabit a shared present. We don't. We inhabit overlapping light cones, regions of spacetime connected by possible causal relationships. Betelgeuse sits outside our current light cone. Its present is inaccessible to us. Whatever is happening there right now, we cannot know for at least 642 years. By the time we find out, it will be ancient history. The present retreats forever from our observational capabilities. This isn't a limitation. It's structure. The universe is constructed this way. Information travels at the speed of light. There are no exceptions. That creates a fundamental line between knowledge and ignorance. We can know the past. The present is uncertain. The future is inaccessible. Betelgeuse's supernova will teach us this viscerally. We'll watch something that already happened centuries ago. The explosion will be news to us, but it will be old news to the universe. We are always behind, always chasing, never reaching the present moment of distant objects. Some find this depressing. We'll never truly know what's happening now in the broader universe. By the time we see it, it's history. But consider an alternative. If we could see everything at once, if distance didn't create a delay, causality would be broken. Effects could precede causes. Time would lose its meaning. The light speed limit protects causality. It ensures that effects follow causes. It creates an arrow of time, a direction, a structure. Without it, the universe would be chaotic. With it, we have order, predictability, and functioning physics. Betelgeuse demonstrates this beautifully. The star follows rules. It burns fuel, contracts, heats up, and eventually collapses. Each step inevitably leads to the next. The sequence is deterministic. We can predict it without seeing it. This could be because causality is maintained, because the speed of light limits information, because the universe is structured. When the supernova finally becomes visible, it'll confirm what we already predicted. Or it will surprise us, forcing us to revise our model. Either way, we learn. The universe teaches through examples. Betelgeuse is one example among billions. But it is our example, close enough to study, bright enough to see, time to happen when we have the tools to understand it. That timing is arbitrary. We didn't arrange it. Betelgeuse doesn't know we exist. It died millions of years ago, according to stellar physics. We happen to develop intelligence in its final chapter. Purely by chance. But by chance we can exploit it. Humanity's window of technological capability is narrow. We've had serious astronomy for maybe 400 years. We'll probably have it for thousands more, barring catastrophe. Betelgeuse's supernova might occur during this window. Or it might not. The odds favor it happening eventually, but eventually is vague. If it happens next week, we're positioned to study it thoroughly. If it waits 10,000 years, future civilizations will have that opportunity. Either way, someone benefits. Knowledge enters human understanding whenever it comes. Timing influences who learns, not whether the learning happens. This long-term view helps. We're not racing against time. We're participating in an ongoing project that spans generations. Astronomers today prepare the equipment, develop theories, and train students. Those students will train others. When Betelgeuse explodes, whoever survives will carry on the accumulated knowledge. Science is cumulative. Each generation builds on the work of the previous one. Today's observations of Betelgeuse provide information for tomorrow's understanding. The supernova, when it occurs, will be explained through the frameworks we are building now. Our preparation is not wasted if the explosion is delayed. It's an investment in future knowledge. And the preparation itself teaches us. Building instruments, refining models, coordinating observations, all develop skills and understanding applicable beyond Betelgeuse. We don't just wait. We are improving. Every observation, even of an unexploded star, adds to the data. Each refinement of the model increases accuracy. Work continues regardless of when the key event occurs. This patience is characteristic of astronomy. We study processes that take longer than a lifetime. We ask questions that we ourselves may not be able to answer. We contribute to understanding that benefits people we will never meet. It requires a special mindset. Long-term thinking. Delaying gratification. Belief in collective progress. Betelgeuse embodies this perfectly. We're watching. We're waiting. We're preparing. We don't know when it'll happen. We know it will happen. That's enough. The act of watching itself is meaningful. The preparation is valuable. The knowledge we are building is important, whether there is a supernova or not. Because ultimately, this isn't about one star. It's about understanding how stars work. Betelgeuse is a case study, an example, a test subject. What we learn applies to countless other stars. The principles are universal. Physics doesn't change from one star to another. Only the details change. When Betelgeuse explodes, it'll validate or challenge our understanding of those universal principles. Both outcomes advance science. Validation means our models work. Surprise means they need improvement. Both are progress. So we watch. We wait. We prepare. Betelgeuse hangs on Orion's shoulder, burning its last of fuel, approaching its inevitable demise. We can't stop it. We can't predict exactly when. We can only observe and understand. That's enough. That's all. That's the meaning of doing science. Watch the universe do what it does and learn from watching it. The star will die. We will see it. We will understand it better than any supernova before. And then we move on to the next question, the next mystery, the next opportunity to push understanding forward. Because that's what we do. That's what makes us who we are. We look up. We ask. We work to understand. And the universe, indifferent yet generous, provides countless opportunities to learn. Betelgeuse is one opportunity. Just one. But it is ours, and we are ready, and when the light arrives, carrying news of an explosion that happened centuries ago, We will be here, watching, recording, understanding. Another piece added to the endless puzzle. The star will change. We will learn. And somewhere in that learning, meaning arises. Not given. Created. By us. Through our attention, our curiosity, and our patient work to comprehend what we see when we look up at the night sky and see it change.